Hey Andrew.
Hey Hong, how's it going? Can you hear me?
Good. Yes, I can hear you.
Hey, so this is being live streamed right now. I'm
That's
just going to
cool.
update the website with the link, and we're just
You
dealing with.
just updated.
I'll do it right now, and maybe you can just take
Okay.
see if it's working. And then I'm
Yeah,
just dealing with a
sure.
few other tech issues. And then I'll. I'm glad to hear that it's working on your end, though.
Yeah,
Try a screen share right now. Maybe help.
yeah,
Thanks.
it works pretty nicely.
Great.
Yeah, we only have the Zoom link on the website. And that Zoom link.
Sorry, I'll update it in a second, Hong. One second.
Okay. Yeah, sure. By the way, that Zoom link requires login.
Okay, Hong. The live stream link should be up on the website now. Let me know if you're able to access it and it looks okay.
Okay.
The one last issue is they haven't given me an adapter I need to use the micro to connect the microphone to Zoom from the room, but I'll let you know when that happens.
Okay. But for the other presenters, will they be able to connect their microphone?
Yeah, so
Zoom?
there's an external microphone here. And if it works, it's just going to constantly be on, so they won't have to set up their microphone.
Mm,
One thing they'll have to do though is screen share. And if you notice that like there's a problem with screen sharing or somebody didn't share their
yeah,
sound or something, maybe you can just
sure. Yeah, especially if there's sound that's playing on their laptop.
great. Yep. Yeah,
Yeah,
exactly.
there
There's
might be potential issues.
yeah. So if any of those come up, just maybe you could remind them. And we'll be able to
Yeah.
hear you.
Okay. By the way, yeah, I just checked the live stream link and it works pretty
Oh,
nicely.
great. Okay, thanks. So I'm good. I'm done with the hybrid stuff. And so great. Thank you. Thank you for testing that. Okay, so this microphone doesn't show up on my. Can someone on Zoom talk? Just we want to test the audio here. Anyone on Zoom want to talk? Z-Win, do you want to talk? I see you have your video on. Just so we can test something out. Oh wait, sorry. Did you say something? I can't hear you.
Can you go back to the using the microphone?
Oh, you're right. You're right.
Yeah.
Yes. Oh, great. This is there now. Okay. Sorry. Can you say something again, Z-Win?
Can you hear me?
I thought I heard something.
No, can you go back, Andrew? I think.
Oh,
it's this
sorry.
one, the bottom one.
Maybe there's some
Is it
problem on
microphone
my side.
speakers?
Oh, okay. Sorry. Can you say one more thing?
Test.
Okay.
With
It's coming
that-
with speakers, yeah.
That's not going to the.
Sorry, we're just you can't see us. We're debugging some AV issues here.
All right. Do you have any kind of audio that you play on here?
Oh, actually, he's gonna keep. Actually, let me just. Yeah. So somebody over Zoom say something.
It's like microphone.
Probably external headphones. Oh, microphone. I see. Yeah. Probably Mac.
Okay, I need somebody to say something.
Anybody on Zoom? Can you just say something? We want to see if we can hear your voices.
Let's go.
Test.
Oh, it looks like somebody's trying to talk, but we can't hear them.
Where?
Can you hear me?
Oh, wait. I think I heard something. Can you say that again? Maybe the volume is just down low.
Yeah.
Oh, great. Yes.
Can you
yes, we
hear
can
me?
hear you. Yes, we
Okay.
can. Thank you so much. Okay,
Nice.
great. Meet 2, is that?
Uh,
eMeet 2,
no.
is that, should I, what was that?
No, no,
called?
no, no.
Don't use that, okay. So it's just-
EME 2 is that little box up there, so actually we can use that.
Yeah,
It's looking for it.
but
So,
let's test this though.
hold on, you see stuff right there?
I do, yeah.
All right.
So just, can people,
I'm sorry. Just apply for 1 second.
he said something. Hong, can you hear us?
Yeah, look, it's popping up right
Yeah,
there.
I can hear. Yes, I can hear you.
Sounds good?
Yeah, it's great.
Okay, great.
So, you got it?
I think we do, thank you.
No worries.
But I think,
Okay, I think it's fine.
yeah, I think we're good.
The only thing is I can't make this full screen, right? Because it's Google Slides.
We can't.
Not if
So
I'm
I'm just gonna
sharing
set
to
up
Zoom.
My
Do I
other,
have to share to Zoom?
oh, sorry.
Do I have to share to Zoom?
I think that's the only way to do it,
Okay.
unfortunately.
For them to-
You want to use my computer?
No, it's just
Okay.
anyone who has their presentation on Google Slides will not be able to share to Zoom and get it full screen. But it's okay, it's just
Oh,
the
I see,
tab
I
at the
see.
top. I think it's fine.
Okay. Okay.
I'm gonna leave
There-
now.
there should be a way for you to be able to
Really?
do that, but. Google-
Wait, where did my laptop go?
All right,
Oh,
so in Chrome, go to view. Your full screen. And then.
Okay, so
stop sharing.
let's make a slight change. If you wanted to, if you're originally planning to use your slides, but you no longer can because of the setup, email me your slides. You're gonna go. So we'll change the order slightly. So that we'll have everybody who uses my computer.
You're
We
amazing.
know it's me
You're
there.
amazing. How about
Yeah.
that? There you go.
Great. Keith.
I like that. That's cool.
Yes, the people who will inspect using my computer.
Okay.
Who all needs, okay, so if you're originally, we can no longer support people using their own laptops in the 9 a.m. session. Or without some extra work. So if it's possible, that'd be great if you could send me your slides and present on my computer. And then you're gonna go first. I'll just put my computer up and we'll just go through everyone. And then we'll transition to the people who have reports. So if you were originally planning to use your own computer, just send me your slides over email and we'll go through with that. Sound okay?
Never mind. So we're setting your computer back up.
That's right. Yep.
Let me. Here, I'll get this stuff. Bye.
Oh yeah. Actually, let me set that up. Here it is. Let's see.
Hi, everybody. My name is Susie Kühne. I'm professor at the Goethe University Frankfurt and affiliate professor at them.
Okay. Oh, put this here. Okay. Let's try again.
At the IBM Watson AI Lab. And today I want
Okay, that's good. All right. And then I'm just going to download everybody's stuff. Okay. And change the order.
Just remember that this got a plug-in, so I think. Oh, yeah, you got an old one.
Oh, this is a new one. It's a new one.
It's a new one?
Yeah.
Really? Oh, wow.
Yeah.
So-
Oh wait, there's now feedback with this. Should maybe from. I see. Sorry, did somebody say they sent me their slides? Maybe it's just a delay. You can just email those slides. Anyway, you were also. Okay. Maybe it's just a delay. Yeah, that's right. No. It's just a delay at that. Oh, I just got it. Yeah. Oh, okay. Okay. So how many of these can I expect? I think there's just 2, right? Oh, you also, okay. Yeah, I should invite them. Oh, yeah, sure. You want to invest in it? Or- Yeah. Oh, yeah, don't worry. Here's just a 9 AM session. Here's a 9 AM session. There actually be getting through, right? You, and you. Tell you. I spent mine on. It's only, if you're on TMT, you should be okay. There's somebody who's coming up who will have the computer. Okay. But if not, you're planning to use your own computer. If you're planning to do that, if you change your plan, we'll use my computer instead. Okay. Yeah, no problem. Okay, I got one from Ben. Anybody else? There should be 3, I think, total. Okay, great. All right, so in the meantime, all right, thank you so much, everyone, for coming. I'm sorry for the technical issues. As you can see, there's quite complicated setup here to get sound working. I apologize for that. But I'm really excited to see everyone in person here. Just to give you a quick overview for the day, we're going to have 2 paper sessions, one in the morning, one in the afternoon, that are covering the different papers that people submitted to the workshop. And in between, there will be some invited talks. In the morning, Arsha Nagrani and Jeanette Bogue will be speaking. Then after lunch, David Brang and Carl Vondrick will be speaking. After that, we're going to have invited paper talks. These are mostly just papers at CVPR about sight and sound that are relevant for the workshop. Also, some other recent work on archive. And then finally, in the evening, there'll be 2 talks by Hilda Kuhn and Pedro Morgan. And before we get started, I want to thank all of the other organizers here. In particular, I want to thank Arsha, Daffy, and Rohan and Hong, who have been dealing with a lot of technical issues and who have been doing a lot of work throughout the conference. You'll see them later on today chairing different sessions as well. And if you have any sort of technical issues, the person to ping is Hong. He should be over Zoom, and you can just send him a chat. Great. So, so as I mentioned, there's that slight change of plans. If you were originally planning to use your laptop, send me an email. And I still only have one. I still have one from Ben. So I need the if it's just a Google slide, you could also just send me the link. Oh, you sent me a link. Okay. Okay, that's weird. And the location of the posters should be near the catering area. I think it's the DE area in the lobby. Yeah, the lobby of the DE area. You can we'll have throughout the day. You're welcome to present your poster during any of the breaks, and in particular during the lunch session. Again, the poster session is also optional. The main event will be the talks. Oh, thank you, Gloria. I just got yours as well. Okay, I think there's a third one that I haven't gotten yet. You sent it to me? Okay. Oh, Google Drive. Oh, I just got yours. Okay, perfect. Okay, so in this first section of the paper presentations, we're going to have a slight change of plans. The people who emailed me, you're going to go first, and then we're going to have a Q&A session after that, and then we'll transition to the other people who submitted their presentation over CMT. Okay, so first up is going to be, oh, and I should say, by the way, it's a 5-minute presentation, and there will be no questions afterwards. All the questions will come up during the Q&A sessions, and there'll be several that will be presenting at once. Finally, also, I want to check the people who are over Zoom, who are presenting at this session. Is anyone doing a live Zoom presentation of their during the 9 a.m. session? Who all is doing that? Okay. Can't remember. Okay, great. So let's get started then. First up will be learning sound localization better from semantically similar samples. Sorry, did you want to do it over PowerPoint or
just like representation? I mean,
Okay.
presenter.
okay.
Sorry, excuse me. Could you share the screen?
We're just getting it set up right now.
Okay, thanks.
Sorry for that. I'll let you know, and then Hong, maybe you can let us know if there are any issues with that.
Yeah, sure.
Okay. And the next up will be Ben and then Gloria. Okay, I don't. Here you can. There you go. Oh, good. Okay.
Good.
Oh, wait, so I need to do the screen share on this one. Sorry. 1 second. Yeah, sorry. 1 second. That's fine.
So does mic works? Okay, good. Let's start. Okay. Yeah. Hello, everyone. Today I will present our work learning sound localization better from semantically similar samples. This was published in ICASS 2022. My name is Jinsik. This work was done in equal contribution with Arda Senozak, Hyunggon Ryu, and the professor In-Seok Kwon. So the goal in sound localization is to design a model that predicts sounding sources in a visual scene. To answer this question, audio-visual sound localization field is recently growing fast with lots of important works. But among these works, most of recent deep learning-based approaches use contrastive learning. So existing audio-visual works use contrast learning by assigning corresponding audio-visual signals from the same video source as positive pairs, while randomly selected mismatched pairs as negatives. Ideally, this seems plausible because the audio and the image that comes from the same source are likely to be corresponding to each other, while the audio and image from different sources are likely to be less relevant. So, however, in practice, this random selection can cause false negative pairing that contains semantically similar samples to the negative pairs. Therefore, these false negatives have a harmful effect on the model training. We also make another important interesting observation about the response maps of semantically similar samples. So semantically similar samples can give similar response maps to the corresponding audio-visual pairs. So let's look at some examples. We will keep the image same, fixed, and then pair it with different audios. So this attention map is obtained with using an audio-visual pair from the same source. And here, the core image is same, and it is paired with semantically similar audio, but from different video source. So the obtained localization response is very similar to the original pairs. And as expected, pairing with unrelated audio gives random results. So from this observation, our idea in this work is to explicitly mine semantically similar samples to a query audio-visual pair, and using their multiple response maps directly in the contrastive learning with multiple positives rather than single positive item. So now let's see how we selected these positive samples. Like as a first step, we obtain a set of unlabeled features from training set for each modality by using some pre-trained models, let's say pre-trained self-supervised sound localization model, or it can be pre-trained ResNet trained on ImageNet, or VGG sound network trained on audio modality. So after that second, for every sample in the training set, we compute the just k nearest neighborhood by using feature distance. In our case, percent similarity. And next, we select positive samples randomly within that neighborhood. This process is repeated for both audio and visual modalities. Therefore, we obtain positive samples from each modality for the query pair. So note that existing self-supervised method in computer vision constructs positive pairs from a single instance by applying data augmentation. In our case, we use semantically similar but different instances as positives. So this figure illustrates our model architecture. After selecting hard positive samples, we construct 4 different positive pairs and multiple, way more number of different negative pairs. So because of these additional positive pairs, our model is learned with like 4 times more supervisions, 3 times more supervisions. So these computed response maps are directly used in contrastive learning formula. So these are some qualitative results on VGG SS dataset and like the computing method. And these are the results on Flickr test dataset. So the middle one is the proposed method. And the proposed method like achieve competitive performance on both VGSS and sound Flickr test dataset. So in our previous ICAP submission, we used pre-trained self-supervised sound localization network to find nearest neighborhood for audio and visual modalities. So this was originally reported numbers. And we just replaced this network with pre-trained ImageNet and VGG sound network. And we just recently, with the new experiment, we got significantly higher performance. So I'm just introducing the numbers here. Yeah. So in this paper, we observed that semantically similar samples can give similar response maps to the corresponding pairs. So from this observation, we propose how to find semantically similar samples and incorporate them into contrastive learning. And this is different from widely used self-supervised contrastive learning, where augmentation plays a major role in constructing positive pairs. And the proposed method achieved state-of-the-art performance on the standard benchmark. Thank you.
Okay, next up, Ben. And just to check, is everything going smooth over Zoom? If you're able to hear it? Okay, I think that is a yes. Okay, so
Yeah.
okay, great.
Okay. Good morning, everyone. This is Ben. Our work is entitled Audio-Visual Event Localization, a well-recursive joint co-attention. This is a joint work by Illinois Tech and Cisco. My advisor is here. So for a short introduction, so what is an AVE? So if the definition of AVE is given a video sequence, an AVE is defined as an event that can both be heard and seen. So our task is trying to use both audio and visual information to predict whether an input video has an AVE and what is that AVE event. For this particular purpose, we propose an approach using recursive fusion with joint co-attention mechanism to tackle different representations from different modalities, i.e. here is audio and visual. So for our motivation, first of all, in multimodal learning, fusion is one key challenge. And second one is the co-attention mechanism allows for mutually attending of feature from different modalities. Such by intuition, we could draw like a more robust representation for the later task. And here comes the question. So will our recursive representation fusion help the model to learn this robust representation by our intuition? Here comes our methodology. This is our general architecture. If you look at the middle part, our joint co-attention layer allows two different modalities to attending to each other by multiple times, of course. So technically, we can repeat this process like multiple times, but here we are using more like we are for each different layer. We are not reusing the encoder. So basically, the memory usage will grow. But if we haven't explored if we are reusing the encoder, what is the performance? That's part of the future work though. So for quantitative results, we test only on one data set that is called, I think it is proposed in ECCV 2018, but we compare with different methods here. So among all of them, our method reaches to the state of the art. And here are some qualitative results. As we can see, both different representations allows to better capture what is the AVE inside the video. If you can see the attention map in the third line, so basically we can even capture two different locations within the video that have the same AVE event. If you look at the top the bottom right, there are two locations that indicate playing guitar. And here are some more qualitative results. We show the attention map that are drawn from both representations. So if you can see, there are different AV events like a baby crying. You can see our model really pays attention to the location that is both heard, can be both heard and can be seen. So this is kind of like a proof of our joint co-attention mechanism really works. And here comes our conclusion. So first of all, we propose a recursive fusion method, and also the intensive experiments demonstrate the effectiveness. And thank you.
Okay, great. Next is Gloria. And you had a Google slide, right? Okay, good. All right. It's not sure. Oh, okay. Yeah, I don't. Oh, I should. Okay, maybe I'll do that. Great.
Hello, this is a joint work with Venkatesh Kadandal, who was not able to come, and Juan Montesinos, who is here as well. So first, let me define the problem we want to address. Given a video with a human face and a voice, our aim is to estimate if the frames and the voice are synchronized or not. And for that, we train a model in a self-supervised way by using positive and negative pairs. This is the model we propose. It is basically a multimodal transformer which ingests both audio and visual features. The audio features are extracted from mail spectrogram by using 2D convolutions with skip connections. Then the visual features are extracted from frames cropped around the lips and using 3D convolutions and skip connections. Then the core of our model is the multimodal transformer that we denote as vocalist for vocal lip sync transformer. And it's formed by 3 cross-modal attention blocks. The first one, in yellow, the role of the source and target modalities are swapped between them. And we address 2 different domains, speech and singing voice. So first, let me show you with an example what are the differences between both. We will listen to the same content, first spoken and then sung by the same person. Oops, sorry. So.
Yeah. Huh. Oh, wait, somehow.
It would be better.
Wait, can you try?
There is some echo.
When you're gonna play something.
Have noticed. The baseline methods, and we have considered different context window sizes. We can notice across all methods the results improve when we increase the context, and in all cases we get the best results. Here some results on singing voice with the a cappella dataset. Again, we consider different context sizes. Here we can notice that the results on the accuracy are worse than in the case of speech. This happens because the synchronization task is harder in singing because of these sustained phonemes. And here we can also notice that the margin improvement when we increase the context size is larger than in speech. And finally, we show how the visual features learned for this self-supervised task in synchronization are useful for the task of singing voice separation. So here we have a mixture with different voices. There is some audio here as well.
Oh, sorry. I think it should work. I think I fixed it, but
Yeah,
I think you should try playing it.
it was playing, it was playing.
Oh, you were.
But
Okay.
we didn't hear it.
Oh, I see. Okay. Okay. Try. Okay. I think. Okay. Let's do it again.
The voice corresponding to the target trade. Okay, there are 3 more.
Okay.
Coming. And for that, we have taken the YNet, which is basically a unit conditioned on visual features. First, I will play 2 results with the YNet using 2 different subnetworks, visual subnetworks that have been trained from scratch in order to solve the source separation task. Now,
Sorry.
one more. Now I will show the results using the same unit, but now with the pre-trained visual features from the synchronization task. It's better in the last one, especially in the silence part, where we get less interferences. So for quantitative results on source separation, please refer to our paper or our poster. And you have more demos and very soon the code as well in our project webpage. Thank you.
Great. Apologize for the technical issue there. I'll continue with this setup for the morning session, but then hopefully the afternoon session will have a different solution.
like I kind of like did some empirical experiments, and like indeed somehow like heuristic filtering of those data sets do help training model. But in general, when you train in really large scale, I think like proper loss design with some regularization would be enough to handle those cases. But yeah, it really depends on data distribution. But from my previous experiences, like so far, the models are doing it with implicitly, but explicitly dealing with those problems would definitely improve the performance.
Other questions?
Thanks so much. Are there
I-
any
I-
other questions?
Yeah, if not, I had a question. I was wondering what you think there was in the second paper, yeah, the second paper, the use of semantics for sound localization. I was kind of curious to what extent you think you can get by with just semantics alone, and how much you need sound. Yes, for you, yes.
So, I'll try to restate your question.
Yes.
So your question probably be how much does the network training rely on the semantics of the sound and the images? Is that the question?
Yes, yes.
Okay. So our intuition is actually drawn from like the correspondence between the audio representation and image of representation. But from our experiment, these correspondence sometimes can be unreliable. So that's if you look at the numbers of the experiments, so that's why the accuracy of predicting the category can be around like 60-ish. So basically, I think there are still some room for improving the correspondence of these two modalities. That there is definitely room for that. We haven't figured out a way to do that for now. So yeah, that's my answer.
Thank you.
Thank you.
Are there any questions for the speakers? Well, if not, let's thank them again.
Thanks so much.
Okay, so now we're going to go back to the normal schedule. All the people who submitted their presentations to CMT are now going to be covered here by Daphne. And there's one little wrinkle we found here, which is that if you're playing sound, there seems to be a lot of feedback. The way this setup is working, so just tell Daffy when that happens, and he's gonna.
I'm just gonna
mute
mute
this,
Zoom.
and he's gonna turn the volume up on this simultaneously, and then the other way around. So just let us know when you're gonna play sound. I know that's not a great setup. We'll have something else in the afternoon to try to deal with that. I apologize for the inconvenience. So yeah, great. I guess the first one is quantize. Oh, go ahead.
Okay, so first paper is quantized GAN for complex music generation from dance videos, presented by Yeju. Wait.
Good morning, everyone. So I will first want to thank the efforts from our organizers and hope that every one of us can have a great time in the following week after 3 years of online meetings. So
Sorry about that.
yeah.
Yeah, you need to just share. Sorry for the delay.
Just find the.
Oh yeah.
Where's that the Zoom?
We can. Oh, here. You can just unshare while you go through the Slack.
So
This should just be, yeah, do you see it?
no video.
Oh, no video, you don't. Yep. Good, good. Yep. And then just do it. Should be the right link. I think it was just some Zoom thing. Okay. Okay, good, good. That
No,
was
it should
good.
do it.
Great. Yeah, you need to share audio. And when you do the screen share audio. Click the checkbox. Yep, great. Awesome.
It's an issue with the. Wait, is this? This looks okay.
Yep, you're doing it. Oh, yep, just gonna plug that in. You're doing the screen share. Great.
Okay, sorry about that.
Keep your volume up, and then when somebody plays sound.
Because you can think so.
Thank you. Yeah. So my name is Ye Zhu. I'm a PhD student from Illinois Institute of Technology. So today I'm going to present our work, Quantize the GAN for complex music generation from dance videos, which is a collaborative work with Snapchat and Princeton University. And you can also refer to the link here for more code and samples.
Oh, sorry, we are seeing your presenter's view. Are you able to swap the displays?
Can you share the other screen? Oh,
It's okay.
Yeah, now works.
Okay. So in this work, our goal is to generate music from dance video inputs.
Yeah, that's fine.
So we start by investigating different music representations. So as we mentioned here, most existing works that use symbolic music representations, such as 1D piano roll or 2D MIDI events, they can be used for synthesizing high audio quality signals. However, it is limited that we have to specify a predefined instrument type, and they are using the predefined standard music synthesizer for decoding back to the raw audio domain. So in this end, we aim to use a different music representation, which is a learning-based quantized vectors. So in this way, we can find a unified representation with relatively high compression ability as an intermediate way to learn this kind of motion and visual, as well as the audio mappings. So we propose a dance to music and framework, which takes the motion input and also the video frames as input. And then we fuse these two information, which is used later for generate the quantized again. And then we quantize the vectors. And then we perform a codebook lookup process, and then use a learning-based synthesizer to decode such music representations back to the raw audio domain. So our experiments are performed on two data sets. The first data set is AIST++, which is a subset of the AIST dance data set that are includes dance videos filmed in the clean studio environment. And also, in addition to the existing AIST++, we also collect our own TikTok dance music data set, which includes the dance videos annotated and collected from in the wild environment. And also as evaluations, because music is something that is relatively difficult to perform evaluations. So we try to assess our generated quality from different musical aspects, including the beats coverage and beats heat, which measures the rhythm feature, and also the genre accuracy in terms of the music type and diversity, as well as the dance music coherence and also the overall music quality from both objective and subjective points of view. And here we show some qualitative examples of the generated music. Also, as follow-ups, we actually also explore the proposed dance to music generative task via the recent diffusion probabilistic models. So please also check our conditional discrete contrastive diffusion project, which is a relatively general conditional framework that not only works for dance to music generation, but also that can be used for text to image and other conditional generation tasks. And that's all for my presentation today. Thank you.
And I think that's the very helpful AV tech. I think we finally fixed the audio issues. Fingers crossed. You shouldn't need to do anything funny when you play sound. So it should just work. Oh, I think we did this one right now.
Right, so next step is a modeling in here, audio classification of paired products. It's Roman.
Hi everyone, I'm Romain Loiseau and I'm present to the work we did with colleagues from IRCAM, Imagine and my advisor, entitled The Model You Can Hear. Well, it's running maybe entitled A Model You Can Hear, Audio Classification with Playable Prototypes. In this work, we propose to learn a classification model that relies on the reconstruction of input sounds by a very few prototypes. To this end, we assign to each class of the dataset a prototype that will be learned alongside gain and pitch transformations to reconstruct samples of this given class. Our goal in this paper is to classify large audio collections while relying on an easily hearable summary of them. Indeed, many recent methods rely only on high-dimensional latent representation of the inputs. And even though those methods often perform well, they are very difficult to interpret. In this paper, we adapted the transformation invariant clustering paradigm for audio in a supervised setting. We provide an audio classification model based on learned prototypical sounds that can be heard directly. Our model produces state-of-the-art results for speaker and instrument classification while remaining easily interpretable. For each input audio clip characterized by its locked MEL spectrogram, each prototype provides a reconstruction of the input by being adapted in amplitude and pitch shifted. At training time, each prototype is assigned to a specific class, while at test time, we assign the input to the prototype that best reconstructs it. The reconstruction model is the following. Each learned prototype produces a reconstruction of an input at time t by being shifted in amplitude and in pitch. In our model, both values of the prototypes and deformation networks are learned parameters. So we train the model by supervising jointly the reconstruction error of the correct class and the cross entropy on the reconstruction, so that each prototype specializes to its assigned class. After training, we can hear and look at the prototypes to get the essence, the timbre of each instrument or speaker. We trained our model on both the Sol and Negri speech datasets, and here you can see 5 of the prototypes learned on those datasets. Learning those prototypes only for reconstruction, we get very good results at classifying audio clips compared to a simple convolutional classifier, here denoted as a direct classification, and also compared to a network that compares the latent representations from an autoencoder to learned latent prototypes. To conclude, we adapted the transformation invariant clustering paradigm for audio in a supervised setting, and we provide an audio classification model based on learned prototypical sounds that can be heard directly. Our model will choose the state-of-the-art results for audio classification tasks while remaining easily interpretable. And you can see on the website there are learned prototypes you can go to here and look at them. Like, I'm making I got time, but maybe we can wait to learn them. It works. Yeah, it's perfect. So as I said, I can deform every prototype using a gain and a pitch shift profile. So we can learn, for example, for the clarinet, the 3 deformed versions of the prototype. So here, so you just have the whole prototype without deformation. So it gets the essence of the instrument, and then you can apply any deformation you want to look to hear at the learned prototypes, and you can play Mario theme if you want. So basically, each prototype reconstructs an audio sample, and you then learn the essence of each instrument. Thanks for your attention.
So next paper is audiovisual audio vocalization in hypersensitive videos. Child Monk.
I just send my slides to go down, or do you want me to?
Do you wanna? It's not.
Okay.
I might not want it.
Can we do next maybe the?
Yeah, how we skip you for now?
Can you mind quickly?
Okay, thank you.
Okay, in that case, let's do our next Q&A session. So it's basically just like for those two last papers. So are there any questions or?
And if you do have a question, please come up to the mic. Yeah, so I had a question about the first paper. I was curious what cues you think the model is using to synchronize the music with the dance.
So thank you for your question. So in terms of the like which attributes contribute to, I think there's a difference. So in terms of the reasons such as beats, between correspondence between the dance and music, we think the motion data input plays a more important role compared to the visual part. However, in terms of the music genres instead, I think for that part, the visual frames could also be very helpful. So does that answer the
Yes, thank you.
Thank you.
Are there any more questions for this paper or? Yes, please.
Thanks. Yeah, cool paper. It's also a quick question. So I noticed in the examples you played of the generated music that I was mostly hearing the beat being generated. So I was wondering if you have had the chance to do any analysis or any thoughts about whether your model is also capturing harmonic components, instruments and chords, or is it mostly generating beat patterns?
Well, I think it's so. Thank you for the question. It's very insightful. Actually, in the preliminary results, we show the beats are more easily to be captured, especially given the strong motion representation data as input. However, there may be the sound problem, but there's also the reason. In addition to the reasons, but also the musical part that is along generated along with the beats, but which is kind of more difficult to hear in this case. So we could invite you to look at our more samples and also which kind of shows the other side. But we agree that in this case, especially given the inputs from motion and dance, we think the motion part plays more important roles in the beats generation, but the other can also, it's also an interesting aspect to look at the future. Thank you.
Are there any more questions? So shall we go? We're running a bit behind schedule, so maybe we can go to the next paper. Okay, so next presentation is a video one. The paper is called The Sound of Motion, Multimodal Post Motion Estimation for Video and Audio. And I'll just play the video.
Hi, my name is Ci. Today I present the sound of motion, multimodal host motion estimation from videos and audio. Sound occurred everywhere. When we hear some sound, we can imagine the pose or the motion. For example, this is rooster crowing. And wolf howling. For horse trotting, we can imagine how the foot is stepping on the ground, but we may not imagine the appearance of the subject, like colors or size, or the accurate location, or the tailful movement of the subject. So this is why we also need visual information. Humans experience the world through multiple sensory channels like vision, hearing, touch, smell, and taste. Image and videos are often used for 3D human shape and pose estimation. Many work studies the correlation between sound and motion. Much research stimulates the integration about videos and sound. However, there are few studies for animals. Our goal is to investigate multisensory integration to recover the 3D motion of horses. Our hypothesis is that audios can help to estimate more accurate poses. Because horses have half hooves and strong bodies, and they can produce characteristic and significant sounds when moving. Our method is to use the H-small model, a parameterized articulated 3D shape model that uses beta and theta for shape and pose estimation. We also propose two regression architectures for exploring audios as an additional information for regressing the H-small parameters. We have two blocks, one for visual input and another one for all modalities. We assume that during training, the network learns the correlation between main modality and auxiliary modality. We have text-to-fusion networks here to handle multi-modalities, the model fusion network and the early fusion network. The difference is that during testing, early fusion network needs both modality input, while the model fusion network can handle missing audio data. We also provide two baselines. One is image-only network, removing the audio channel. Another one is audio-only network, removing the image channel for pose estimation. The dataset we use contains videos, audio, and 3D motion capture data, recording horse subjects trotting on a treadmill. During training, we randomly pick 3 horses in dark colors. And during testing, we have 2 separate testing datasets. Test data 1 for the other 3 horses in dark colors, and test data 2 for a white horse. To show the network really learns from audio, we test the audio-only network with original audio and white noise.
Capturing.
From the table and the visualization results, we see that original audio outperforms the noise audio. The white noise will result in very rigid pose.
Capture.
We show a video example in test data 1 with all networks. We can observe that all networks perform similarly.
Capturing.
We show another video examples in test data 2. We see that the image-only and the early fusion network predict rigid legs, and the audio-only network and the model fusion network can still predict reasonable poses. Here is the table of quantitative results, which shows that the fusion models for 2 modalities outperforms the single modality, implying that the audios benefit the 3D reconstruction. More discussion can be found in the paper. To summarize, we utilize the H-small model and propose 2 regression networks for multiple sensory integration. And we show that the complementary use of audios and videos help to improve the 3D poses estimation from videos. Thank you.
So, Mr. Peter answer the question in the session. Did you do this already? Have not. Okay, so next paper is allowing sound localization better from semantic signal samples. It's whatever. Maybe go to the next one. Okay, so let's scalable video script synthesis.
Okay, so good morning, everybody. I hope everybody is doing well. Yeah, so today I'm going to be presenting SVTS, which stands for Scalable Video-to-Speech Synthesis. My name is Rodrigo, and this is a recent research project from our research group at Imperial College London. Yeah, so video-to-speech, as the name indicates, is basically going from video of a speaker's facial movements into the corresponding audio of what that person is actually saying from the silent video only, so no auxiliary audio. As one can expect, this is a pretty hard task. It can be seen as like a step forward from lip reading, which is a task I think most should be familiar with. So instead of predicting just the text from the lip movements, we want to actually predict the audio, which means that we need to model emotion, intonation, and all of these things that are not present in text. There are two, in my view, really exciting things about this task. Firstly is the fact that it can be trained on raw audiovisual data without any additional labels. This is unlike lip reading or text-to-speech, which require ground truth manual labels that have to be done by humans, and this is expensive, whereas we can just train on any video of speakers that we find. And the second exciting thing is that there's a variety of applications, such as, for example, in video conferencing, if the audio is either absent, corrupted, or way too noisy, we can just replace it with the audio that we predict directly from the video, or even this even has medical applications for people who can't produce voice speech. So we can use this model to produce speech for them based on their lip movements. So I just wanted to give a quick overview of the current state of the art in video to speech. So these are two works that came out in 2021. Actually, the one on the left is from us as well, and the one on the right came a few months later. And these were state of the art at the time when they were presented. So as you can see, the common trend here is that these training procedures are pretty complicated. Both of them have multiple losses. On the left, we have a bunch of comparative losses and an adversarial loss. On the right, we have an AV synchronization loss, multiple discriminators. We even have multiple generators. And this trend towards complex training procedures has been pretty consistent in video-to-speech literature in the previous years. Obviously, this is in an attempt to produce better and better quality of audio. The problem with this additional complexity that actually we experienced ourselves in our work on the lab is that it becomes harder and harder to scale this training procedure because we suffer, first of all, from slowness of training compared to a normal feed-forward network, because we've got all this fancy stuff. And secondly, we can experience a lot of training instability when having this complex training procedure, training for a long time on lots of data, especially in unconstrained settings. So these works actually, and most video-to-speech works, focus on small data sets, such as GRID. And although they produce good results for that nowadays, it's a shame that they focus on small data sets because, as I said in the previous slide, one of the most exciting things about video-to-speech is that it can be extended to any audiovisual data, so we can extend to really large data sets. So our new work aims to counter these shortcomings by presenting a simple architecture that we can easily scale to larger audiovisual data sets. So it's pretty simple. Basically, we train a video spectrogram predictor based on a ResNet plus Conforma architecture, which is common in lip reading, for example. And then we use a linear projection layer to project those encoded features into a spectrogram. So this is our end-to-end training. And during inference, we use a pre-trained vocoder to synthesize the waveform from the predicted spectrogram. And actually, one thing in our training procedure that I didn't mention is that we use a speaker encoder to model the voice characteristics that obviously can't be accurately derived from the video alone. So by using this simpler architecture, we can much more easily scale, for example, to LRW, which have been approached before in video to speech, but we get much better results than all previous approaches. So it's a substantial step forward. For example, in word error rate, we get less than half of any other of the previous approaches. And actually, we are the first work to extend to scale our method to LRS3, which is a substantial step forward in terms of scale and in terms of the constraints in the data set. And we actually experiment even by adding training data to LRS3 from Voxeled 2 in a total of more than 1,500 hours of training data. just to see if our model continues to scale its performance with even more data. And we find that this extra training data still improves the performance on the same LRS3 test set, indicating that our model keeps scaling. But at the same time, we don't compromise. So on grid, we still achieve state-of-the-art performance, meaning that we can be good on both smaller data sets and very big data sets by scaling our model accordingly. So I wanted to show a quick demo of our performance on, on grid. If it doesn't work, we can try another link.
Maybe.
Oh, is that it? Yeah. Okay, it looks like.
Bin red at R0 now. Bin red at R0 now. Bin red at R0 now. Bin red at R0 now.
Bin red with K9, please.
Oh, yeah. Yeah. On the normal slides, I think it must be. Oh.
R0 now. At R0 now. Bin red at R0 now. Bin red at R0 now. Bin red at R0 now.
Bin red with K9, please. Bin red with K9, please. Bin red with K9, please. Bin red with K9, please.
Lay white at J1 again. Lay white at J1 again. Lay white in J1 again. Lay white at J1 again.
Place green by U5 now. Place green by U5 now. Place green by U5 now. Place green by U5 now.
Is that okay? Okay, so hopefully you could hear those samples. There were some audio-visual synchronization issues that had to do with the technical setup, not in the original video. So actually, you can check those samples on our website, and we got a lot more samples where those came from. Hopefully, you can tell that in our model, the amount of artifacts and is reduced, and the clarity of the audio is clearly improved. And our full paper, which was actually recently accepted to InterSpeech, is also available on arXiv now. And yeah, thank you a lot. Thanks a lot for watching my presentation.
Thanks so much. No, I think it was pretty clear. Like the last one sounded pretty good, but yeah, sorry about that.
No worries.
Okay, so the next paper that is quantifying predictive uncertainty for stochastic video synthesis from audio. Yeah, go for it.
Hello, everyone. Hello, everyone. I'm Anup Chiren. I'm a researcher at Merle, and today I'm going to talk about quantifying predictive uncertainty for stochastic video synthesis from audio. This is joint work with my intern, Moitreya Chatterjee, and Professor Raj Puja. So in this talk, I'm going to present this problem of audio-visual imagination, where it's an in the wild setting of video generation from audio. So to set the context, we assume that there is a set of initial frames that you have seen, and there is the whole sequence of the whole video, the audio of the video available to you. And the problem is to synthesize in the wild setting the missing frames from the video by listening to the audio and some initial frames to set the context. It's an extremely challenging problem because there is no restriction on the setting that we assume. But in the experiments, there is a limited setting because it's a very hard problem to solve. But in general, we don't assume any restrictions with this with the approach that we're going to present. And this is a problem which has a lot of potential if it is solved properly. For example, in occlusion reasoning, you can hear some sounds from somewhere, and you want to make some decision on whether there is some catastrophe happening somewhere that you have to attend to immediately. So you have to imagine in your head what is happening by just listening to the sound and the context. And that's the kind of thing that we are trying to address. We base our framework on our earlier work, which was published in ECCP, which is called Sound to Sight, and where we propose these data sets for evaluating this task, and as well as proposed a model, a variational autoencoder sort of model, which learns a prior, from which you sample a latent variable, which is then used in a prediction network to synthesize a future frame from a past scene frame. And the key thing is that that predicted frame is matched against a ground truth frame using a mean squared error to train the whole model. And now we started asking ourselves, is a mean squared error the right kind of a model to train this network? If you assume that there is a lot of diversity in your generation process. So here we show two examples. So there is a ground truth, which is in the first row, and then there is a possibility 1 of synthesis and a possibility 2. And both of these are plausible given the context of the synthesis. But if you use mean squared error for training the model, then possibility 1 will have a low loss and then low gradient. Whereas possibility 2, which is also plausible, but it will have a high gradient. If you don't have too much data to train the model, then the possibility 2 can actually destabilize the training process, and the model trained would not be generalizable because it forces the loss. The loss forces the learned model to always predict things that are in the training set. So that affects generalizability. So we started thinking what exactly could be a solution to this, and one option is to actually scale the MSE loss by a factor which is corresponding to the diversity of the model. And what if you actually have a mechanism to predict the diversity by looking at those initial frames? And so that's the approach. And the idea is to produce a weight on the predictive on the MSE loss. So the contributions of this work are like a predictive uncertainty quantifier, which estimates the predictive uncertainty of the stochastic video synthesis model from audio. And PUQ, which is the predictive uncertainty quantifier, is derived using a hierarchical variation patient setup. Model, we show experiments on the two data sets that we use in Sound to Sight and show good results. Essentially, we built on the Sound to Sight model, and you have the prior and the posterior variation autoencoder, where the prior is also learned alongside the model. And the key contribution is this top block called variance encoder decoder, which takes as input the variances predicted by the prior and the posterior, that is those sigmas over there, and produces an empty variable. Empty is a scalar that is going to scale the MSE for the predictive process. And looking inside this yellow block, we have another autoencoder that takes these variances and does an encoding decoding process. And so the encoder takes the covariances and produces a set of variables which are then used in a decoder and produces this MT, which is the scaling. Mathematically, it looks like this. It's a complicated thing, but let's decompose it. So the idea is to produce this MT variable, which is a scaling which works on the xt hat minus xt, which is the MSE loss, and MT is derived from a variational encoder that takes in a latent vector and produces MT. And this latent vector comes from the prior, the learned prior. And so the idea is essentially to learn to predict the uncertainty in the model and then use it to scale MSE. And the remaining parts of this math is similar to previous works, where you have the A1 to T, which is audio, and then the predicted video frames, and which produces a latent variable, and then that latent variable is then used to generate the future frames. And we experimented with two data sets. M3SO is a synthetic data set where a digit moves around, and then at some point in this moving around process, there is a block introduced somewhere which is unknown to the method. And idea is that when the digit hits the block, it produces a different sound. And the problem is to synthesize where the block was introduced by just listening to the sound, and also reconstruct the trajectory of the moving digit. And then the YouTube painting is just to listen to the audio and then generate the future frames. I can't hear anything, but okay. I know. What about that? Okay, maybe there's a glitch. Yeah, okay, it's fine. Yeah. Okay, that's okay. All right, that's fine. Yeah, okay, that's okay. Yeah, some glitch. It's okay. The videos will be online, so it should be fine. So the idea is to actually predict the audio, the video from the audio, and we compare against two other methods, one sound to sight, which is S2S, and that doesn't have any variance prediction on it, and G and F is without any audio, and PUQ is the method that we propose. And we can see that the other methods kind of saturate without the regularization from the audio and the variance. And we did some quantitative analysis as well, and we see that even with low data settings for training, this method converges faster than previous methods. This is the accuracy on the test set, and even on the other data set converges very fast and gives better results. That's pretty much it, and the data and the code are available, and if you have any questions, thanks so much.
Okay, we'll do one more paper and then we'll do a Q&A for so the next one is also going to be a presentation. Paper title is Exploring Probabilistic Approach to Vehicle Sound Source Localization in Urban Scenes, and the presenter is Julia Wilkins.
Hi, my name is Julia Wilkins, and today I'm going to be presenting Exploring a Probabilistic Approach to Vehicle Sound Source Localization in Urban Scenes. This work is a collaboration between New York University's Music and Audio Research Lab and Bosch Research. Automatic audiovisual scene understanding is a challenging problem space that explores questions such as how can we intelligently use audio and/or visual data to train a system to interpret videos in the complex ways that humans do. Let's take a quick look at an example. These scenes can get complicated. We have multiple vehicles moving at once and even overlapping vehicles, which can be challenging in the context of sound source localization. Our work here builds upon the recent release of the Urbansis dataset and the proposed baseline method for localization in that work, which uses a binary representation of bounding boxes as the ground truth data, as we see here. When multiple overlapping vehicles are present in a scene, this method loses important information about the density of vehicles at a given position in the scene. Our goal is to estimate the location and density of sounding vehicles in videos of urban scenes, using stereo audio only as input to our model. We focus on predicting a Gaussian representation of bounding boxes of vehicles in the data. So why would a probabilistic representation of bounding boxes be advantageous? One advantage here is that a probabilistic representation allows us to retain information about the scene when multiple overlapping vehicles are present, something that can be lost in both vision methods alone and in methods when bounding boxes are mapped to regions. Additionally, we no longer attempt to map vehicle sound to a box or a quantized region, and explore perhaps a more realistic representation of vehicle sound production. To tackle this problem, we introduced probability density localization, or PDLoc. The input to our system is stereo audio from videos in the Urbansis dataset, which contains over 1,000 videos of urban traffic scenes containing bounding box annotations and corresponding audio. We extract log-mel spectrograms and GCC-FAT features from the audio, and then pass those features to a 3-layer CNN, followed by a single recurrent layer. The model is then trained to predict a Gaussian representation of vehicles in the video over time. As shown in the output image here, we first map bounding boxes to individual Gaussian distributions, using the center horizontal point of each bounding box as the mean of the distribution, and fixing the standard deviation. We sum the Gaussian curves in a given frame, and normalize such that the final distribution is still a true probability density function, as shown in the black curve here. We stack the frames of a video over time, such that the model can predict the frame-by-frame location and density approximation of vehicles in each video. Now I'll show some results and analysis. We chose to compare our method with a traditional signal processing approach, beamforming, as a baseline. In terms of detection, our method outperforms beamforming across the board. This is likely because our model is trained to discriminate traffic sounds from non-traffic sounds, while beamforming does not have any prior knowledge of types of sound sources. On the task of localization, we also outperform beamforming. These results show promise in that learning-based methods, where the model has access to not only audio information, but also a mapping to an intelligent representation of visual data, offers advantages over traditional signal processing approaches. In the future, we plan to provide additional baseline comparisons to our proposed approach. However, this has proved quite challenging, as there are not prior works that predict a probabilistic representation of sound source position. And because of this, the output of either our method or of a comparative method typically would need to be boiled down in a way that such a comparison is possible. Let's take a quick look at a qualitative example that highlights some successes and challenges in our proposed model. Focusing on the ground truth Gaussian representation in white and our predicted model output shown in blue. We notice that overall, our model is conservative in predicting peak height. Recall that we constrain each distribution to a PDF, so when more vehicles are present, peak height is naturally lower. For example, in frames 3 and 5, we're able to localize a single vehicle very accurately, but struggle when predicting a taller single peak. In frames 2, 6, and 7, when 2 vehicles are present at the same time and slightly overlapping, we lose some fine-grained localization but capture peak height with more success. We believe the challenge in accurately predicting peak height is due to a high presence of frames without vehicles in our training data. We also constrain these distributions to a true PDF, resulting in a uniform distribution and likely influencing model output, especially in moments of uncertainty. Overall, we've shown here that training a model to predict a probabilistic representation of bounding boxes can produce intriguing results in both sound source localization and in density approximation. This work also highlighted difficulties of working with a small dataset, which only amplified our challenges with the high presence of empty frames in the data. In the future, we hope to apply the proposed method to additional urban scene datasets. Additionally, as future work, we would like to explore a multitask modeling setup, splitting detection and localization to address the bias towards empty frames, or perhaps experimenting with a fully parametric approach. Lastly, we plan to work on further interpreting our model output such that it could be used for something like car counting in the future. Thank you.
So let's do a quick Q&A session for the last 4 papers. So are there any questions?
So I have a question about the speech synthesis. I was wondering, I've seen the results box there, how it works, and which is logical. So I was wondering that it's about expressiveness of the network to model any speaker or maybe it's learning the speaker with voices, or if it's more about the quality of the data set, which is way more than
So the next paper is also a video presentation. Oh, sorry. So the next paper is called Semi-Supervised Exploration via Multisensory Input.
Efficient exploration is a long-standing problem in reinforcement learning, especially when extrinsic rewards are used or missing. A popular solution to this issue is to feed an agent with novelty signals. Efficient exploration.
Oh, I did. Here I did. Oh, is that not working?
Who is speaking?
The speaker, that one. But what's not working? Wait,
It's a
yours isn't.
long-standing
It's not
problem
sharing.
in reinforcement learning, especially when extrinsic rewards are usually sparse or
I switched the computers.
No, but like.
Oh, so people can, okay, if people can hear our voices, can they hear? Wait, so this is what you're doing.
missing. Intuitively, each multisensory agent in the world should acquire multiple sensory information at the same time. Under the reinforcement learning framework, the agents should find some relation between multisensory inputs in the same time step.
Can you open your sound settings? It could be from you. Maybe headphones. Wait, is it connected to that? Here's the other one. What was it?
To maximize a new novelty signal, multisensory incongruity, and learning, especially when extreme.
So what is this?
Was it? Oh yeah, can you go to the website? And
Yeah, that's what I'm supposed. It's the issue with the video.
Okay, yeah, so maybe it's just the video.
Let's just go with the.
Yeah, let's skip that video then for now. So let's email them. Great, so everyone can hear, did everyone hear that sound over Zoom? Yeah.
Yes, we can.
Okay, sorry about that. Let's just go to the next paper. Like for the paper with sound stereo or the visual navigation. Is there visibility?
Is this supposed to come through the microphone? Sorry. Is this supposed to be?
Maybe not. Okay.
There it is.
Well, let's go to the next one.
It's that little speaker up there.
Is that okay? Should I say? That wasn't working. I tried.
Yeah, just they should be able to hear through the yeah, it's
And,
picking up stuff right now.
Next paper, that is Eclipse.
Good.
I'll ask you later. Thank you.
Okay, we can hear the video. All right, just make sure. All right. Good. Good.
Hi, my name is Xianbo Ling, and today I would like to present our work Eclipse diffusion in long-range video retrieval using planar sound. And this is a joint work with JLA, Monkey-Bento, and Get the types. So what makes the long-range video retrieval so important? So as you imagine, human action usually so complex, and the video spending several minutes. So for example, assume you want to know how to make a French toast for breakfast. The video is quite very long, so that is hard to understand such long content in the video. So also you may search such content. So like preferring French toast in YouTube, you can see a lot of the videos resource. So that is very important to understand the information in the long range video. So in this case, given a video, given a text description, we want the model to retrieve the corresponding video. So for the prior work, they almost works on the short range video is like maybe 1 to 10 seconds in duration. So almost imagine that because the video are usually very expensive to process. So that is because as you can see here, there are a lot of the redundant contents between turn and turn. So as you can see here, the image contents are pretty similar. So if you want to process all this information, it's very expensive to process. So that is the output benefit behind it. We want to use audio signal to contain this control video dynamics, and also audio is much more efficient to process this information. So in this case, as you can see here, the conventional long range video, you have to like sample a lot of video. But if you plus audio, you can just sample fewer video frames plus audio signal that can capture the temporal information. So our method is adapt from the recent clip model, and we adapt the clip model into an audio video one to process the long range video test. And in our model, we have the 3 kind of main components. It's the text, video, and audio encoder. And the text encoder encodes the textured global information of it. And for the audio and video encoder, is take the video input and the audio input here. So we can compute the comparative loss between audio video representation and the text representation. And in our extreme model, we propose the A to B module and B to A module. So for the A to B module, here we use the audio information to support the video information. And then for the video to B to A module, we use the video information to refine the audio information. So we evaluate our approach on the activity capture dataset, and the dataset has the long range video is about like 3 minutes, and also it has the corresponding text description. So we evaluate our method in the standard text to video metric and the video to text metric. So as you can see here, our method is recently sales method clip. And we only use half the video number of video. And also we verify our method on several different data sets here. The first is the QB highlight, and the video range is quite long, it's like 8 minutes, and for the demos and YouTube 2 and Array. And also in the inference time, we have a lower G-flop compared to clip models here. So that is a quantitative resource here. So in the text input here, they're described by the person playing piano near the window. So our model, because our model takes the audio as input, so we can merely recognize the probably someone playing violin. But for the baseline, because it's a vision only model, so we can only like capture the contents of Windows, but it cannot capture the sound, so it gives the wrong result here. So that is conclusion here. So our model can leverage audio as a complementary information that can reduce the redundancy of the video. And also our method can generalize on several diverse long-range video benchmarks. And there is more detail for our website. You can find more detail on our project page. Thank you.
Thanks so much. Okay, and let's move to the last paper of this session. Okay, so the next cycle is all the visual audio localization in simple videos. President is Pravon.
Good morning, everyone. I am Pravon, and today I'm very glad to present our work on audio-visual optimization in Infocentric videos. So this work is collaborated with Yahoo and Rag and Tree. So let me first introduce the task here. Okay. Yeah. So our task here is to localize the sound object in the Egocentric video by given a video and synchronized audio string. And you can find that in this example, the sound object is the frying pan. However, compared to the audio visual localization in server-side video, it would be more difficult to localize sound objects in Egocentric one since we may encounter some real problems. So first, the viewpoint is usually based in server-side video. Should I play the movie?
You might have to hit enable content.
Yeah, in the Egocentric one, the viewpoints are usually changed as the web. So with the wearable device, I usually go around in the thing, and that will cause a lot of ego movements there, which may damage the learning of audio localizations. And also, due to the frequent viewpoint change and the limited field of view, some of the people sometimes may shift their attention from one sound object to another, which creates the out of view audio noise here. For example, okay, yeah, so as the people shift their attention from one topic job to another, the frying will sound and the audio noise to be example. So to effectively learn audio visual localization model, we need to address these two problems. One is the ego motion, and another one is the audio noise. To achieve this goal, we propose a number of framework here. First, we extract key frames from an original audio from the video one, and to create a noisy audio input, we sample another audio from a random video two to compose the audio input. And then we fit them into the video backbone and the audio backbone network to share the features. And since we want to disentangle the audio noise, so we have this audio branch, which we take the visual feature and the audio feature as input. And by taking the mask prediction as a process, we can enforce the network to learn to disentangle the visually related or audio representations. And we then fit the disentangled representation back to the video branch, and we apply a soft localization to highlight some regions here. Then we fit the features into our geometry aware temporal modeling modules to tackle the viewpoint change here. Finally, we have a localization loss to guide the learning, and also we obtain the final localization result here. And here are two steps in our geometry aware control modeling. The first one is that despite the emotions in the user-centered videos, we can still leverage the rich geometry information from the friends. And for example, we can estimate the homographic transformation between these two adjacent friends, and then we apply the homographic transformation and the feature space, and we can perform the alignments here. And then after the feature align, we can just aggregate them temporarily to get a final visual representation. So more details are shown here. Our localization objective is contrastive law, which we use the synchronized audio visual content as the positive signal and the asynchronized one as the negative signal. Yeah, we train our network on the two data sets. One is the epic features and another one is the Eagle 40. So we show some video demos here. Find that our methods can localize the sound object with the motion, and also our method can try to enclose multiple sound objects at the same time. And to quantitatively evaluate our methods, we adopt three metrics. One is the S4, and another one is the CIOU, and also the AUC with the threshold of 0.3, and compare with other state of our localization method, and you can find that our method achieves the result up here. And also our ablation shows that each of our components contribute to the final localization performance. Yeah, and here's another visual comparison with other methods. And also our method can surpass the others in the qualitatively. And thank you. That's all for my presentation today.
Maybe we can take one question.
Yes, so let's simultaneously do the Q&A session simultaneously with a break. So if you want to ask questions for the previous speakers, tell us the microphone, ask them. If not, we'll take a 5-minute break.
Okay, let's thank the speaker again.
So when those are posters, they're probably stable location, so it might be slightly different what I've seen. It's updated on the website. It's in the D&E section, and then the certain number is there. Go to the site now. So you can present your poster at any time during the break, especially the lunch break. There's no designated poster at the time. The regular is an hour-long operating later in the afternoon. That would also give you time. We'll let you know when comes Yes, please do. Thank you also.
You want to talk and maybe they can still hear you? Maybe you have to talk into the microphone. Sorry, you might, I didn't see it. Maybe you could just speak into the microphone and we can see if they can hear you. Were you able to hear that, Hong?
Yes, I can hear you, but do you have any other audio now being played?
No, we're not playing audio, we're just speaking. But you can hear it.
Are you able to hear us all?
I can hear you.
Okay, good.
But do you want to play some audio files or?
I'll play something now. Can you hear it?
This is a Globig plant. It's a small one.
Yeah.
Yeah.
Good. It works.
This is a Globig plant. It's a small one.
There's one that's connected.
And what are we trying to do? We're trying to get the output of.
This is a Globig plant. It's a small. One. This is a Globig plant. It's a small one. This is a glow big plant.
What is this? Okay. This. Yeah. Come on.
Plant. It's a small one.
Yeah, I know, I'm just trying to.
This is a glow big plant. It's a small one.
So we're gonna keep switching computers instead of.
This is a glow big plant. It's a small one.
Yeah. Oh, yes. Yeah.
It's these little boxes, man, they've been giving us problems all day and it's causing a bunch of other little problems.
5 years is not the first.
No.
But I think we probably need to.
Go on.
start to,
Copy you.
As long as. I think it's okay if we don't get people moving over this space for now. But if we're able to at least get them to hear what she has to say.
Okay.
In the meantime, I'll introduce our speaker. Very excited to have Arshia Nagrani speaking today. Ever since her PhD at Oxford, Arshia has been a real leader in the audiovisual area. She was responsible for perhaps the most widely used speech data set, VoxLab and VoxLab2, as well as a whole bunch of other work in audiovisual speech understanding, cross-modal biometrics, and so on. And since graduating, Arshia has done a lot of really interesting work on multimodal fusion, work on transformers, and among her other accomplishments is dealing with some of the tech issues this morning in the earlier session. So very excited to hear what you have to say.
Great. Thank you so much, Andrew, for the kind introduction. Thank you. Yeah, thanks. So I love these Sight and Sound workshops. Andrew's been doing a fantastic job of organizing them. It's great to see how the field has grown. And I'll just be speaking about some of the recent work that we've done in this space. Just a brief intro. So I've been lucky to live in many different countries. I grew up in Hong Kong, Singapore. I then studied in the UK, did my PhD at Oxford, and now I'm at Google Research. So just an overview of what this talk will be. First, I guess we all know what multimodal learning is, but why do we really need it? So just
from both the human and the machine perspective. And then I'll dive into some recent work that we've done at Google and also collaborations with many other people. So what is multimodal learning? I think everybody in this room knows that. Learning with more than one data type. So we can now we have text, we have images, we have videos, we have sound and speech. And why do we really need to use all these different modalities? So if we begin, we can look at a really useful prototype that we have, which is us, humans. We perceive the world with so many different sensory streams. We interact with the world through vision, sound, touch, smell. And one of the major reasons is for degeneracy or redundancy. And that's so that if one of our systems isn't working, then we can still function, we can still move around in the world. And there are a lot of studies that show this, particularly in the visually impaired, where even though they can't see the world, they develop a sense of space and you know, the world around them using touch. So that's one good reason. But another great reason is also that these different sensory systems can actually educate each other. And there's a lot of studies that show that this could actually help humans learn or babies learn, not just by looking at things, but also picking objects up, touching them in their hands, feeling them. And a really great study on this actually is a study on transparency. So as we know, transparency is a really difficult kind of concept to learn. We know this because, you know, birds keep flying straight into windows and so on. So there was this really great study where they had 8-month-old infants. They gave them these transparent boxes, and then they put these like objects inside the boxes, and they asked the infants to retrieve the objects. The infants who weren't allowed to play with the boxes were just not able to retrieve the balls because they kept putting their hands in through the actual glass. Whereas infants who could actually play around with the objects before, they realized that, okay, these 3 sides are transparent, but they're physical, and one side is open, and then they would put their hand in and take out the ball. So this really shows us that the way we touch and the way we feel actually also changes the way we see and perceive the world. And a final reason why we as humans perceive the world with so many senses is also because this fusion actually helps us with robustness. So if we can use multiple signals to come to one conclusion, then we can just end up with a better, you know, hypothesis at the end. So that's, I mean, from a human perspective, there's lots of studies in this area, that's very interesting. But now if we move to a machine learning perspective, a lot of the rationale is actually the same. So we want robustness. We know that the content around us is becoming multimodal. Videos online have captions, they have titles, they have descriptions. Why should we only limit ourselves to one modality? The second reason is just like humans, we can also do self-supervision. And so we can actually use the redundancy between different modalities to help us learn using fewer labels. And then finally, some applications in machine learning are just inherently multimodal. So for example, video captioning, we're going from video to generate text. Automatic speech recognition, we're also again going from generating text, but in this case, of sound and audio. And so if we have these applications that are fundamentally multimodal, we need better architectures that can learn to process input and output different modalities. So I like to kind of divide the space into two areas. So one area is cross-modal supervision, where we basically use one modality to help us learn in another modality. And there's lots of works on cross-modal supervision, self-supervision using multiple modalities. And this helps us because labeling data manually is tough. And in this case, we're actually using what is redundant between different modalities. And the second kind of idea, the second space of works in this area are actually multimodal fusion works, where we actually combine different modalities for robustness. And in this case, we exploit what's complementary between the modalities, or you know, what you can get from one that you can't get from another. So I'm just going to dive into some recent works that we've had, both at Google and also collaborations. I'll be focusing mostly on audiovisual fusion. So first diving into some architectures, then how we can actually get data to train these models, and then finally a new application that we have for ASR. So yeah, so the first work is actually some work that we had at UNEPS last year. And so as you know, video is inherently multimodal. We want to find a good way to combine all these different use different modalities, but we want a single model that's robust, that's efficient and scalable, and also that can take in variable and inputs. But if we look at these areas, different communities have tended to function differently. So you have the computer vision community that's had a lot of great architectures for video and images. You then have the audio community, and you have the NLP community. And what's actually been happening is that you then get these specialized architectures, we have different data sets, we have different benchmarks. And so the dominant paradigm for fusion for a long time is actually late fusion, which is where you have these different state-of-the-art models for each modality. You extract the representations, and then you just combine the scores or the representations right at the end. And this is actually in contrast to how these humans perceive the world. There's a lot of work that actually shows that humans have a very early fusion process going on. And so that's kind of what we want to explore. And so when you were looking around for architectures, I think everybody knows now that there's this big transformer wave. Some of the good things about transformers is that they break commanding context. Unlike RNNs or LSTM sequences, they can actually have access to all other tokens in the sequence. The other great thing about transformers is they seem to be now being toyed as a generic architecture because they can operate on any input that can be tokenized, and we know that all inputs can be tokenized. People actually think that like universal perceptual models, the attention mechanism of transformers are also extremely parallelizable, and they're actually shown to conform excellently at scale. So we ran a look at transformers, and we've seen that they're now actually putting the state of the art on many different modalities. So not only text, but also images, videos, and also audio with the recent audio spectrogram transformer. So to begin with, we just take a simple transformer. This is the simplest idea, where we take in all the modalities we have. So say we have RGB frames and spectrogram. We basically tokenize these frames and spectrogram patches. We get one long sequence of tokens, both RGB tokens and spectrogram tokens, and then we just feed them to a vanilla transformer. So we're doing nothing over here. It's just one transformer, and we have a full pairwise self-attention between all the tokens. And this is very simple. It's a nice idea, but unfortunately, we know that the self-attention mechanism scales quadratically with consent, and this seems a bit unnecessary, given that we know video has so much redundancy. So what we do is we actually introduce a very small number of bottleneck tokens. In this case, we have thousands of video and audio tokens and only 4 bottleneck tokens, so this is really a small bottleneck. We then allow full pairwise attention within a modality, but all cross-modal connections are limited to be via these bottleneck tokens. So really, we reduce the complexity of the model of fusion monetization. The other kind of innovation that we make is we also realize that we don't actually need bottlenecks at every single layer of our model. We actually introduce them only midway, and we call this the fusion layer. And we find that this actually allows earlier layers to specialize in unimodal patterns, and then we can introduce the cross-modal interactions after a fusion layer. So what we find is that wave fusion actually outperforms early and late fusion on most data sets. And in this case, we're testing on action recognition and sound classification data sets. And the other thing we find is that our original motivations of the bottlenecks is that we actually just wanted to reduce computational cost. But what we found, which is kind of surprising, is that using the bottlenecks actually improves performance at all the layers. So you can see on the left, the red graph is with bottlenecks at different fusion layers, and the blue graph is without bottlenecks. And we test our model on 2 types of tasks, so action recognition data sets like kinetics, applications, moment in time, and also sound event classification data sets like audio stack, BTB sound, kinetic sound. And there's more details in the paper, but I'll cheat to the comment. I'm going to skip this slide. And then, so one thing that I kind of like about this framework is that it's very general. It can be used for any modality that can be tokenized. We've tested with optical flow, which is we tested with text. And these bottlenecks are kind of just like global tokens that can be used to, form correlations between any input modality. And then we kind of wanted to see what was going on, so we visualized. So we backpopped We used attention rollout to basically see the effect of the CLS focus right down to the images. And we found that with MBTE, our model is actually focusing on more narrow regions in the images. So for example, you can see with the baby crying, the model is focusing more on the mouth, with the piano, it's focusing more on the fingertips. And this kind of confirms the intuition that these bottlenecks make the model share only what it really needs to share and what's necessary between the different modalities. So, yeah, so the model is available online. We released the code and the models, and yeah, you can take a look. Are there any questions just before I go on to the next part of the talk? Or we can say, yeah.
I have one question. How can your method apply to those three transformers?
For example, what?
Three transformers.
Yeah, so that's a great question. And the thing I like is that the idea of the bottlenecks can really be applied to any other architecture. It's very flexible. So it's just they're just like CLS tokens that we append at the start of the sequence. So yeah, they can be applied in conjunction with these other efficient architectures as well.
You mentioned that late stage fusion outperforms early stage and late stage fusion. Do you have any intuition why that is?
Yeah, that's a good question. So the fusion layer is kind of like the hyperparameter. We found that, you know, on some data sets, the best fusion layer is like 8 or 7 or 6. We did find that it was better than late fusion in all cases, and that's because I think it just gives the model more flexibility and that it can have these interactions earlier on. Why it outperforms early fusion is not clear to us. I mean, it's clear that the complexity is less, but why it should do better is something that, you know, it's like early fusion, whatever it's doing at early fusion, whatever it's doing at mid, it can do it early, right? It can like ignore the first use. So it's a good question, but I think it's just like something to do with the regularization of the network.
Thank you.
Wait, Andrew, do you want me to stop at 25 or go on?
I think the goal is fine. So I think you can go and
Okay, I'll keep going with the rest of them and then I'll come back to the questions. Sorry. Yeah, so this is another kind of work that we've been doing at Google that's still in progress. And over here we were like, so we can have these great architectures, but we really struggle to find good audio-visual data to train our models. And we don't really want labels anymore. We don't want application labels. We want natural language descriptions. And this is because captions are way more flexible. They can be as detailed as code to be live. They're great for so many more applications like video captioning, video retrieval, touch answering. And also from an AI perspective, language is the way to communicate. Videos are how we perceive the world. So if we can, you know, bridge this gap, then that's also really nice. So we really want some good audio-visual data that's with captions. But if you look at existing data sets, for video text data sets, we have manually labeled ones that are not very big. Floating moments in time is a very recent introduction, but other than that, they're all very small. We have then semi-automatic ones like how to use millions, web figure text, hashtags, but these are very noisy. And then if you look at audio and text, it's even fewer data sets. The manually labeled ones are only things like audio caps and Propo, and on the other hand, image captioning data sets, such as conceptual captions, are really big. You know, we have millions. And this is because we can really scrape the internet and we can get loads of images with text division and really good localized text. So our goal here was to see whether we could actually use these image captions in a way to get free supervision for audio and video modalities. And so what we did was we started with a seed image captioning data set. We then took the frames in this image captioning data set. We went to a big corpus of videos online, which Google has access to and we can get. And we basically tried to find frames that matched with these seed images in the captioning data sets. We then took video clips that matched these frames and we transferred the captions from the image captioning data set to these video clips. So for example, we have an image captioning seed image from this data set, like a pop artist performs at a festival. We then take this image, we look for clips that look similar. you take the audio and you take the video clip and you reuse the same caption. So we've done this with a number of data sets, but just as an example, we start with the conceptual captions streaming data set, and we go and get the so the first data set we create is this video CC 3 million. So it consists of video clips from YouTube that are matched to captions from the conceptual captions data set. And we actually compared this data set to how 200 million, because that was the other video data set we had at the time. And we find that it's actually a more diverse data set, it's more multimodal. We've filtered it for some lens pipelines, and we also found that unlike how 200 million, which is just focused on instructional videos, our video data set consists of various different domains. And the other thing is that we also have multiple captions per clip and multiple clips per caption, which is unlike my education data sets that have a one-to-one mapping. So you can see some examples over here from my data set. On the left, you have the single image from conceptual captions streaming data set. On the right, you can see some mined videos. The last two columns are actually 2 frames from one video, so you can see that there's some amount of motion, both active motion and camera motion. And some more examples, the thing I like is that we can also get videos and audios that are like animated and have different styles. And then we also had a look at the level of noise. We've done a lot of cleaning up since then. Obviously, the audio is not as high quality as the video, but even in the video, we do find that there is some amount of noise. Sometimes the model does make mistakes. So you can see at the bottom, the last video clip that's achieved is actually a car wash, but our model thinks that it's broken glass, and that's because it looks very similar to the image of the car in the broken glass. So training on this data set, we actually evaluated on 3 tasks. We evaluated on video retrieval, we evaluated on video captioning, and then we also did audio retrieval. And if you just look at the video captioning, the thing I like about this data set is that we actually get some pretty good zero-shot video captioning results. So most video captioning works till now have had to pre-train on how 200 million, but then always fine-tune on a target data set. But we find that because you already have a huge captioning data set, we can actually get some zero-shot results. We also get some results on audio retrieval, and this is kind of nice because we use no audio supervision. So we start off with image captioning data sets. And I think the reason why this works is that often image captioning data sets are actually hallucinating audio sounds. So in the conceptual captions data set, we found captions like these on the left, like person performed by a blues artist, or man is singing, or man is, these captions are hallucinating audio that's obviously not there. And so if we can find audio from text, then we can use these captions. Okay, I can take some questions now on these last 2 words. Yeah, that's a great question. So you're saying instead of starting with image captioning data set, you start with existing video captioning data set. That's a great idea, but we really wanted to do this at scale. And the image captioning data sets that we have are like millions, whereas existing video captioning data sets are so small. But it's a good idea, definitely. And we want to do something similar with audio as well. Yeah, that's true. Yeah.
Have you tried using just the titles of the YouTube videos?
Yeah, that's a great question. So there is actually a work from Jonathan Stroud, who he created the WBT data set, and I think there's some other papers as well that where they use YouTube titles and YouTube descriptions, and that's those models actually perform really well, but those data sets haven't been released. So yeah, we found that this worked as better than that data set because we wanted localized captions, and the title for the video is for the whole video. 5 minutes. Okay, I'm going to keep going then. So I just wanted to talk about this recent work as well that we had on audiovisual speech recognition, and this is just been on archives yesterday. So our goal here was actually, we wanted to do ASR, so speech recognition, but we want this to work when the audio is really noisy, corrupted, and most previous audiovisual ASR works, they actually focus on lip motion. And this is the strongest key you can get for ASR. However, we want to see if we could do this when this is very far away, when the lips are not very clear, when we have occlusions like face masks, and also for egocentric viewpoints and many structured videos on YouTube where we can't really see the lips. And so we wanted to see if we could actually learn how other objects in the scene, the background, and so on. So we introduced this new model, which is called Avatar. It consists of this end-to-end trainable transformer with early features. We actually use the MPC model that I had described in the first part of the talk. We do early fusion of the audio spectrograms and the RGB frames, and then we just added decoder to generate the text. And what we found is that if we just train this model straight away for ASR, it will just ignore the video stream. The model has no incentive to look at the video because audio is just the strongest tool for ASR. And so we have actually to force the model to look at the video. And the way we do this is by different masking schemes. So we mask out random parts of the audio, we mask out entire words either randomly, or we mask out content words, which are basically non-stop words. And for non-stop words, the model really has to then look at the vision to resolve the task. So we evaluate with both artificial and real noise. For artificial noise, we randomly mask a chunk of the audio signal. Real noise, we added audio signals from the audio set noise category. And we find that across all these cases, vision actually helps, and the masking strategy is still performing. But you know, evaluating with this artificial noise isn't very satisfying. So what we did was we went to YouTube and we actually found videos where the automatic YouTube ASR API fails. So these are samples where audio and ASR doesn't work, and a lot of these are actually different accents. The YouTube ASR API is really good at American accented English and not much else. And so we found that on these cases, actually vision is a great tool. And it improves the performance. I do have some, okay, these are just results, but I do have some videos I want to play, and I'm going to try playing them and we'll see if you can hear them.
This is a Globig plant. It's a small one.
Okay, so the audio model predicts this is the Globig plant, and then the vision model corrects it to this is the Globig plant.
Okay, so the plan is completed.
Yeah, so I'm sorry you can't see that, but the audio, and he said dependent permissive, and it corrects it to the plane. So that's completed.
This is a Globig plant.
Okay, so
It's a small
the plan
one.
is completed.
And then just some more examples.
This deserves, definitely deserves a happy dance.
And I absolutely love this shake.
The thumb reaches for the coin.
So we have lots more examples on our website, and this data set, the VidSpeech data set is also publicly released. So as well as the video data set that was put out in the second half. So go and check it out.
This deserves definitely deserves.
And then I just wanted to briefly touch on some more application fusion that we've been working on. So audio is really useful in the egocentric domain because the microphone is maybe close to the person and may record sounds that are out of the camera. So there's a whole workshop, obviously the Ego 4D workshop and the application workshop, and some great audio visual works there. We also are doing a collaboration with the anthropology department at Oxford, and we actually found that for actual recognition of chimpanzees, audio is also a really great signal, and in this case, these chimpanzees are cracking nuts and they're dropping on trees, and the sound is a really great indicator. And I actually really like working with these data sets because unlike human actions and human faces, we don't have the same privacy issues, and also these works actually help with conservation research. So that's another nice outcome. And then just in general, with training with multimodal data, I feel like some of the biggest challenges are different modalities of learning rates. we have very different input representations. So text is symbolic, sound is usually one waveform, images are usually 2D. We also have very different noise topologies to deal with. And then obviously, the more modalities we combine, the more expensive our models become, and so we need more efficient outputs. Yeah, and that's what I have.
Gonna get set up for you.
Oh, okay. Yeah, definitely.
Thank you so much. It was very interesting talk. And I want to know more about the whole aspect like how we were in
Sorry, I can't do it.
Oh, okay, probably the compliment.
Sorry, you said temporal act.
Yeah.
That microphone is broken.
All right. No worries. Yes, I was curious about hearing more about temporal aspects of different modalities. So you mentioned briefly that the LM lines that with different modalities run at different rates. Yeah. Also, they should offer different timings, and how you control the relationship on both those.
Yeah. Okay. Yeah, so that's a really great question, and also one of the biggest challenges. So, because sound is a 1D waveform, the way we represented it are spectrograms, and you have time on one axis, frequency on the other axis. Obviously, this is different to images where you have multiple images per second, and you have this huge amount of redundancy. So what we found actually that for the MVC work, we found asynchronous sampling actually helps just as a data augmentation technique. But in most other works, I think we found that synchronous sampling is better because you want to align up the audio and the vision. So I think it's a great question. It's definitely an open problem, and I think it depends on how we represent. Yeah. How we represent the input, but definitely something to think about. Yeah. Yeah, I think so. For example, in the egocentric domain, if you have like washing, the difference between like washing something or frying something, you can have the sounds that are really strong with the microphone. You can also have, if the microphone is close to the person and they are making a sound, then that's not going to be captured in the viewpoint, the camera view, because the camera is looking away. So in those cases, sound is useful. And there is actually a challenge. There's actually a challenge in the Eagle 4D where they have, which is I think speaker recognition and speaker diarization, and in those cases, they want you to transcribe the speech of the speaker, but the speaker is like, you can't see the lips, you can't see the face, and that would be the help. So I do think the egocentric domain is so interesting for audio visual applications, basically, and models. Yeah,
Oh, yeah. So, my question is about the audio modeling. So I saw that audio visual model and the audio that big attached.
Yeah.
Like to glance from the audio. So images, the objects, the fact that they actually not objects and that over a single region.
Yeah.
But for the sound and frequency presentation. The audio actuators never have the right length and the repeated person. So if you use a small patch, the product will cover like a red zone.
Yeah.
So the audio plan, like audio
Yeah, so that's a great question. So I think when image CNNs were so good, the audio field took spectrograms and then just wanted to reuse these great image models and then just use spectrograms as images. And you're right that spectrograms are not like images, right? Spectrograms in sound, when we add noise, it's always additive. In vision, you have an occlusion, the pixels behind are lost. Objects in images are, they're opaque pixels. In sound, you can have multiple objects in the same location because they're transparent. So there's definitely different statistical properties between spectrograms and images, and that's why I think I actually like the MVC work, because we basically have a tension between every single patch in the transformer, right? So even though we have one patch, it can attend to all the other patches. We can also try different sizes of patches, which we did do, and it did make much of a difference. But I think that's a very valid point that we shouldn't treat spectrograms and images the same. So yeah. Sorry, I think.
Yeah, so I really see what you mentioned, where even by using like image data sets and captions, there were some descriptions that were hallucinating audio, and you mentioned that you were able to kind of find those audio kind of events because of that. I was wondering if you explored that, and what are the limits of that? What kind of sounds people might describe, and what other kind of sounds are never in there?
Yeah, that's a great question. So a lot of it was music and singing. There was like babies crying and that kind of stuff. But I do think that the biggest challenge is actually with the distribution of YouTube videos, and that for this to work, we need the sound to be correlated with the visual frames of the video. And then on YouTube, people edit their videos a lot. You have irrelevant music, irrelevant like voiceover, and that actually was the biggest challenge with this. So we're in the process of cleaning that up.
Great. So let's make the speaker again. And I'm very excited to have our next speaker here, Jeanette Vogue. Jeanette is an assistant professor at Stanford, where she works on robotics. And prior to that, she was a group leader at MPI. And prior to that, she got her PhD from KTH. And Jeanette's work deals with, in part deals with multimodal perception in robots, where she's done some really interesting and creative work that really spans the whole spectrum, from both work on the sensor level to learning algorithms that robots use multiple modalities. So I'm excited to hear what you have to say, Jeanette.
Thank you. Thank you so much for the invitation.
Sorry,
Ooh, I can hear myself. Sorry.
I don't know. Can you try again? Or just
1, 2, 1, 2. How's that?
Oh no, okay, no, we can't hear you now. Okay, sorry. I don't know. I don't know. We can unplug the mic. Do you want that? I mean, I know. No? Can you, oh, do you see this? Can you try presenting it to that? I'm so sorry, there's just some feedback on our end.
Oh, I don't know. Do you want me to test?
No, it's working. Yeah, great.
Awesome. Thank you so much. First of all, thank you for inviting me, and then thank you for dealing with this audio setup in this hybrid workshop. I've been to my first conference at ICRA in Philadelphia, and it was a joy to organize a hybrid workshop. So I can't really see the audience, but I hope this what I'm going to talk about is interesting to you. Yeah, so my research is driven by the question of why people are so incredible at manipulation, and at the same time why it's so hard to make robots do the same and show the kind of dexterity that people shown, the robustness when executing and learning these manipulation skills. And as you are, as the first speaker already said, right, like people really make a lot of use of all the modalities that we have access to. So just think about this game, Jenga. If you've played it before, you know you don't only need vision and physical intuition, but you also need a sense of touch to actually figure out which block to remove next. And so there are a lot of scientific studies on how people actually exploit multiple modalities for perception that are more rigorous than playing Jenga. And so here's a very old study from J.J. Gibson, who, yes, the affordance guy, and he presented the study in his books, The Senses Considered as a Perceptual System. And here subjects were supposed to find a reference object among the set of irregularly shaped objects. And these subjects were most successful if they could actually touch and rotate the objects instead of just passively looking at them or visually rotating them. And really, this is some evidence that humans exploit multimodality that is only available through physical interaction. And maybe some other evidence, there are also people exploit signals over time. So here you see like a black and white image, and only if you actually consider the signal over time horizon, you actually can figure out what is going on. In this case, it's a bunch of dogs. And there's more experiments like this, very old one from 1963 from Held and Hein, where they present evidence that in biological systems, it's really important to understand the concurrency between your own motion and the sensing to develop meaningful behavior. And maybe in the interest of time, I'm not going to actually explain this. The point is that the kitten that actually is in this contraption and has control over its own motion and sees how the visual input changes in response to its own motion can actually develop visually guided behavior, while the other one that is just being kind of floated around in the space without control cannot, or is worse at it. So feel free to read this paper. It's very interesting, actually. But my main point is basically that people have this ability to exploit multiple modalities, and often they use their own body to get this kind of signal, either vision, but most importantly, touch and sound as well, or even smell, as the previous speaker mentioned as well. And robots can't do this, but they do have all these sensors in their body. We just don't have a good sense yet on how to exploit them really super well. And so I personally have done a lot of work on actually exploiting the sense of touch. So tactile sensing, voice talk sensing, and sensing of the joints. But there's more and more work on actually exploiting sound as well in robotic manipulation. And here are just some examples from the literature to give you an idea of what's going on in the robotics field. So this is a bit older work from Sinapov et al. From ICRA 2009, where they tried to basically interact with different objects, collect data in all the different senses that a robot has access to, and then understand what the properties of these different household objects are. Sound sensing is also used in hardware to actually, for example, in these super interesting new soft hands, and they are used to understand where contact is being made on these soft hands that are otherwise very difficult to sensorize and to sense, actually. There's also even more recent work where the sense of touch is used, the sense of sound is used to actually find specific objects, in this case, a keychain. And sound is also used to understand how a ball is actually bouncing, what material is made of, in order to play with it, even in the blind, when you're blind and you don't have access to vision. So these are all some really cool examples of how sound has been used specifically in robotic manipulation. And today, let's see how far I get, but I wanted to talk about some of our recent work on how we use sound models to identify object materials, specifically from impact sounds. And I also, I hopefully managed to at least mention, is going to talk about and a data set of virtual objects that allow us to do contact localization, shape reconstruction, and grasp stability estimation from these multiple modalities that also include sound. So this is work that is actually, that last one is actually being presented at CVPR this year. And in case I won't get to this one, I know that Rohan Gan, who's the first author of this paper, is in the audience. Maybe you can just quickly wave. And, if people have questions to this and we don't have time at the end of my talk, please feel free to ask him or bombard him with more questions. Cool. So let me first talk about this first work that was presented at Qual this year. So I hope this actually works. I think I shared sound. So let's see if you hear this. So I want to start off by trying to illustrate to you your own mental intuition about impact sounds. And so here I show an adversarial example for inferring materials from vision only. So in fact, only one of the glasses here is plastic, is glass. The other one is plastic, and one of the seemingly steel forks is plastic as well. So now I'm going to play this clip, and if you listen carefully, you'll hopefully be able to classify the materials of these cups. And if you listen especially carefully, you may even be able to classify the materials of the fork. Okay, so listen carefully. I hope this works well. Okay, so I hope you heard this, and probably you were able to understand which one is plastic, which one is glass for both of these objects. Probably the dropping the fork on the table also helped a little bit. So what you just mentally did is called source separation. So when the glasses were each struck with a fork, you never heard the impact sound of the glass by itself, but rather heard the combination of the sound of both the glass and the fork. And yet you were still able to mentally attend to the sound of the glass to classify it. And perhaps you could have even done this if there was a conversation going on in the background or some noise otherwise, okay? So people are really good at this. They have a powerful intuition for mentally reasoning over forward and backward problems relevant to impact sounds. So how can we give this ability to robots? So first off, let's look at prior work. And honestly, all you need to know is that there are two camps, like as always, in, especially in robotics. There's the model-based camp that actually fits physically interpretable parameters. And then there's the deep learning camp that, just fits a lot of data in a non-interpretable way. And that works really well. You can learn from data in the wild, but the parameters are uninterpretable, right? As opposed to these methods where you actually physically understand what these parameters mean. Cool. And then this is a more recent work from 2020 from the Magenta team at Google. They proposed this DDSP model, which is a differentiable audio renderer that is kind of in the middle of these two camps. And it's specifically designed for musical instrument sounds. And they can learn interpretable parameters from data in the wild. So again, these are, though, relevant to music. Okay, so we wanted to also basically combine the best of both worlds, model-based and deep learning-based methods, and propose DiffImpact. And so hopefully using these techniques, we can get interpretable and transferable parameters, yet by being fully differentiable, we can learn from data in the wild with these learning-based methods. Okay, so at this point, you may be wondering, why do we care about physics-based models with interpretable parameters? And so the reason for this is that if we can extract physically interpretable parameters about objects, tools, contexts, environments, and so on, we can actually easily reuse these parameters to extrapolate and simulate new impact sounds using new combinations of parameters of contact conditions, objects, environments, and so on. So this is maybe also going to be useful for any kind of simulation that you want to fine-tune to learn at a larger scale from, right? I'm going to come to this. I'm going to come back to this later with the second work. Okay, so to see how we can extract these physically interpretable parameters from uncontrolled recordings, let's consider the physics of impact vibrations first. And it turns out that an impact sound can be broken down into two main components: the intrinsic contact forces acting on an object, or the impact force profile, and the intrinsic acoustic model of an object, that is its impulse response. And so basically the convolution of these two components is the most fundamental aspect of an impact sound. And other components such as background noise and reverberations of a room and so on are also big contributors. So our model also models these, but I want to focus basically on these 2 points here for the sake of brevity. So we focus on these forces and the impulse response here. So if we can decompose an impact sound into each of these components, we can infer important properties of objects and how they were contacted. And then we could even specifically swap out the impact or the object parameters to simulate a new sound in a new acoustic environment. But the problem is decomposing an impact sound into these constituent contributions is an ill-posed problem, since we're essentially trying to solve deconvolution. And so the key idea behind diff impact is that we can bias the decomposition of impact sounds by using physics-based models to both provide a helpful model bias and extract physically interpretable parameters. So I start by focusing on how we parameterize the impact force profile with a physics-based model. The first thing you should know about impact forces is that they are generally not ideal impulses. They have different sharpnesses to them, depending on the velocity, shapes, hardness of the colliding objects, and so on. So we use a Hertzsche-Hafstein model of contact forces, which can be parameterized with the timing of the contact, the scale of the magnitude, and the time constant tau, which represents the sharpness of the impact. And more specifically, we use a Gaussian approximation of this model, which has the same parameters, but has smooth derivatives, which then allows us to make all of this differentiable. So we model an impact force as a linear combination of m impact events, each parameterized by these 3 parameters, and to create a time sequence of multiple impact events, basically. So next, I'll explain the physical model behind the object impulse response. So rigid object vibrations are well modeled by modal vibration models based on a spring damper model of a network of particles within the object. So as shown here, each object has multiple modes of vibrations occurring simultaneously, with each mode vibrating with a different frequency, initial gain, and damping. So an object's impulse response can be expressed as a sum of exponentially decaying sinusoids. And this is shown here, with all of the different parameters that are already mentioned. And so I've explained the physical models we use for the impact force profiles and the object impulse response, which we convolve together to get an impact sound waveform. So the main thing that's left to explain is the loss we are optimizing against. And so for our loss, we compute the magnitude and log magnitude spectrograms of the original ground truth audio, and then compute the same for the audio synthesized by our model. And then we take the L1 difference between the two. And so now let's see how this all plays out on an example of a studio recording of striking a ceramic mark multiple times. So here's the original recording. And so to model and extract parameters from this real recording, we start by initializing a random series of impact forces and a random impulse response shown here. And these are convolved to get our running estimate of the synthesized waveform. And we take the spectrogram of this and then compute the L1 loss against the ground truth spectrogram to adjust the parameters of the upstream models during the gradient descent optimization. So this is how this looks like. And here we have estimates of the extrinsic impact forces and intrinsic object impulse response, which results then in the following synthesized clip. Sounds pretty good, I would say, in comparison to the ground truth that you heard earlier. And the full model actually has more to it, to look at all of these different things that impact a impact force sound. Let me skip over this though. So we evaluated basically this model in different applications. So first we showed that we can learn from these controlled recordings in the studio, just like existing model-based method. We next show a passive learning use case where DiffImpact can outperform existing deep learning methods to enable a robot to learn acoustic models of objects passively from data in the wild. And finally, we show an interactive learning example where DiffImpact can equip a robot to learn separated acoustic models from impact sound recording collected in a noisy robotics lab. Okay, so here's some examples from the experiments on the controlled recordings. So basically the goal here is to show that DiffImpact can match real impact sounds and that because of its physics-based model bias, it can infer physically meaningful quantities about the impact as well. So this is again like hitting these objects with an impact hammer that records both audio and ground truth impact forces. And then we fit, there's this, and then we fit a modal impulse response for each object and make an estimate of all of this. So here are some examples from the Ceramic Mac, ground truth, and the synthesized waveform. And that sounds pretty good, but what we really want is to show how DiffImpact can enable a robot to passively learn acoustic models from in the wild impact sound data with many imperfect impacts through an end-to-end learning task. So we curated a data set of audio from ASMR videos where the creator is finger tapping different everyday objects and doesn't actually say anything. So it's perfect for the purpose that we have in mind. And then we use DiffImpact as a rendering layer and an autoencoder for impact sounds. Our model and all baselines were given the ground truth magnitude only spectrograms input. Then we're trained to reproduce the sound from the spectrogram using ground truth audio supervision. And we compare our autoencoder based on DiffImpact to other autoencoding baseline frameworks, which were designed for musical instrument or human speech. So here's how this looks like. This is again ground truth. This is the synthesized sound using this model, this baseline that is actually essentially made for musical instruments. We did add some tweaks to it to make it a fair comparison as well, but you can hear it's not exactly great. It sounds very washed out. Waveclo does them better, but it's actually optimized for speech and it needs a lot of data as well. And this was our approach. And we show actually in the paper in Human Studies that people mostly prefer our model. It seems to them that it explains best what's actually happening in the video. And here you have an interesting experiment with a robot that does the same what you have done at the beginning of this talk, namely sound source separation, right? So we want a robot to understand what's the material of the tool and what's the material of the object from actually dinging things against it. So remember, this was the task you did at the very beginning. And now with our model, we can actually separate these sources. So here again is the recording from the actual robotic lab. Which you may have heard, it has quite some noise. For example, the motors of the robot are actually making noise. This is from the microphone directly recorded, then synthesized and denoised. And now you will hear the fork and then the mug. separated. And we can do this for all the other objects as well. So you will actually be able to hear what the material is quite distinct. So for the objects themselves, this separation that the structure of diff-impact allows us to do works pretty well, I would say. It works less well for the tool. And we use this separated sound to actually do classification of materials. And basically, our model in blue is basically performing best, but you do see for that actually for the tool, it works less well. We also looked at Young's modulus, which is like a different kind of parameter that determines sound. Cool, so the key takeaways is diff-impact uses models to extract physically interpretable parameters, which can be used for simulation and extrapolation. It is differentiable, so it can learn from recordings in the wild, and it can solve many dual forward and backward problems with just one framework. And we use these results for important downstream tasks in robotics, such as material classification and stiffness estimation. Cool. So unfortunately, I'm totally out of time right now. I actually have to run. And I can't talk about this work that we did on creating a virtual multimodal data set that we show works actually for applications like contact localization, shape reconstruction, grasp stability estimation from vision, touch, and sound, which is actually going to be presented at CVPR. And again, Rohan is in the audience. If you can, wave again, Rohan. Ask him about all of this. This is basically how the model looks like. It's basically intrinsic object models where we combine nerves, a cool new tactile sensor, and this audio model that you just heard about. Just to conclude, for robots that manipulate objects, the sense of touch, vision, and sound really augment decision-making. And it is still an active area of inquiry, how to fuse these multiple modalities with many open questions. There's always this question whether you prefer interpretable parameters versus actually having a non-interpretable representation of this. And then how can you scale to many different tasks? And with that, I thank you again for the invitation and for the attention. And I thank all my students, funding sources, and of course, all my great collaborators.
Thank you so much for your talk. I think it's well given that Rohan is a collaborator on the thesis, so you're welcome to help him and ask him questions. Thank you again.
Thank you.
So now is the lunch break. If you have, I assume you have to go and you don't have any time for questions. Okay, great.
Yeah, I'm really sorry. I would love to answer some question. I'm gonna hear how Rohan is answering all these questions later. I catch up with him. Thank you again.
But yeah, so now the lunch break. Thank you to all of you. Thank you for bearing with us with all the technical issues. At 1 p.m. we'll be back. And there'll be the second round of if you're one of the second round of if you're one of those presenters, please come 15 minutes early just so we can double check the presentation and make sure everything works. Thank you.
What is the black thing?
Oh, I think that's just.
Oh,
it's like, it's my.
That's okay.
Hey, Hong, can you hear us? Okay. Oh, thank you. Yes, we were having problems right before the lunch break. It'd be great if you could help us out. I think right now, I don't know if the problems are happening.
Did you want to try to the bot?
Oh, yeah, okay. Could somebody over Zoom try saying something? I think we wanted to play sound from here and have it go on that speaker.
Oh, okay, yeah, there's a. This will have to be plugged into that phone for the.
Yeah, that was what it used to be. Yeah.
Okay.
But I don't know.
Do you want to try playing something out of there right now?
Yeah, I'll try.
Yeah, that will be whatever comes out of your laptop, but it won't be associated with coming out of that phone. So.
Wait, so what should I do? Can you play something from there on share? Wait, what if you share from there?
Share what?
Wait, the issue is like the audio coming in through Zoom, right? Can you share the Zoom and say something? So now this is connected.
Oh, that's right. That's right. Oh, so what you mean, like play it on that computer over Zoom?
I mean, wait, that window already has the audio plugged in here. So we want to maybe, well, I can try it on my phone and just go outside.
Oh, wait, actually, don't we want it on this one so that you can hear it through that big?
No, but so this works. But like if somebody's presenting. So what if somebody, what we want was like if somebody's presenting through Zoom, yeah, we want the sound to come here, which we haven't tried.
Yeah, I thought that you'd want to do. Are you doing a screen share?
Okay, so
I think we'll still have a computer. I don't think we should use this other computer for that. Oh, for the posters here? I say at any break or the lunch break, you're welcome to set up your poster and do the presentation. In particular, there'll be an hour-long lunch break or hour-long coffee break later, where there would be a good time to do the posters.
But there's any specific place?
Oh, it's on the website. Okay. Or it should be.
Okay, so on the website I can find.
Yeah, it should be at the top. Let me.
Okay, so.
They changed it, so it's.
Yeah.
Okay. Yeah, let's see.
So just when this will be.
This is where it is. 65 through
Okay.
85.
So during.
Recording in progress.
Yes, yes. You can do it right now, or you can do it.
Want to try it again?
Yeah, let's try
See,
it.
the thing is that if you're playing that too, it's gonna get that.
Yeah, Okay, well,
If you're muted, it should be still okay.
Okay,
Yeah.
it's still working.
Okay, but if somebody wants to play, so if somebody presents again, do we all have other speakers that are presenting?
Yes, yes, we have one.
So for them, we need their audio to come through here.
That's
So
right.
How does this work?
What if you? I mean, this one's already able to play sound through that. What if we play?
Okay, I'll go outside and I'll.
Okay.
Let's see.
Sure, okay. Great. Thank you.
You need the sound from this one as well?
Yes, so sound has to come from, because we have, let's make sure that's.
We'll have to set up another input. We have the XLR.
That was
You gotta run
working earlier. Oh, now
It was working earlier because we had the DI set up to that, but we also need it for this if you need sound from here.
yeah, this is a workshop on sound, so it'd be great if people could play sound.
Okay, yeah, let me get another DI and we'll set that up.
Yeah. Oh, sorry, I'm just muting this.
Hello? Andrew, can you hear that?
Hey,
Wait,
This
so
is
can you hear the sound properly?
we can hear you, but we're gonna test out the speaker setup. So you can keep talking and we'll hear you.
Okay, wait, so you can hear me well through the speakers of the room then?
No, we can't. So we're testing that out though. Can you just, maybe you can keep talking and we'll let you know
Yeah.
when we work.
Yeah, so
Great. Yeah, feel free to do your thing.
yeah,
and,
I can count or something like 1, 2, 3, 4, 5,
yeah,
6,
yeah.
7,
Or I
8,
can let you
10.
know when we do it again.
1, 2, 3,
We'll let you
4,
know.
5, 6, 7, 8, 9, 10.
You can stop. Yeah.
Wait, is it okay now? Andrew? Yeah, let me know when to start talking again.
Daphne, can you talk again?
Yeah, can you guys hear me now? Hello?
Oh wait, I think he should be talking, but we can't hear him.
Yeah, let me know when to try again.
Hey, Daphne, can you talk again?
Hello, guys? Can you hear me? Oh, hey, I want to see. Yeah, we've met. I don't think we've met like on. No, I don't think so. So nice meeting you. Yeah, same. No, thanks for attending the question. No, we always have this technical. Now we type it.
Yeah, I mean, that must be challenging, but Bluetooth tonight.
Hey, Daphne, can you talk again?
Hello, Andrew, can you hear me? Is it okay now?
Okay, we can hear you, but it's not coming.
Oh, you need to select it on here. I'm sorry.
Okay.
So go to your.
Okay, let me know when to try again.
Yeah, that's right.
Okay, wait, can you do it again? Daphne, can you say something?
Hello, guys, can you hear me?
Oh, yes, we can. But
It
there's
works?
one thing for me though. One thing is, can we play sound from this computer successfully
Yes, now we can. Let's try it.
Okay.
And make
I think we're good on your end, Daphne. You can come in. Thanks. You can hear us? Okay. We'll find out. Okay, so now I should play some kind of music here or something. Okay, this is the computer. Oh, good. Yeah, can you play it? Is this sound working? Because I have like clips. Excuse me, the sound still on here still isn't working. Can I turn up the volume here? It's still the one thing that's not working is this.
What was that volume?
Can I turn up the volume here? Or?
Yes, it is. I'm sorry. Turn that on. This should be our volume. Yeah, make sure that your volume on the computer is almost as well.
It's up.
It's up. Okay.
Like that?
Yeah.
Okay, wait. So let's try it again. Oh wait, now we're getting an echo.
Now we're getting feedback. Yeah. So, we need to take.
We need to take the audio from here, right? And the chat.
That one's coming into that, and then Daisy changing out of that.
Everything that was okay. The one issue here is the echo with the
That's echo. Is the person who's talking?
No, I think with echo. Wait, I think it's when I talk.
They're on different. Just so maybe mic on here.
Yeah, it is good.
Andrew has been running this thing for like 5 years. I think like every single time is like issue. And now we have time to do as well. It's just.
It seems now like the one issue is my. Let's see. But this seems to have an echo. I think that's the one issue. Wait, is it still echoing? Is
I'm gonna think this song. It's just an example.
It's only when he's talking through it, right? That it's echoing. Just make sure this is set. I mean, it's set to this, right? I'm pretty sure. Emit. Okay. Okay. Let me try something here.
A good example. It has long enough.
Oh, good. Yes.
What about you? Are you is it the violin? Like making sound.
What time do you guys?
Now.
Right now.
Yeah.
Yeah. I'm gonna.
It was working this morning for a few minutes, but I think this was plugged into that. That was
Yeah, so the problem is I got two different systems going.
We try a variant of the.
Let me try to set up another one.
Thank you. I really appreciate all the help.
We're gonna set up another one.
Another what? These
Oh,
pods?
these pods.
But like the versions were like.
Yeah.
So I'm sorry for the delay, everyone. We're setting up another sound system, so be a little bit of a delay. I'm sorry about that. Wait, it's not.
Can you set it up over here on this computer? And I'm gonna go down real quick and deliver something to them.
Andrew, so there's no feedback on the Zoom at least, and just want to let you know.
I'll meet you back over.
Yeah, sorry. I think there's still echo in the voice. I think. Wait, actually, is it? I don't.
Ask him to talk.
Can you talk in Montreal?
Hey Andrew, how are you? I don't hear feedback on the Zoom at least. It's quite good on the Zoom.
Oh, sorry, we can't hear you. I don't know if it's your end or if it's just. I don't know
Hello. Test. 1, 2, 3. Is it good?
I think it's okay.
Tell him to keep talking.
Hi. Hello. Test.
Is it working now? Did it start working?
Like when we come back to somebody giving a talk remotely, can we just like switch off the rest?
I think it's fine when there's like a Q&A, but I think I'm totally fine with that.
No, I mean the thing you did with the microphone was fine. I think so. Wait, is it possible? Sorry.
Oh, that wasn't very. I think that wasn't very.
No, but at some point it was fine. We just need to switch off the microphone. Is it possible to switch off the microphone?
To what? Switch
So
off the microphone?
at some point, I think our issue was that like the speaker from Zoom
when they would speak, there
Yeah.
would be echo, and I think it was everything was fine, but they would just also hear themselves on the microphone.
I think there was other stuff going on. I don't know. Wait, this is pretty helpful for debug. If you don't mind. If you don't mind, yeah. Thank you.
Okay, ask them to talk. Oh wait, we're getting feedback from the system.
I'm also fine with getting rid of a computer. Whatever do you think would be helpful?
I know, man. I'm trying.
Oh, there's a sauna.
No.
Might be you might be like I said.
Go ahead and ask them to speak again and see if they can hear. I want to see if.
What's that?
Go ahead and ask them to speak.
Hey, Maitreya, any chance you can speak again? We're trying to see if we fix
Hello,
that.
hey, test. Oh, yeah, I can hear everything. Yeah, okay.
That's good.
Yeah.
Yeah, that's coming out.
Wait, that's pretty good.
Right. That's not right.
Oh, it's not.
Right.
I'm okay with that. If that's
Tell them to go.
plug it in the microphone. Yeah.
Tell them to go again.
I think we have something like the way.
All right.
Yeah, there's no feedback now. It's good.
Okay.
Wait, so this was coming from here?
Yeah.
Maybe we can just use the microphone.
Oh, sure. Yeah. I'm sorry for the delay. Hopefully this will be resolved shortly. Maitreya, can you talk again? I'm sorry to make you do this.
No worries. Hey, Andrew. Hello, hi, everyone. Test. Working?
Yeah.
Good. Yeah.
Yeah, we can hear him, but it's not very loud.
Hi. Test. Hello. Better?
We can hear you, it's just not very loud.
Not loud? Okay.
I guess my voice is echoing. But the tech people are here debugging stuff, which is why we're asking you about this. Thank you for
No worries. Yeah.
Oh, no, it's fine.
Oh, wait, is it?
Hello.
Oh, we can hear him well. He's sure just let it go.
Yeah, now I hear feedback on Zoom as well.
Wait, actually now, can you speak again? I think now.
Hi. Test. Hello. Hi. Test.
I think the last one was pretty good.
It was still open to the system, so turning this thing off. And plugging this into here. And this is going to here. Okay.
Hey, whatever it was in the morning was working pretty well for a while.
Yeah, and go ahead and
Is this full?
It looks like we're still getting an echo, but Maitreya, can you say hi again?
Hi, everyone. Welcome to the Sight and Sound workshop.
Thank you. I think that worked well. I think the issue is my echo.
Yeah, I do hear the feedback on Zoom as well. So.
Unmuted. You hear that?
Okay, great. I'm gonna unplug this and we'll get back to you soon.
That's still. Okay.
Oh, so we need this one?
So yeah, you can throw in like that. Oh, but.
Check, check, 1, 2, 1, 2, test 1, 2.
I think we ran out of.
Can we have somebody talk on the other end? And see if it's working or not?
Excuse me, can somebody say something on Zoom, please?
Say something. I could play something. Yeah.
No, that's good. That's good. Wait, so does the sound come from here now?
It's coming from here and it's also coming out into.
So you can also
our
share from.
speaker.
Okay,
Yeah,
perfect. I think we're set.
Great. So everything's working, I think. Wait, can we try playing a sound on the
Yeah, let's do that as well.
It's the final
Like the
test.
violin test.
You just hold the microphone.
Wait, did you hear that
Okay.
from the?
It's just coming through the speakers on this. So we're gonna have to set your output, whatever, wherever you get into that to this device that you need. There we go.
Thank you. Let's do a round of applause for the. Great. So I'm sorry. So sorry for the delay. We're gonna proceed as usual and do our second paper session for the day, and it's gonna be chaired by Daphne.
Okay, welcome back, everybody. So we'll start with two papers that we didn't have time to show in the morning. And they're like both pre-recorded. So the first one title is Sound Adversarial Audiovisual Navigation, and I'll play the video now. Thank you. Moving next to the the next paper, that's also from the previous session. Title is semi-supervised exploration via multisensory ecogruity.
Daphne, the Zoom screen is not shared, I think.
Sorry?
I think the Zoom screen is not shared.
Oh, sorry. Is it okay now?
Yeah, works.
Okay. Great. So moving on to the next paper. Which one was the first one?
Rethinking.
So the title of this paper is How to Listen Rethinking Visual Sound Localization, and I will present it by Magdalena Fuentes.
Hello, you hear me well? Yes, okay. So I'm going to be presenting this work that was led by Hojang Wu and my other colleagues at New York University and Script. So the object of this work was in the context of like, what object is making that sound in an image? So if it's or a video of a violin, the goal is to find that is the object that's producing sound. If the video is on vehicles, the object is to find a vehicle in that image, given the sound. So the study was focused on three main things that we wanted to do. We wanted to understand the design choices behind visual sound localization methods, so the ones that existed before as well. We wanted to understand a little bit better what are the models actually learning from the data, from this audiovisual data, and we wanted to understand what insights the evaluation benchmarks, and by that I mean the data sets, are providing for this task. That's the part of like rethinking. So a little bit of context of how this is typically done. When you, like a lot of previous work, what they do is you have an image of and the corresponding audio of the object that's sounding there. And what you do is to train an audio and image encoder with some sort of distance, like contrastive loss, for instance, and project them into the same space. And for the localization part, typically what people do is divide the image into patches, so just smaller images, and then get the embedding, the image embedding for those patches, get the audio embedding from the corresponding, let's say, second of audio, and then compute the distance of the patches with respect to the audio, and those that have the violin should be closer to the audio than those that don't have it. That's what typically is done. And that means that you, as I said, get the grid, and then you get a bunch of embeddings, and you train your model like that. We took a little bit of a different perspective to this. What we did, we use explainability methods from like that are typically used in, for instance, computer vision, to understand where the model is attending for a given label. Instead of doing that for labels, what we did was to get the audio embedding from the audio encoder. So I get the sound of the violin, I get the embedding for that sound, and then I use that as a query for the image encoder instead of a label. So that will give me, hopefully, the image encoder attending to where in the image that sound was produced. That's an alternative way of doing localization that we explore in this work. So the study, basically, we looked at three things. Different types of encoders. Basically, in summary, don't worry too much about that very loaded table, but in summary, what we saw in the encoders was ResNet versus transformers. The localization strategy, so these patches, dividing the image in patches versus explainability. And then for the loss function, typically people use contrastive loss, this idea of bringing the two embeddings together. And there are some previous works that do negative mining, which is you get negative examples, not only from other videos, shuffling things as is typically done, but also getting patches from the same image. So those are the three things that we wanted to compare. So architecture, localization strategy, and the loss function. So a little word on test datasets before. We looked at 4 datasets for this study. And these 3 rows show the different statistics of those datasets. The datasets are Flickr SoundNet, the first column, BGG sound sources, music synthesis. Oh, thank you. Yeah.
Oh, sorry, I made more.
That's okay. Yeah, thank you. So the first column is Flickr SoundNet. The second one is BGG sound sources. Those two are typically benchmarks used for localization, audiovisual localization, then music synthesis and Urbansys, which I'm going to talk a little bit later. The first row is showing the number of simultaneous bounding boxes in those images, in the videos. So for instance, Flickr always has one at a time. BGG sound sources mostly has one, but also has some videos with 2 and 3 and so on. Music synthesis always has 2. Urbansys has a distribution that's like a little bit less concentrated. The second row, which is interesting, is the distribution of the position of bounding boxes for the different data sets. So you can see certain concentration for Flickr and BGG sound sources in the middle of the image. And music synthesis is 4 videos of different instruments. That's why you have these 4 things. And Urbansys is a traffic data set, so it's a little bit more spread out because vehicles are moving around. The last row is it's showing the percentage of frames and percentage of area of these bounding boxes, which is roughly the first one has like mostly the bounding boxes occupying 40%. The second one, same tendency, and for music synthesis and Urbansys, bounding boxes are smaller. Why is it important to look at these things, in my opinion? Because, for instance, based on these statistics, we use as baselines a bounding box in the middle of the image without any prediction of any model at all. Just to know what happens if we don't do anything, is just put a bounding box there. How do we score in intersection over unit? For music synthesis, instead we put 4 bounding boxes. And for Urbansys, it was a little bit more difficult, so we put like a bounding box trying to, that was the one that scored the best. So here are some of the results of the study. I'm going to try to walk you through them. So basically, the table is divided by data set. So Flickr, BGG, music, and Urbansys. The baselines are the ones that I just mentioned. LBS is state-of-the-art localization method that was published in CVPR last year. DSOL is only a baseline for music synthesis, and the 3 latest methods are ours. The first one is the RC-Grad is ResNet based, and the other 2 are transformers, and also a benchmark with text. So the image in the left, this one that first of all, one interesting thing that we observed with the baselines, for instance, for BGG, SS, and for Flickr, only with the bounding box in the middle of the image, we scored really high, compared even to the other of the methods and previous baselines, which was a surprising and not so surprising result, which we think is interesting for moving forward in these methods. And the other interesting trend is, like, for instance, for the baseline, the LBS baseline, we noticed that it tended to predict the heat maps in the middle of the image independently of the data set. So here is like the output of the model on the left, and on the right, the distribution, the actual distribution of the data set. And we think that has to do with biases of the data that was used to train, and also the patches that tend to concentrate or be coarser and concentrate to the patches that are in the middle in the training. And then for RC-Grad, which is our ResNet based model, we saw that it can adapt quite nicely to the different distributions of the data sets, and it is quite versatile in that sense. And for the transformers, we thought initially that the transformers will do better than ResNet, because that's what typically happens. It scored pretty bad, and what we noticed is that is because of the way that we are evaluating these models. Typically, if you are gonna, let's say, identify a bird that's sounding, the bounding box is around the bird. And what the transformer tend to do is to focus on a specific, like the peak where the sound was actually being produced, so, or the head of the bird, and that scored really badly because the bounding box is much bigger than that. So there is also like a matter of like maybe with the actual data set that we have right now at the level of the coarse bounding boxes we have, it's very difficult to evaluate these models. And just a qualitative example here. This is what I'm talking about. The left square is all BGG sound sources examples. The right is Urbanza's. This is one of the examples that, like, if you see, I don't know if I can. Here, this is a bird. This is the prediction, and bounding box is like out of the whole bird. And the performer is just saying, like, this is where the sound is being produced. And that's, of course, going to score bad, but it doesn't mean that necessarily the model is wrong. And these are the type of differences that we saw between ResNet and the transformer. And yeah, things like another thing, like these models are typically use one image and a portion of sound. So they are, don't use any dynamics. And for examples such as this one, in which this vehicle is parked, this vehicle is moving, this one producing sound, the model doesn't know, and it will say like, oh, the bigger car is the one that's producing sound because of this lack of dynamics. Just one demo of the output of RCGrad, the ResNet model in the urban data set. And this one you saw in the test sound. So just a couple of words on future work on that. As I said, there is a lot of room for improvement of audiovisual visualization, localization models. If we add dynamics, for instance, flow or multiple frames, if we add multi-channel audio, all of these models are based in mono audio, and even stereo will produce or give a lot of information about the spatial information about the sources. And also moving from like all videos in third person to egocentric will be super cool to do. And that's it for RCGrad.
Thank you so much for.
Is the sound still coming through? Somebody said they were having trouble.
The sound is still getting through.
Oh, they can't. Okay, oh no. Okay, so
I think the Zoom sound is not shared.
Sorry?
Oh, I think you have to hit.
The Zoom sound audio sharing was not enabled. Like we could hear the speaker, but not the sound from the computer.
Okay. So sorry about that. Can
No,
you,
it's not.
you could hear the examples?
every one of these.
Sorry, one moment. Can you hear it now?
Yeah.
Oh yeah. So sorry about that. That should be fixed now.
Yeah.
Okay. Yeah, thanks so much for this presentation. We'll move on to the next one with the same presenter. So the title of this paper is Urbanza's, like the data set we saw about urban sound inside dataset and benchmark. So take this down here. All right. Hopefully this doesn't annoy you like before.
So hi again. Now I'm going to talk about another piece of work that's very related. Basically, it's that data set that one of the data sets I mentioned just now. And this work was done in collaboration with people from New York University, Universidad Pompeu Fabra, the MTG, Bosch Research, and Universidad de la República. So the context of this data set is that, as you all know in this workshop, we use, to navigate the world, we use the location of sound sources. When we cross the street, we pay attention to cars are coming or a siren, and we make space and stuff like that. So being able to make machines to recognize sounds and navigate as we do will has many applications in self-driving cars, or even for people that are hard of hearing, to as assertive devices and so on. So we looked into this a little bit, and what do we want to do for making machines able to do that? Well, understanding a real scene is determining what is sounding, but also where it's sounding and how it's moving. And in particular, in urban settings, this is super interesting, but because it will allow to do, for instance, low-cost privacy-preserving mobility systems if we do only audio, awareness devices for the hard of hearing, and so on. So when we start looking at this, I come from the audio side of things. I'm a machine listening researcher. The way that this is done in machine listening, so machine learning for audio, is typically that data sets are synthetic or done in unrealistic conditions, because localizing a source for audio people, for us, means typically having multi-channel audio, so multi-arrays, 4, 5 channels, and then knowing where the sound source is located, the distance to the microphone, the elevation, and the angle with respect to the microphone. And doing that in the wild, in like urban settings or real world applications, is really complicated. So what we did is to look at what computer vision people are doing and like trying to bridge thinking about that. And we got inspiration from a paper that was looking at inferring the position of vehicles, but instead of knowing all of these details about the location of the vehicle, they were using bounding boxes as a proxy for the position from the video. So that's why we curated this data set that's called Urban Sound and Sight, or Urbansas, that has more than 5,000 clips, spanning 50 locations in different countries. And the reason why we do this is because when we started looking at it, at this problem, there was no available data set for it. And we wanted to be able to do not only audio, but audio-visual research. So we went all in annotating the data set, and we annotated not only the audio, but the video. The data set has video at 24 frames per second, which we annotated at 2 frames per second with bounding boxes of the different vehicles that appear in the data set. We annotated occlusions. We annotated the audio with strong labels, meaning the beginning and end of each audio event, with classes, with off-screen sounds. And the idea is that at the interaction of these two things, we can understand better how things happen in urban sounds, because sometimes, like you can see here, sometimes you hear something before you see it, or you see something before you can actually hear it. So we annotated both audio and video to understand these things. We paid particular attention and having a diversity of conditions in the data set. So both active and inactive scenes. So not all of the scenes have vehicles. There are videos of actual urban scenes. Sometimes there's a vehicle passing, sometimes there's nothing. And that adds a really extra challenge for modeling. Different amount of vehicles per frame. So there are really complex scenes, or like just only one vehicle, different classes of vehicles, different camera angles, different scene compositions, etc. And we also included the lighting, so night and day labels. And we provide, as part of the release of the data set, a benchmark that does only audio localization, but it does only audio localization again in the video. It's just a standard audio model that uses not only the log spectrogram that you might be familiar with, but also the difference in phase of the audio signal. Like, I'll see that. And produces basically where in the image is the vehicle located and what class is it. So, and we quantized the image in different regions to make that localization. So it will look like this. just to speed up, this is how the model looks like. The output is in the middle, the ground truth is in the right. And the nice thing is that we evaluated this with the intersection over union that can be compared to the audiovisual datasets, the audiovisual models, sorry. I'm not gonna go through the results, but basically the random baselines work really, really bad. And it's a challenging problem that we hope this dataset, we managed to get some good results, but it presents really interesting challenges that we hope that are useful for the audiovisual community as well. And some of the directions that I'm exploring is one of the papers that was presented in the previous session. So audio-only localization with these probability distributions, the visual sound localization, and more than that. And that's it. Thank you.
Thank you so much for those presentations. They're very interesting. The next paper should be this one. Slideshow, here you go. Okay. So the title of this paper is on negative sampling for audiovisual contrastive learning from movies. And the presenter is Mari Kalaye. Take away.
Hello, my name is Mahdi, and I'm going to talk about negative sampling for contrastive learning from movies. This is a joint work with my colleagues, Shervin, Lingi, Nagendra, and Ashok at Netflix Research. So let's quickly review how does contrastive, cross-modal contrastive learning works. Given a bunch of videos that you have, we define a two-stream network, one for video, one for audio, and use those in order to extract embedding for video and audio. And the objective is that the audio embedding for an instance I is closer to its own video embedding than any other video embedding coming from other instances. And of course, you can swap the places for video and audio. So that's the gist of cross-modal. And if you compare it, for instance, with the SimCLR objective that you give one instance and augment it two ways, think about augmentation as switching modality. You switch from video to audio or the other way around. So that's the same idea. But of course, like we are Netflix and we want to do this on movies. So we very soon realized that applying it very naively doesn't work. So we start deeper into what's happening. So the first thing is the data regime is different. Usually when you look at the data sets that are used for self-supervised learning in literature, these are like kinetics, audio set. These are, I would call it large catalogs of short videos. You have hundreds of thousands of 10-second videos. In our case, we have a small catalog of long videos, a couple of thousand movies, but each one is 1 hour and a half. On the top of that, we realize that the distribution of the data is also very important. So I'm using this example, for instance. The first row is some random frames from Titanic. The second row is from Matrix. And if you just uniformly sample your mini batch, you would realize that you would have a lot of examples that come, we call it cross content. One is from movie one, the other one is from movie B. And these are legit negative pairs, but they are extremely easy for model. And we actually did a very funny experiment, just did average RGB values of frames for show, and we just plot them. It's perfect for separation of movies. And these, and there are many more things like this, such as the face of the main character, the scenes, the thematic music that the director uses. All those things, we call it artifacts, content exclusive artifacts, that if you don't use them properly, you would end up having a contrastive model that is, it's a very easy objective. So the training goes down, you're happy, you do generalization, nothing else. So it's important to do negative sampling within the show. And for instance, if you pick in this one, the red and red, first these are like objects that appear in the show, let's say face of the main character. It's likely this happens. It's not very probable because you have the diversity within the show. So pretty much what we did in this work was to start extremely sampling negatives from one movie. So we even got to a case which the entire batch at each training, each step of training was coming from one single movie. The other thing which is different for training from movies versus like Kinetics or AudioSat is that these are uncurated data sources. If you look at Kinetics, these are like well-trimmed videos. There's a single action starting from there and ending. So yes, while we are not using labels, it's still a well-trimmed data set. So your supervision is through the clean data set. While in movies, there's nothing like this. So we have artistic curation. There's no blurry frames. They're like perfectly shot, but there's no semantic curation. So with that said, I'm gonna quickly move through the modeling. We have like N movies. We clip them into 3 seconds. We have audio and video for each one, pass them to backbones for video and audio, projection head to get to some common latent embedding, and then compare it. In order to create the batch, one thing we make sure, and this is like regular NCE loss, one thing that we make sure is to sample a lot of clips from the single show. And pretty much the idea is this: if you just pull all the clips of all movies together, you do IA random sampling uniform, it's a very low probability that you end up 2 clips from the same movie in your batch. Hence, most of your negatives in an NCE formulation are going to be extremely easy. So we force it to at least pick K samples from each movie. And the one thing that we want to measure is we calculate the similarity of negatives, just negatives, and we put it in 2 sets, similar and dissimilar. And the ideal goal is these 2 should not be different. Otherwise, the model would cheat because it knows this negatives come from the same show. Let me just quickly reduce it. So that's a metric we track. So quickly to the experiments. Here you can see that as we increase the K, means more negative sampling from the same show, the training becomes harder as expected, but generalization becomes also better on 3 action recognition and 2 audio classification. This is linear evaluation, and these are gains on the top. I don't have more time in 5 minutes to go over these, more than happy to answer afterwards. We also wanted to see that the fact that we are doing this sort of sampling, does it actually deliver what we intended? We want to get rid of the content exclusive artifacts. So the plot on the left actually shows the KL divergence between the distribution of the negatives when you sample within a show or just uniformly. And as you can see, if you don't do that, you just the regular sampling, the naive IID sampling, not only the difference is larger, but the model continues to cheating even more and more as you continue training. That's why it goes up. But as you increase K, you have a way to control this thing and do not let the model to exploit these artifacts which are not semantically useful. Another way to measure it is we define a like clip-based movie classification. Pick every 3 seconds and assign the label of the movie and try to do classification. It should not be able to do that unless there's some artifacts there. And again, we see by doing this, we can reduce it. I'm not gonna go through the state of the art. You can just refer to the full papers on arXiv, but we are not beating the state of the art. So do not expect to see beating state of the art when referring there. So that's it. Thank you.
Thank you so much for the presentation. Okay, so moving on to the next paper, which is should be this one. So this one is from the University of Tampere.
Sound.
Sorry?
It has sound. So
it should be all right. Hopefully we okay. And so the title is Audiovisual Voice Separation Transformer. We presented you by Juan Montesinos.
Yes.
Okay. Yeah?
Yes.
Okay, awesome. So take it away. A moment. Let you. Cheers.
Okay. No. Enable media. Okay. So hello everyone. Glad to be here to present this work in audiovisual voice separation. First of all, let me a bit introduce what audiovisual voice separation is. And the idea would be we have a mixture of sounds and we would like to isolate the voices present in that mixture of sounds by leveraging the visual information. So we can see a very simple example. So here we have 5 voices, 3 instruments. Our goal could be to recover the voice of the guy inside the box. Basically, the main advantages of this audiovisual versus audio only is that we leverage leap motion, so the algorithm, the performance is usually better, and it works well in noisy scenarios. Also, we can deal easily with variable amount of voices, but the major drawback is the additional computational cost to process the video stream. To alleviate this, we propose to use face landmarks, which are what is inside the box. So those are key points that keeps or summarize the structure and the motion of the face. So we can get rid of some pre-processing steps compared to using raw video. And there are some other advantages. So we can reduce the storage cost. That for people like me in smaller universities is very good. So for example, working with video, even in a poor resolution of 200 by 200, that implies terabytes of data and millions of data points, while landmarks are thousands of points. So as well, the fewer data points, probably the fewer model parameters we need to solve the problem. And it's also less prone to overfit, so that we can end up training end-to-end in both large scale and small scale data sets, as we will show later. And also using face landmarks is good from a privacy concern perspective, because we don't exploit the ethnicity or the accents of people, and we don't need to keep track of the identity. For example, we can extract the face landmarks on an edge device and send that plus the mixture to a cloud server, keeping the privacy of the user more or less intact. So to have a good trade-off latency versus performance, which was our main goal, we proposed this model, which is a transformer-based model, where we process the face landmarks with a graph convolutional network. So we extract from the audio the spectrum via short-time Fourier transform. We downsample it for efficiency, and we use this encoder that keeps the temporal dimension. And we can construct this audiovisual signal that is fed into a transformer that processes the signal both from the temporal perspective and the frequential perspective to obtain a complex mask. So basically this mask, if we multiply that by the input spectrum, we're gonna get a very good estimation of the isolated voice. However, we realize that there are some interferences that are really attenuated but still present, and they can be a little bit annoying. And we show that if we use a second smaller stage, so this encoder decoder, it has very few, 10 times less parameters than a transformer, and we solve a different optimization problem. So at the beginning, we were solving an L1 over a complex mask. And in the second one, we have some binary masks and we use binary cross entropy. So if we solve a different optimization process with this small network, we can boost the results and save training time, power, resources, and etc. So we test this in a large scale data set for speech. It's Voxelab, has 2,000 hours in different languages. And we compare mainly against Visual Voice, which is a very good paper using raw video and the appearance of the people. And we basically perform quite similar, although we have less interferences, and you will observe that qualitatively. So this is an example. We have these two guys from a show in the US.
I'm just glad that I've been able to remember my materials.
I didn't know that. I didn't know that. And they didn't know that I didn't know that.
And basically, this is the estimated landmarks as well as the prediction. The model is not trying to remove people laughing, so that will not be filtered out.
I found out they were Mexican. I didn't know that. I didn't know that. And they didn't know that I didn't know.
And if you compare to Visual Voice, which was a state-of-the-art paper, you will see that there are less interferences and that we model better the situations in which the person speaking is seen from a side view.
I'm just glad that later on I found out they were Mexican. I didn't know that. I didn't know that. And they didn't know that I didn't know. And that's
so in short, yeah, we can reduce the interferences and improve that scenario where from the side views. We also tried this on singing voice. The main conclusion here, despite the papers, is that we cannot, as you can see here, if we train our model in speech, it cannot extrapolate well to singing voice. So just quick example. It failed, but yeah. So this is filtered out. And This is a previous paper where you can see there are some corals and so on. Thank you very much for attending.
Thank you so much. Very interesting results. Let's go to the next paper. Could the presenters please? We're running a bit out of work, so please try to keep it within the 5 minutes. Also, like look at Andrew and me. We'll let you know if you're like running out of time. So the next paper is called "Everything at Once: Multimodal Fusion Transformer for Video Retrieval," and the presenter is Nina Shvetsova.
Yep.
Sorry about that. Okay.
Thank you for introduction. This is joint work with the following authors. Our world is multimodal, and humans capture their world combining multiple sensory signals such as vision, sound, or touch. And video data approximate this kind of input, combining video and audio information, and this information can be further enhanced with text description. So co-occurrence of multiple modalities can be used to learn multimodal representations, multimodal embedding space. In such embedding space, the input from one modality, such as text, can be matched to other modalities such as video, audio, or combined video-audio representation, and enable such tasks as video retrieval. So how we can learn multimodal embedding space in self-supervised? One of the standard solutions can be to utilize pairwise contrast losses. For example, in case of video, audio, and text, we can extract features by modality-specific encoders, then we can pull features over time, and then project them into multimodal embedding space by modality-specific projection. And in multimodal embedding space, we can apply pairwise contrast losses, such as contrast loss between video and audio modality, contrast loss between video and text modality, and text and audio modality. So in this case, we have a multimodal embedding space where we can match one modality to another modality. But is it good enough to represent multiple modalities at once? For example, if we want to create representation for video and audio modalities together, we can separately extract embeddings for each modality and then average them to obtain video audio representation. But in this case, embeddings were extracted independently and they do not utilize clues from other modalities. So how we can obtain a fused representation for such input? So for this, we propose to use the fusion transformer. So let's consider the case where we create representation for all three modalities together. So our architecture started the same with extracting tokens with modality-specific encoders, and then we combine them to a joint set of tokens and apply fusion transformer where we allow tokens from modalities then to choose. And output tokens that are enhanced with the information from other modalities then combined into final representation in a similar way. But how we can train such a fusion transformer in self-supervised ways that can utilize correlations for all modality combinations? So for this, we propose to train a fusion transformer with a combinatorial input on all possible modalities combination. So we apply fusion transformer to obtain video representation alone, only for video and audio together, for audio alone, and all other combinations. And we apply contrast loss not only between single modalities, but also between all possible combinations of modalities. So in terms of performance, we related our method in zero-shot text video retrieval task, and we compare it to the methods that do not use audio information at all, and to the methods that used average video and audio embeddings and as video representations. And we show that a fused video audio representation from our method increased performance in 6% in UCOOC2 datasets. We also evaluated our method in zero-shot action localization task and show that fused video audio representation also improved performance in both considered datasets. We also analyzed fusion capability of fusion transformer. Here I'm showing average attention for query keys tokens from different modalities. And we observed that some heads have strong attention incitement for single modality fusion, and in between there is some heads that are responsible for cross-modal attention. And here are some results for text-video retrieval. I'm showing top 3 retrieved videos for a given text query, and we found that even if correct video does not occur in top 3 results, retrieved videos are still semantically relevant for the query. So that's all. Our code models are available. I invite you to try it out, and you can find more information about our method in the paper or in the poster session. Thank you.
Thank you so much. It's very interesting. Let's move on to the next. By the way, we're running out of time, so we won't do a Q&A session, but we'll have the pretty long poster session afterwards, and feel free to find the speakers there and have discussions about the papers. So next presentation is the paper title is Leveraging Real Talking Faces via Self-Supervision for Robust Forgery Detection. And the presenter is Alexandros Chaliassos. Sorry. Here you go.
Hi, I'm Alex. I'm a PhD student at Imperial College London, and today I want to talk to you a little bit about our CVPR paper, Leveraging Real Talking Faces via Self-Supervision for Robust Forgery Detection. So 2 main types of face forgery include identity swapping and expression swapping. So given a source and a target video, identity swapping maps the identity from the source onto the target, while expression swapping transfers the expression, keeping the identity unchanged. So there's been a lot of recent interest in detecting such facial forgeries due to the potential social harm. And although deep learning-based detectors work very well on samples generated by forgery types that has seen during training, they tend to underperform on novel types. There have been recent works that address this cross-manipulation generalization problem, but they often focus on low-level cues that are easily destroyed by common operations such as compression. So to address both cross-manipulation generalization and robustness to common corruptions, previous work, lip forensics, forces the network to focus on high-level cues around the mouth region by pre-training the network to perform lip reading. However, it focuses exclusively on the mouth region, ignoring potentially salient cues on other facial regions, and also requires costly text transcriptions in the pre-training phase. So for this work, we ask ourselves, can we force a detector to focus on high-level cues related to facial appearance and behavior by leveraging real and unlabeled talking face videos, which are abundant online? So to that end, we propose a 2-stage approach dubbed real forensics. And in the first stage, we leverage the correspondence between the auditory and visual modalities in talking face videos. So in particular, we learn temporally dense representations in a self-supervised way that capture the information shared by the 2 modalities. So this is factors associated with lexical content, identity, or emotion. In the second stage, we use these learned representations as targets to be predicted by a forgery detector in a multitask fashion in order to force the detector to focus on these high-level cues. So in more detail, in the first stage, we use a cross-modal student-teacher framework whereby students ingest real video and audio and are tasked with predicting targets generated by the momentum-based teacher from the other modality. The students contain additional predictors on top to prevent the so-called representation collapse. And the students are updated via a usual gradient-based method like Adam, and the teachers via an exponential moving average operation, like in the method bio, which this is inspired by. And in the second stage, we use the video teacher, which is now kept frozen, to produce these targets to be predicted. So to assess cross-manipulation generalization, we follow the protocol of training on 3 of the Face Forensics ++ dataset manipulation types, and then testing an unseen type. And we do this for all 4 types in dataset. And we see that we perform on par with the state of the art in this setting. Further, for cross-dataset generalization, we train on the full Face Forensics ++ dataset, and then we test on unseen challenging datasets. And we see that it performs well, and shows that the detector can perform well even when it is exposed to more challenging forgeries than originally trained on. Finally, to test robustness to common corruptions, we train on clean samples, and then we test on samples that have been corrupted by various common corruptions. And we see that relative to other methods, our method is more resilient it tends to be more resilient to corruptions, especially those that corrupt low-level content, such as compression. And this suggests that it indeed focuses more on high-level cues. And yeah, for more experiments, the ablation study, you can check out our poster session Thursday, or check out the full paper on arXiv. Thank you.
Thank you so much, Alex. Okay, I think we have 2 more papers. So actually, okay, this one is a video. Okay, let's do this one, and then have one more presentation. We're done.
Hello, everyone. I'm Ping Chuan Ma, a 4th-year PhD student at Imperial College London. In this presentation, I will talk about visual speech recognition for multiple languages. This is a collaboration work with Stavros Petridis and Maya Panti. Visual speech recognition, also known as lip reading, allows machines to transcribe videos directly into text without any audio signals input. Today, to achieve better VSR performance, researchers focus on using large training sets. However, in this work, we demonstrate that designing better models is equally important to using large training sets. We propose a new architecture based on auxiliary tasks, where the VSR model also predicts audio and visual representations from pre-trained ASR and VSR models. And we show our approach outperforms all existing VSR works trained on public available datasets in English, Spanish, and Mandarin by a large margin. For English, we use public available datasets, such as LS2 and LS3, which are the 2 largest public available lip reading datasets. For Mandarin, we use the CMLR dataset. For Spanish, we use not only the CMU Mosaics, but also TED Talks in Spanish. Apart from this, we include unlabeled datasets like FoxLab2 and AV Speech for training. Next, let's move on to the models. The left image shows a baseline VSR models. The baseline VSR models is trained with cross-entropy loss and CCC loss, which are the typical 2 losses for speech recognition. The right side shows a VSR model with auxiliary tasks. The proposed auxiliary tasks are able to provide additional supervision to the intermediate layers of the VSR models. The training pipeline includes 2 steps. First of all, we train baseline ASR and VSR models. Then, at the second step, we freeze the weights of the pre-trained ASR and VSR models and train a new VSR model with auxiliary tasks. In the auxiliary tasks, we try to map the prediction from the intermediate layer of the new VSR model to the targets from the frozen ASR and VSR models. We present the results of LS3 on this slide. Firstly, we show that our model achieves SOTA performance without using extra datasets. Secondly, we show that the VSR performance goes much better by including more training data. For example, it leads to 17% absolute improvement in word error rate compared with the current SOTA performance. This confirms the recent trend in the literature where using large training sets results in better performance. We also present results for other languages, like Mandarin and Spanish, and we show that our model also achieves SOTA performance on these two languages.
In any case, once this technology really becomes mature and we can truly do face and facial expression analysis in the wild,
衷心祝愿大家在新的一年里新春愉快，身体健康。
Muchos vecinos habían pasado la noche entera recortando sus propios papelitos porque también habían descubierto.
Oh, I think this was it. Okay, let's end this video. Okay, and we have one last presentation. So, oh. Okay, so the name of this paper is Tap to the Beat, cross-modal music beat localization for dancing videos. Will it be presented by you? You. Okay, fantastic. Great. Okay, should be okay.
Thank you, everyone. I'm Yu from Princeton University. I'm glad to be here to present our talk about Tap to the Beat. It's a cross-modal generation of music beat based on the dance music. So we propose a new task that is to locate the music beat based on the dance moment. So the only input here is the visual part, and we want to find the music beat with from the dance moves. So the motivation here is people can naturally feel the rhythm and the beats when watching the dance videos. So as shown in the figure, we can see there are strong correlation between the dance moment and the music beats. So if we can successfully predict the vision predict the dance beat from the vision input, it maybe we can generate potentially better temporal alignment between the visual part and the audio part. So this is so here becomes the problem formulation. Given the video frames, we first extract the 3D skeleton points for each frame, and then we can formulate the dance moves by using all the key points. And in addition, we also calculate the acceleration of each point. So it is calculated by the difference between two frames. So here we found this speed difference may be better for the model to capture the beats. This is target of this problem. So we have a lot of body movements, and we can find the ground truth of each beat based on the music part, and we use that as the ground truth label for the vision prediction. So this is our proposed transformer for this task. In general, it contains two subsets, and we can leverage both the 3D body motion and also the speed difference between the key points. So given the dance movement skeleton as input, we first leverage the skeleton feature of each joint and input them to a transformer encoder to leverage the video information. And meanwhile, we also calculated the acceleration of each joint. So we also input the speed difference to another transformer, and then we filled their feature by a joint cross model transformer encoder. And then we take the output to a decoder and generate the final prediction using MLP and a clarification layer. So to better leverage the supervision signal in this task, we also propose to use a voting system, a voting mechanism for the inference. So actually, it transfers the prediction from a binary clarification to a sequence prediction. So here, the training target for each frame is a remaining step to the next bit. So in this way, the model can be clearly confident at the predicted labels, which means how many frames to be the next bit. And in this way, this is some video demo. Maybe we cannot play the sound here. Okay, it's okay. So finally is this is our result. As it can be seen, we have two kind of evaluation here. ACCB means the background accuracy. It means the beat accuracy, and the ACCB means the non-beat accuracy. So our model can achieve the trade-off between these two kind of the two kind of prediction. And that's all. Thank you.
Thank you so much. Like we said, sorry about running a bit late, so we're gonna skip the Q&A session. And yeah, we encourage everybody to discuss about the papers we present here during the coffee break. So let's thank the speakers again once more.
Good, so David should be online now.
Ooh, I think, anyway.
Hey, David. Great, okay.
Can you
You
share
want to do a screen share?
Yeah. Once I screen share, I think I'll lose sight of you. You can hear me okay?
Yep.
Perfect.
You won't see anything here anyway, so great. Looks good.
Perfect.
So I'm really excited to welcome David Brang to speak here today. David is an associate professor of psychology at the University of Michigan. And we've seen a lot of computational work today talking about multisensory fusion, cross-modal learning. And David studies those topics too, but from a psychology standpoint. He studies how the human brain integrates information from vision, sound, and touch. So I'm really excited to hear what David has to say.
Perfect. Thanks so much, Andrew. I really appreciate it. Thanks for having me at this workshop. So very broadly, my lab studies the neuroscience of auditory visual interactions. And if at any point you can't hear any of the things that I'm presenting on the screens, kind of flag me down. I can still see video, unfortunately. So broadly, the goals of my research are to try to understand what information is shared across the senses. So in general, neuroscience has typically focused on the sensory systems in isolation, this idea that we have an auditory system and a visual system. But by integrating information across the senses, the brain can actually generate better models of the world. These are computationally more efficient. They enable better perceptual processing, faster responses, better detection. And in the context of noisy environments or after brain damage, one sense can support processing in another modality. And so a lot of people have already given the great examples of how lip reading can facilitate speech perception. And so my lab studies how the human brain can enable these auditory visual interactions and the statistical properties of the environment that they pick up on. And then we apply these multisensory enhancements in a clinical context. So in this talk, I'll focus on how sounds benefit visual processing, and conversely, some of our other work on how vision benefits speech. So two sides of the same coin. And so one tenet in our work is that information is transferred across the senses to really optimize our experience of the world. And so there are different levels at which information is shared and different neurological mechanisms through which one modality can affect another. And I think a lot of these things can be useful when building computational models of how the senses interact, because sensory interaction is not a unitary phenomenon. There's very different types of mechanisms and types of information. So one of the most common effects that we see is that when you have any type of co-occurring stimulus, so this can be a sound and a visual image appearing at the same time and at the same position in space, then this will actually increase neural activity, increase the the neural processing to that specific auditory and visual stimulus. And this information is transferred directly across the modalities. You don't need any secondary systems to coordinate this transfer of information. It's incredibly fast and robust. Alternatively, other cross-modal representations are much more conceptual. So these can be amodal representations, the idea that a large object is going to be associated with a loud sound or a high pitch. And these are all based on intensity mapping, such that you have this high level of each of these representations versus a small object will be associated with a quiet sound and even a low pitch or a dim flash of light. And so these are more amodal or higher conceptual representations. And further, there's some representations that are cross-modal, but a little bit more ambiguous, and we don't have a perfect understanding of what causes these sorts of representations. Sound symbolism, or the Buakiki effect, is a popular version of this. And so this is cross-linguistic. Majority of languages across the planet have this association for wanting to associate the sharpish object with kiki and the roundish object with the word booba. And we think this happens because of the statistical mapping of the shapes that our mouth actually makes when producing these sounds. And so you think that these roundish shapes should be associated with more of a curvature of the sound and the text. And so there are a lot of different ways that perception benefits from multisensory signals. One already alluded to is this idea if you have a simultaneous auditory and a visual stimulus that's located in the same region of space, it's going to enhance neural activity to that specific stimulus. And so this would be greater than if you just presented either the auditory or the visual signal in isolation. We use this as a cue because if an object is present in the environment to both modalities, it's likely that it's an incredibly salient cue and we want it to attend to that stimulus. And so we have this super additivity of response to that specific stimulus. And this also plays in the idea that across the modalities, you have uncorrelated noise, but a correlated signal. So the easy way I like to think about this is you can see better with two eyes versus one eye. Even though the image to both your eyes is almost the same, you have less correlation of the noise across the two eyes. And so you have better vision when you add in this second redundant signal. And so a lot of the redundancy across the modalities can enhance perception, even though it's not exactly adding new information. The other way that the senses can help one another is each can have different expertise. Within the auditory domain, you have great temporal precision for the onset and offset of specific sounds, and you have spatial precision around your entire body, whereas you have limited line of sight within the visual modality. Conversely, within the visual frame, you have great spatial precision for anything you can see in front of you. And finally, each of the senses receives different information at different times. And so as I'm speaking, you get preparatory lip movements that can actually precede the onsets of sound, particularly gestural cues, if you can see anything on the video, can precede the onsets of different beats and help segmentation of words, or words within a sentence. And so the timing of the modalities can be asynchronous, and that asynchrony can actually help you provide or help you process information as it comes into your field of view. So today I want to look at a couple different ways that we think that the brain supports our ability. Oh, is everything okay?
Oh, yes, it is, but it's fine, keep going.
Different ways that the brain supports auditory and visual processing. First, starting how the visual system benefits from auditory information, and then conversely, how the visual system supports auditory speech perception. And so behaviorally, we know there are a lot of different benefits of auditory processing on vision. If you present a sound at the same time as any type of visual stimulus, if you're trying to localize an object in space or respond as fast as you can as a race car driver to respond to that flash of light, a sound is going to increase cortical excitability within the visual system, speed up reaction time, and enhance detection thresholds. And if we look in the brain of humans, we can actually see that there are direct connections connecting up the auditory and the visual systems. But it's unclear what the exact information that's transmitted across these different modalities. My lab uses a technique called intracranial EEG to answer a lot of these questions in addition to other neuroimaging approaches. And so the reason why we want to use this approach is because it leverages high temporal and spatial resolution in allowing us to track neural activity as it moves through the brain. So physically what we do is we implant electrodes in the brains of patients with either epilepsy or a brain tumor. So it's a clinical tool that doubles as a research tool within neuroscience. It's the only way that you can really acquire direct neurophysiological information from humans, and it's a relatively rare clinical tool. And so it's a unique opportunity that we have access to be able to do psychology and neuroscience studies with human populations and measure electrical activity generated in the human brain. And just as a side to orient people a little bit, this is going to be a raw voltage signal that we're acquiring from the surface of the brain as individuals are watching or listening to different types of stimuli. And then we can break down this raw voltage signal into its spectral components to be able to try to have some resolution of different types of information. In the low frequency domain of these neural signals, we can look at kind of a feedback or these top-down modulations of neural responses in this low frequency oscillation. Conversely, high frequency activity in the spectral power reflects a bottom up or this feed forward response. And this is analogous to any type of processing within a recurrent neural network where you want both of these feed forward and feedback responses to be able to modulate neural activity. This on the right is an examination of what some of this looks like if you just have somebody move their hand while you're measuring both the high frequency and the low frequency activity. You can have this very small response, neurons responsive to the hand moving, and then top-down feedback that's going to modulate neural activity much more broadly, such that if you had them attend to a region of their body, you're going to have much more of a broadband response throughout their motor system. And so looking at auditory visual interactions with this technique, we can start to examine the type of information and the processing that happens when sound enters into the visual system. So the first thing we found is that sounds activate visual cortex incredibly quickly. Within about 30 to 50 milliseconds after a sound is presented, you get activity evoked within the visual system. And so this is an electrode on this lower left plot implanted within early visual areas, primary visual cortex of the human subject. And then we would have a sound presented at this time point and then activity evoked in the visual system. Again, there's no visual stimulus. This is just the neural activity evoked to a visual response, or to an auditory response, sorry. And for context, the visual system actually processes visual stimuli quite slowly. You don't usually respond to a visual stimulus until about 50 milliseconds. So sounds can actually modulate neural activity more quickly to sounds than to visual stimulus, which feels a bit counterintuitive. And it's not just a white noise burst. Any type of auditory stimulus and any type of task will evoke this activity within the visual system. So even if your eyes are closed, you're relaxing, sounds are modulating activity in the visual system at all times, even if there's no visual stimulus to attend to. We see this effect broadly across the brain within the visual system. So this is all different regions of the visual system here. Any non-black electrode is regions that are responsive to sounds in addition to visual stimuli. And so the majority of visual areas actually are very sensitive to sounds. And then we can also compare the types of responses in this low frequency or high frequency activity. And there's a big difference in why or the physiological response of a sound in the visual system once we break it down into its spectral components. Because even though sounds are modulating activity within this low frequency domain, we don't tend to find that sounds modulate high frequency activity. So this driving of neural activity, these feed forward bottom up responses in the visual system. So this is a sound onset in the low frequency domain. A visual onset 400 milliseconds later produces a similar type of low frequency response, but a very different pattern when we look at high gamma power, this measure of how much action potentials are being generated within the visual system. The visual response generates action potentials here, but we don't tend to see action potentials generated by the sound. And so one possible consequence of this is that sounds are activating visual cortex in general without relaying any content. And so one of the important things that we want to be able to understand is what is the information that's actually being relayed across the senses? What statistical features of the environment is the visual system picking up on because the auditory system it has some relevant information there? And so one of the first things we wanted to understand is because the visual system has great spatial perception, we wanted to see whether auditory spatial perception actually biases spatial perception within the visual modality as well. And so basic perceptual neuroscience, if you look at the left side of your visual field, that's going to be processed by the right hemisphere of your visual cortex. And conversely, left hemisphere processes the right side of your visual field. And so we can use this hemispatial bias to present subject sounds that are either left lateralized or right lateralized and see whether each of these sounds has preferential activity into what we call this contralateral region of visual cortex. So effectively, does a left sound bias the same types of visual neurons that are sensitive to visual neurons that care about the left region of visual space? And that is what we find, that left sounds tend to bias the same neurons that would be responsive to a left target in the visual space. So the spatial alignment of auditory and visual stimuli is responsive within these early regions of visual cortex, again, responding within about 30 to 50 milliseconds after sound onset. So sounds presented in space actually bias early spatial processing within the visual system, which makes sense because if you have a sound presented out in space and you see a target in that same region of space, you'll be faster and better able to detect that something is there in your environment. Or even more importantly, if you hear something over on the left, you can saccade over to that object extremely quickly, and you'll prime up those visual neurons to be waiting and ready to see whatever that object is in space. We've replicated in this in many different patients and even with different types of stimuli in different visual regions, but always find the same pattern where you have stronger inputs in the same region of visual space for different types of sounds. But that isn't the only type of information we think is being transmitted. A lot of auditory neurons don't only care about the onset of a sound, but if you have a continuous auditory stimulus, like me speaking here, I have an onset of a speech stimulus, and then eventually an offset of that sentence. Auditory neurons tend to care about these event representations, so the onset and the discrete offset of a sound, to help parse an event in space. And so we can look within the auditory and the visual system to see how each of these areas care about these onset-offset responses as well. This is a spectral breakdown of auditory electrodes, both to the onset of a sound and an offset, with the responses here, a quiet period while the sound is playing, and then a second offset response here, different electrodes replicating that effect. We can see onset responses, offset responses, all within the auditory system, showing that there's this event segmented representation. Visual electrodes show the same pattern. You have an onset response and then an offset response once the sound stops. So the visual system is tagging the onset and offset of a visual signal as well to help us parse these auditory events in the environment on the assumption that many times a visual event is going to be happening at that same region of space, and there'll be some static event that happens at an onset and then something off the offset that we should be attending to. And finally, we wanted to look at the types of ongoing information that's transmitted across the sensory system from the auditory to the visual modality. One important aspect of processing any type of auditory visual stimulus is this idea of entrainment. And so within the auditory domain, if you were to listen to something like a helicopter, a rhythmic each time there's that sound, you'll drive auditory neurons at the rate of entrainment. The visual system is sensitive to this type of information as well. If you were to look at a stroboscopic light in a in a haunted house. It's going to drive your visual neurons at the rate of that visual entrainment. And so a natural extension of this is, do auditory neurons, are they entrained by auditory neurons or auditory activity at that frequency of entrainment? To give you a look what this looks like, we presented amplitude modulated stimuli that are going to be modulated at these different frequencies. Try to lower my volume so it's not too loud. So this is going to be an AM sound at 10 hertz. You can hear the rhythmic faster at 20 hertz, and an even faster 40 hertz rhythm. So within the auditory domain, neurons within the auditory system will actually fire at the rate of this neural entrainment. The question is, do visual neurons follow this neural entrainment as well? Did those sounds come through?
As well, you could actually turn it up louder. Thanks.
Oh, okay. Let me try them again. Is that okay?
Yeah, there might be some filtering happening because we actually can't hear the 20 or 40, but we can hear the 10.
Oh, okay, interesting. And so one way we can look at this, it's a measure called intertrial phase clustering. It's just a way to look at the oscillatory phase of neural activity. The specifics of that I'm happy to talk through in the Q&A if people are interested, but effectively we can present individuals, let's say with this 40 hertz amplitude modulated stimulus, and then look within the neural response at 40 hertz oscillations to see if they're entraining to that stimulus. Within the auditory domain, we can see that there's reliable entrainment to this 40 hertz stimulus. Visual domain, there's no entrainment whatsoever. We can observe onset responses, but just no ongoing response to this entrained stimulus. And so this suggests that ongoing auditory dynamics are not sent to the visual system, only these onset and offset potentials. We've done this at many different AM sounds, all the way from 5 hertz, very slow frequencies, up to high frequencies. Auditory system always entrains, the visual system never entrains. And so in general, for the visual system, sounds can modulate largely these auditory onset and offset potentials, specifically for sounds that are presented in the same region of visual space as the neurons within the visual system that care about those regions in space. So spatial and onset temporal information seem to be incredibly important for sounds activating visual cortex, but not the ongoing dynamics of visual modulations. And so looking at the other side of this system, we can look for how visual information actually modulates auditory processing. I think it's a very different type of mechanism that's happening. It's very, it doesn't care so much about the spatial information. It's more about the information that can be extracted from visual dynamics. And so we've started building a model that can account for different types of information related to the visual system. So this video is completely silent. Nothing is wrong with the Zoom audio, but from this video, you can see that he's saying, that's a bad call. But that's not the only thing you can get from this video. You can see him breathe in before he speaks. Every time we see his lip close, we know that that's the boundary of a word, particularly because he's enunciating to try to cue to the ref. And even more broadly, you likely hear a voice while he's speaking. It's not his voice, but it's your estimation of what he sounds. And this is going to be based on statistical priors in the environment. And these basis functions can actually help you hear him better when he speaks, because you have an expectation of what he as an individual specifically sounds like. And so I'll focus on the first and third of these questions today, just for time constraints, but happy to talk about some of the others later on if people are interested with them. So specifically the idea that the visual system can provide high-level extraction of phonemes through lip reading, and that visual articulators like the shape of the mouth can provide relative pitch, and that this can actually be independent of lip reading ability. And so again, we used intracranial recordings with patients with epilepsy to answer these questions, to be able to track neural activity on the fly as individuals are watching these auditory visual movies. And so the first question is, how is the auditory system actually modulated by visual speech? We wanted to look for the different ways in which vision modulates auditory neural processing to then break down which of these functions, mechanisms are actually carrying different types of information. So we presented individuals with spoken movies that followed with a congruent auditory stimulus. The important thing here is before sound onset, you always get a little bit of preparatory visual motion at the onset of a speech stimulus. And so we can look before sound onset, does vision actually change anything about auditory processing? And then we can see how does the auditory system change to this visual stimulus after the sound has begun. First thing that we find within this high gamma response, this is what is this correlate of action potentials, bottom up, early activity into the auditory system, we find two dissociable patterns of responses. First, and importantly, before the sound is ever presented, we get an increase in activity within the auditory system. So purely having this predictive visual stimulus before sound onset, it starts evoking neural responses in this posterior region of the STG, superior temporal gyrus, and early auditory region. To look at an individual electric response, we can see that a congruent visual stimulus, so this is just where the face is present by itself, starts evoking activity, before the sound is ever present. And at other regions, we can see that that visual stimulus actually has a suppression of neural activity, so a dissociable set of responses. In the low frequency domain, these are going to be the top-down responses corresponding to cognitive types of predictions, maybe some feedback from other types of auditory information. We can see dissociable patterns in beta band activity from 13 to 30 hertz, again with modulations beginning before sound onset, so this predictive cue purely in response to the visual stimulus, and a later response within lower frequency theta band, which we think tracks the ongoing temporal dynamics of an auditory stimulus. And so we can see that there are these multiple patterns of interleaved types of neural modulations, and this is just a replication on a couple of different patients in using different stimuli, different tasks. It's a pretty robust response that the auditory system generates action potentials in response to silent visual speech. But the big question is what information is contained within each of these auditory modulations. One of the easiest candidates, or most intuitive candidates, is the idea that it might be high-level phoneme information through lip reading that's extracted and converted into an auditory representation. One of the important recent findings within the last 6 years has been this idea of how, or an understanding of how the auditory system actually processes phonemes by themselves. There aren't individual neurons within the auditory system that correspond to individual phonemes that you hear in the environment. The way we actually hear spoken words just in the auditory modality is actually through a population-coded distributed representation within the auditory system. So these are a number of electrodes within the STG, and it's going to be the spatial pattern, the distribution of activity along this region of auditory cortex that'll correspond to each phoneme that you hear. And there's going to be spectral and temporal components to this as well. And so when you hear different words, you get a different spatial distribution of neuronal activity within the auditory system. So the idea in the model we've been testing is that lip reading may actually refine processing within these same neuronal populations to tune them to be able to elicit a more precise neural representation for the heard auditory stimulus. And so one way we wanted to look at this question of whether or not lip reading is actually evoking spatial patterns of activity within the auditory system was first using functional magnetic resonance imaging with different types of silent spoken or heard videos. And so the stimuli that subjects are watching were either going to be ma-ma, fa-fa, or ka-ka videos, or silence, or heard videos without the corresponding visual images. What we first find is that we can reliably decode the identity of silent speech, not only from the visual system, but also from these auditory regions, so that the spatial distribution of activity within the auditory system is actually predicting the lip-read words that somebody is seeing in front of them. So it's not only the visual system, but also the auditory system that is encoding the spatial representation of a lip-read word. And this is just focusing on those specific regions, showing that within the auditory system, you can classify not only words, but also lip-read words. Within the visual system, obviously it makes sense that the visual lip reading can be classified, but not the sound, because this isn't a bidirectional relationship. We've replicated and expanded this within intracranial recordings in patients with epilepsy as well, showing them different words beginning with either F, B, G, or D. And again, we can find that electrodes within the auditory system can classify not only heard speech, but these lip-read silent words as well. What we get with these intracranial recordings is also the temporal breakdown of these responses, so that we can see that classification accuracy peaks at a relatively similar time point across these different either auditory or visual stimuli. But we don't think that lip reading is the only type of signal that's relayed from the visual system into the auditory modality. At the overview, I highlighted a bunch of other types of components statistical relationships that we think there are between the systems. One of the other important ones is this idea that pitch can be extracted from the visual articulators. And this is going to be due to a statistical relationship between the auditory and the visual systems. And so, as I mentioned, we already know that static lip shapes have statistical relationships with phonemes, and this is just lip reading, the shape associated with specific speech sound. But broader than that, not only the phoneme that's being produced, there are relative pitch signal, pitch information that can be extracted from the shape of these visual articulators as well. And so we wanted to test this idea of whether dynamic lip shapes convey additional information. So as an example, what this looks like, we can take the phonemes we and u. And so these are the spectrograms of the phonemes over time. The symbols we and u are characterized by relatively stable first and third formants, and the more dynamic second formant rises and falls depending on the syllable. If we look at the dynamics of these spectral components relative to the movements of a speaker's lips when they spoke these syllables, we can see that there's a spatial correlation between the width of these lips and the rising and falling of these specific features. And we found that the width and the spectral components were highly correlated, not only with this specific speaker, but with a number of different speakers as well, and across different types of words. So the idea that hood is going to have very narrow width and produce a relatively lower pitch stimulus, all the way up to haid, which is going to be very wide and higher pitch relative to that individual speaker's voice. And then this full gamut will run a high correlation across different lip width and the pitch that corresponds. And so this is the idea that we found that lip width is statistically associated with a pitch of spoken words. And so we want to test whether the auditory system is actually using this statistical information that's present in the environment. And we think that the way that this is actually occurring is due to the oral acoustics of your oral cavity based on the types of relative pitches that are produced. And so the way that we first tested this was a psychophysical paradigm where individuals were just trying to discriminate whether an auditory stimulus was rising or falling. And we varied the amount of noise in the background. So it's a relatively challenging task. And with these auditory stimulus, we either have a rapidly expanding or contracting disc associated with this rising and falling motion. And so we find that there's a consistent increase in sensitivity to the rising and falling auditory stimuli, depending on whether or not these the visual stimuli are expanding or contracting in much the same way that the lips would expand or contract with the we versus you sounds. And we don't find that with any of our different controls. And so second, we want to examine whether this can actually help us understand spoken speech better. And so the way we did this was to try to filter out specific types of auditory information from an ongoing sentence stimulus. And so this is going to be a full sentence. It'll be extremely difficult to hear, but then I'll give you a cue on what the actual words are present in this sentence. It'll be a little bit more clear. So what we did is we limited the temporal information or limited the spectral pitch information. This is the original spectrogram. Temporal degradation is we're smoothing over the temporal domain without altering the actual frequency information contained. And it would sound like this. So very slurred speech, very hard to understand. And then the spectral degradation will sound a little bit more robotic, whereas the temporal information has been preserved. And so what we wanted to understand is if we have lip reading as an input to the auditory system, we know that's going to provide some benefit. A lot of research has shown that the temporal information from a visual stimulus, when the lips actually parse, can help you hear better as well. And so we want to see whether this spectral component can enhance auditory speech perception above and beyond either of these two cues, which we know exists in the literature already. And so to give you an example of what this looks and feels like, this is an example of a spectrally degraded stimulus. I'll turn my volume up. And so it's very hard to make anything out, but you might have the tip of the ear feeling that you're getting close to picking out some of the words. If I add the visual stimulus, it should be a little bit easier.
So, sorry, we can't hear this.
Oh,
I don't know if this is on our end, if there's a complicated AV system that might be filtering it out, or.
Got it. Okay. It's not important. For the spectrally degraded. Oh, sorry. Oh,
people can check the recording later. That
cool.
Should be better.
The spectrally degraded is going to be the stimulus where you have the intact temporal information, but we've filtered out all of the spectral components. So it sounds effectively like a robot. So that's my attempt of filtering out the spectral, effectively robotic speech where the temporal information is preserved. And then we can see what information the visual signal actually recovers. And so if we look at just lip reading information, individuals are trying to pick out what words they heard. Accuracy is low, but not 0% when individuals are presented with the video by itself, and slightly better in the temporally degraded auditory alone condition. So this is the slurred speech example. Adding in vision to this condition, we find significant improvement, and this exceeds any types of probability summation models. So vision is going to help us hear better, even if it's if we already know how well they can lip read this stimulus. In the spectrally degraded condition, accuracy is again quite low in the auditory alone version, and the boost that they receive from the movie is quite large, with the interaction between these two is highly significant, suggesting that there is a strong benefit of the information you can get from spectrally filtered and spectrally recovered speech. So all of this means that multisensory enhancements in speech comprehension are present for not only temporal information, but for spectral information. So we're covering different types of feature, temporal and spectral, as well as lip reading from the types of information available to us. And then the final thing I'll just send on it is that it's not just these lip reading cues, the temporal cues, and even the shape spectral correspondences, as I alluded to, that there is speaker-specific calibration effects that can happen within the auditory visual interactions as well, so that we know what a specific individual should sound like, and we can use those statistical expectations to help us hear them better in the environment. And since the sounds aren't working, I'll just click through these quickly. And we have a lot of ongoing projects looking at these speaker-specific calibrations as independent effects for ways that we process auditory visual signals in the natural environment. Imagine yourself walking into a bar and you're looking for a friend, you know what they sound like, and you see a bunch of people speaking. By knowing the specific statistics of their voice, you can actually target the spatial location of that individual more quickly and be able to hear them better because you know what they sound like. Same if you're on the phone with somebody. You can filter out the noise better by knowing this fundamental frequency of the speaker that you're talking to on the phone.
Ed.
And so in summary, we know that visual signals help speech perception, particularly when the auditory signal is really reliable, a noisy auditory signal, or if somebody has speech perception deficits or auditory deficits that occur with aging. You need these visual cues to actually help you survive and have better speech perception abilities. And so there are a lot of different cues from the visual system that help us hear somebody better, not only lip reading, but temporal cues about where are the boundaries between different words, spectral cues, and these can be relative cues about the width of the mouth relative to the oral resonance of the mouth, or absolute cues about what is the fundamental frequency of that speaker. Because I've heard them 1,000 times, I know the exact oral resonance of that individual's voice. And we can use all of these visual cues, contextual cues, to help enhance robust speech perception abilities. And with that, I'll just give a thanks to collaborators over the years and our funding agencies. Thanks very much.
Thank you for the very interesting talk. Does anyone have any questions for David? So you can yell it out. Actually, I'll let you just come up to the mic and ask directly. If anyone else has questions, they can line up. That one's broken. Yeah, just this one.
Thank you for the talk. Just a quick question. I was surprised that in a talk on how we coordinate multisensory information, that there was no mention of the cerebellum. And given that it has the greatest number of neurons in the entire central nervous system and receives inputs of all sensory modalities, I was wondering whether or not this was because you do not think it's relevant, or whether or not this is a target of ongoing work.
Yeah, for most multisensory researchers, they've focused on either subcortical systems, including the thalamus and then the cortex. The cerebellum has remained largely unexamined in the multisensory domain. It does have inputs, but we don't find that there's a lot of critical information transfer happening within the cerebellum. Subcortical systems are incredibly important for these basic spatially dependent and temporally dependent responses between the systems. And then the cortex is responsive for any other high-level top-down modulated type of multisensory interaction. The cerebellum much less so, at least from research in animals and humans that we've had so far. It's not to say that it's not, we just don't know what the information that's being transmitted there is doing.
Great. Another question? Cool. First of all, very cool talk. I might mess up some of the vocabulary here, but the part of the talk where you were talking about how sound would sort of kickstart the attention of the visual attention, but then a prolonged sound would not sort of continue that attention on the visual side of things. I was wondering how binary is that, and have you or others looked at, for example, if like the pitch changes more continuously, is there some more continuous notion of novelty that is triggering that attention?
Yeah, that's a great question. So pitch, less so. There might be a slight non-continuous relationship with pitch, that lower frequency sounds might have a little bit of an increased modulatory effect within the visual system. The strongest modulating factor is actually the intensity of the sound. So louder sounds evoke a stronger response within visual cortex. And the neat thing is, if you're in a dark environment, you can actually push this further. A startling sound can evoke visual hallucinations in individuals. We think about this as a hypnagogic type of experiences, and we can actually evoke it in about 50% of people. Within sleep deprivation, you induce some mild visual imagery. A startling sound, particularly loud sound, will evoke a flash of light for these individuals, Kluver-form constants of scintillation or a full field visual flash. Most people don't realize this is happening because it happens right before the onset of sleep, and you don't encode memories right before sleep. So in hotels tonight, try to see if that ice maker kicking on actually evokes a flash. And for a fair amount of people, it does, but we just don't register that it's something to pay attention to. But the intensity of the sound is the strongest modulating factor.
Thank you.
Thank you.
Any other questions for David? Great. Well, since we're running short of time, then I'll end it there. Thank you so much for the very interesting talk.
Thank you.
Okay, so next we have a break until 3 p.m. or 3:30 p.m. I'm going to go to the poster session, but it's also a coffee break. So I'll see you all later.
Oh, yeah, yeah. Unmute and then let me try. That's fine, right? Yeah. But then, so the problem is, yeah, when you talk, you have to talk. I guess. So what I can do is I'll just mute it when. Oh, sorry, I'll turn off my sound. No, I know what to do. I know what to do.
Yes, that is a muted. I'm talking in fun. I think so. Is it, does it read when I talk?
Or hear us?
Anybody on Zoom can hear us?
Those are usually.
I know, I know. Yeah, I think they should be able to hear us. Yeah, we are muted.
No big deal. That
Hi.
sounds totally.
I think I'll remember. Hopefully I remember.
Sounds good. They've already heard about my coach.
Yeah,
Yeah, yeah. Okay, cool. I guess I've been sure.
no, it's okay. Okay, okay. Maybe we can get started right now, right? Okay.
Takes a while.
Do I need to send you the slides or can I directly present from my laptop? You can send a slide. That's better. Okay, so is it okay if I send it by 4:30 or so? By 4:30? Yeah, no, 4:30. 4:30, yeah, should be fine.
I don't know. We can start whenever you can, whatever you think. Okay. Okay, so welcome to the last session. So that's a great slide. We have Professor Paul Dominic from Columbia University. So Paul has been working, has already his work. Originally, he was spent some time at Google Research, and also he graduated from MIT in 2017. His research has been recognized by many university awards such as Career Award, Toyota Young Scientist Award, and Amazon Research Award. And also his work has been widely covered in popular media outlets. So, and he has also worked a lot on the connection of vision and autism, such as speech and also audio source separation, and also other work related to robotics. So let's go down. That's a very kind question. Yeah, so I thought I'd talk about some work that you guys have been pretty excited about. It's such a problem we've been wondering about, which is maybe a problem everyone here in the room is when you go to your health over, how do you know that nobody's watching you? You know, there's so much technology now. There's microphones and cameras, and you can make the cameras really small, you know. And how do you know that like the next guest, who's your guest, right? I mean, you're transfer the microphone. You speak in the microphone, it's not a very. Yeah. How do you know that the previous guest in your hotel room doing kind of light? Right, so try to so you know, the third thing was cost, right? Like, is there a way to stop someone from finding and in some ways it's an academic problem. I mean, probably when you go to your find right? But I mean, it's also not an academic problem in some ways. just with everything you hear about, right? As well as there's this new term called bossware, where your bosses are trying to spy on you, right? So, you know, this is an interesting problem. Is there a way to prevent someone from listening to your voice when you don't want them to? One way of solving the problem, you know, is actually just to like turn on the TV really loud, and you know, and play, use it, and that's you know, okay, the noising algorithms, you know, are working pretty well, but they're not that great. Right? So if you just turn on noise and play white noise, that's what basically doing a lot of these systems that automatically listen to what you're saying. But let's face it, that would really make conversation, right? If you're trying to talk to someone else in your room, talk to your friend or your spouse or something, right? That would be really you couldn't actually, you know, very honest conversation with the TV playing a lot of these in that platform.
Carl, sorry,
the first to be thinking about this. There's been you know, a few work actually in the last few years that's been investigated. How do you understand one of the first work on this in the University of Chicago, where they were able to create this whole response app. And the figure from the paper here, where they're wearing this bracelet, which is making the full responding sound that you can hear. You don't hear it, right? But it basically jams the microphone in the parts of it, crafted in such a way that allows the circuit into the microphone go below and so they demonstrate this that actually jamming something below. So yeah, this is one practical way, right? We can build these, you know, we basically establish this privacy. But you know, the downside of this is that if you need to start like spark purposes, they have to walk around with this giant braid.
It's not complex, right?
So it's not effective if you can go home and get started. But it's also possible to defend against this just by building better hardware, right? Once you know about this type of attack, or regular jamming microphones, you know, then microphone design is just design microphone that so this is the question we're thinking about, right? Are there other ways that we can prevent microphones? Fine.
Andrew?
Probably everyone knows about how to sell example. We were thinking about it, for example. Here's my so right, and for example, are this tiny, you know, the very hard to see noise you add to an image and causes a digital classifier.
Oh, wow.
And you know, the field often sees this as like a bug, right? So like a big problem that's why neural nets are the bug that you but we started thinking of them as like a feature actually, right? Like this is actually a good thing because it gives us control. We can use that as an example to control when someone's really listening to us and when someone should not. So this is like a feature. It's actually a feature for privacy. This has also been done in vision. This is a full website you can check out called tvdazzle.com. And it helps you like cut your hair so that facial recognition. So this was these haircuts are designed for jelly. But this tells you, this basically want to create all these spark ratings in the face of your haircut. That basically is an example. So the question we're asking here is, you know, can we do something similar here for speech? Can we rate the way the jam of the neural net operating on And basically, you know, help establish them. So the way we do this is let's assume you know, we have two parties that are in thought, right? And this is important, right? We want to be able to communicate. If two people want to be able to communicate, have not the mistakes that yelling over a radio, right? So there's these two parties, Bob and Al, and they're and unknown to them is that there could be some spy, some road microphone that has no net and trying to speak. And our goal here is to disable that. How can we disable that? Without knowing where it is, where, you know, where it could be, how far away it is. So the setup is, you know, what we're envisioning here is Bob could take out his phone here, and as he talks, his phone speaker could be producing an adversarial example that will be known as and if Bob has his phone, say this you know, and everything lined up perfect, right? Then what the spy can hear is but the very quiet, right? That's the serial number. That will disable the neural net to fight. But it's so quiet, right? The volume on this is so low that Alex will still be able to. Okay. So what's the problem with this though? Why is this hard? I mean, is this just applying kind of what we know about it? For example, we just applying now, taking what we've done, taking now. The challenge here is that basically the exact noise that you want to produce is going to depend on what you're saying, right? The best episode examples in conditioning, they are crafted knowing what you're doing. Right, knows that the dog, here's the noise I want to add, so no longer. So in speech, this is actually very demanding. Environment is very demanding. Because by the time you finish speaking, right, it's too late. Right? There's going to be a delay. Right? By the time Bob finishes speaking here, as an example, we can take traditional conversation. And the phone tries to play it, it's not going to play until the signal itself has changed, right? You're making crafting adversarial examples, crafting that, you can take off self-adversarial examples in your engineering system, apply it, but when you play it, it's going to be so practically you can use this, right? In a streaming scenario, this would not work. So the main idea here is that we can take advantage of these predictive models that are trying to stay ahead, they're trying to predict what's going to happen in the future. And we can use these predictive models in order to overcome the fundamental vacancies here. And basically allow you to camouflage this voice in your real time. Right? And the predictive models are going to be really useful here because we're going to be able to anticipate what is the noise pattern that will be playing in the future, so that no matter what that person is saying about that time, it's going to be able to do okay. So the problem set up here, and this is really the idea, right? The brain idea is you can do these predictive models to focus on the fundamental problem in the world where it's always changing, or signals always changing. And by the time we're able to sense it and do some processing on it and try to take an action in the world, it's too late because the world will change. So the predictive model is basically widening the window of opportunities, right? It gives us more time in order to do this performance. And so this is just the details of how we close this idea here. So we're going to set this up for a first speaking, and our goal is to figure out what is the adversarial example I could play through a speaker, so over the air, right? That will be effective so let's say that XP, right? You get the observed kind of the waveform at XP, and we need to figure out what is the attack we should be playing And X plus delta. So delta is that. We have a neural net here, which we're going to call F data, that's parameterized with F, the parameters that are representing that vector data. That's going to try to use with the class X AC plus delta. That when they're summed together, right, and you combine what's actually being spoken, what we predict the attack is going to be. This should basically disable an APR, blocking APR system from correctly transcribing we can write down a lot of functions here. Rather than so this is just a lot of functions here. You pick your favorite loss function for APR basically comparing what the predicted speech is versus what the current speech is over something in the data set. And rather than minimizing this, we're trying to practice, right, with maximization. Right? So it's up as high as we possibly can. We want to make this the most, we want to train the most difficult noise that can break the data set. And so basically the way that we model what the prediction is from the our system is that the composition of the ASR as well as what our predictive attack is operating on the path, plus what the actual signal is going to be in the future. Right? So this is where the key equation is, right? This is the second line here, right? You're combining what's actually happening is unknown to you, right? And then in real situations, you don't know what actually delta is, right? So you're going to predict something that when it does get combined with that, is going to stable the full G model. And you can just apply kind of a standard sort of tweak on this that you don't want this to happen to you, right? We want this to be better than turning on the apply. Right? So we can put something down. So yeah, I mean, this is the basic idea here is you can train this whole system up on this speech, right? You take a standard data set you have for ASR and train and stuff, training up this certain model, producing these attacks. I think what's actually kind of interesting about this is, I mean, we all know it's really hard with we don't actually know what a person's going to say. There's a lot of uncertainty in what's going to happen. And this approach doesn't need to predict what a person's going to say, right? It doesn't know the exact words. You just have to adapt to something in what the speaker's kind of characteristics of the speaker's voice. You know, some structure of what words, there's say the, and you probably expect a noun to be certain. And so all it has to do is generate a class at sufficient rate for all the variations in the future. We tried this on basically we tried it on a bunch of different scenarios, and it ended up working very, very well. So it's actually much better than turning on the radio, basically. You can just turn on the TV. You can attack ASR systems much better than that, much lower volume. So, you know, the paper has all of the citations at the bottom here. It was published at I shared this year. The paper has all of the full table numbers. The key highlights here are basically the system is constructing the word error rate by four times, positive 4x the word error rate. And we tried this in a bunch of scenarios. So it works in both what are called black box and white box settings. White box is when you assume you know what the supply is. Black box is when you don't get to see it. You don't know what the supply is. So it works in both scenarios. It works even when you apply the state-of-the-art system at the field. I mean, it depends itself a little bit, right? But the system still works even when you apply it. So we actually tried to build a practical prototype here. We really wanted to see what this program is, like, how this works in the real world. So we don't quite have an final yet. hopefully that's come from existing. But we actually tried that where we'd actually speak in the room. These are some photos on the left of the Columbia lab. Here is our new office space, and the top picture of our kitchen on the bottom here. And so we went in and we just spoke in those rooms. There's reverberation, there's background noise, there's a lot of heat playing, and we just recorded there. And we tried to emit the sound right in the jam. And it's our and it worked. So there's three columns here. There's ASR with no attack, with white noise, and with bar attack. So ASR with no attack is basically what a open state art open source system ASR would do on the speech. Green means it got the letter right, red means it got it wrong. The ASR is pretty good, right? It works on the phone, right? If you just play white noise at kind of an approximate like same volume level as the hard attack, okay, it gets, it actually doesn't get yeah, it kind of gets a little worse, but not really. I think it actually cleans up on mistake. And you play white noise, some of the letters actually clean through. So when you raise this attack, right, what happens? It gets what you want to raise, right? If you really block me, there's our system in real time. You should notice that it starts green, right? The hard attack, it all starts green when it's red. That's because you're start predicting, like anticipating out in the future. So it's sort of, that requires a warm up phase. So you have to speak a little bit, but it's always there's going to be some warm up because that's okay, so I tried to play with some sound here. Hopefully the person will be it's not fully, you can still hear it. You can still hear the tap. But it's like a whisper. It's sort of imagine like talking is a whisper in the back. And we're thinking about this like should you actually be able to have basically possible to have over the air attack that you just can't hear it at all. And I'm not sure it's actually possible. We need to be able to attack microphones even that are far away, right? And even if it's kind of, you feel the speaker in the room next door, right? That sound is too traveling. So if we play too low of a volume attack, it's not going to go to double, right? So, okay, let me shut up and then we try to play it. So you're going to hear here is, what you're going to hear is basically the voice. In the whisper kind of sounds like that's not attack, started. And the transcript is in here as well, so the color and the face are right. Okay, at the end, the reverberation is not part of the effect. But you heard the whisper at the very end, right? That's basically what so yes, this caused a huge increase in words. We have another example, but maybe it's not worth it. Okay, so why don't we try muting this? Okay, we're back on. Okay, good. Okay, yeah, so we now have this model in a bunch of different ways. So we're kind of what does it do? We better understand like attack. I mean, I think we said this is a really important problem, right? I mean, we sort of like a lot of this division of really cool technology that really change our world. So we often forget about like the right part of it. So things like maybe we build like AI for privacy. So what this plot here is showing is each red dot is a word, right? And the vertical axis is showing accuracy after the attack, and the horizontal is showing accuracy before the attack. So basically, because we see everything below the diagonal, that means our attack is effective, right? When it drops down below the diagonal, that's saying that the attack is effective. The size of the circle is basically showing the frequency of that word, how often that word appears in the name. So the really big circle at the top, I think, is the word the. Right? That's like the most common word. And what you should notice is that's not dropping. Basically, that word is really hard to stop. That's the word that's going to be passing through. Right? We're not going to be able to start to that. But that's actually okay, right? That word doesn't really much information content, right? That is very little. Basically, the most frequent words carry the most carry the least attention. So what you do see is that the words that are less frequent with it, that are represented by many more smaller dots, do have a significant drop in accuracy. And those are the most important words, right? Those are the words that things like names or patients or kinds of things that you actually do want to hide from this spot. Yeah, so here's just more ways of analyzing this data here. On the left is showing basically each dot is still a word, showing the word count versus the change in accuracy. So I can see a negative correlation showing the best the linear, or there's a lot of augmented scale. So there's a lot of augmented scale essentially. You see this square trend, right? The more common the word is, the less impact our words. What we also see is about the word length here. So on the right side is showing basically the word length versus the change in accuracy. And here what you see is that the longer the word, the bigger the change in accuracy. It's kind of makes sense because the longer words have more control structure to do with it. Right? If I'm saying the word remember, right? It's easier to start saying remember. It's easier to predict like what's going to happen. So that our attack is actually much more effective on the one word. Which again, the way our language works, the frequent words are often distorted, right? So this is all physics. If you're curious as to what words you should be saying, what words you should not be saying, this is visualizing those words and what the accuracy is not. So the safest word here is safest word on this series, remember. So that before the attack is getting old, the ASR is almost 100% is working to remember. After the attack is almost 0. Right? That's the largest change. I say something about that. The worst words to be saying are says, there's, strong, and sick. Okay, so I mean, I think the take home point here. This is really just a proof of concept. So what I'm hoping that this work does is that motivates more work in this intersection of using machine learning distributed audio privacy. I think reception systems are now ubiquitous, they're everywhere. I mean, not only microphones and cameras, but to include all your phones and watches. So it's like the time is now to investigate what is that role of privacy. And these are some of the hottest fields we designers. AI, there's privacy. So a lot of those methods have been developed independently from each other. I don't think they're actually compatible. So I think it's going to be really, really interesting. Like when you get to restate things in the field, actually compatible with privacy. And lastly, I mean, these predictive models really I think that overcoming some of the ways, right? You know, our world is dynamic. You know, my takeaway point here is we live in a dynamic world and things are changing. The certain models they do that. So project website, you can download kind of the code today. It's not quite like it's app yet, but you can basically run the Cypress model on here. And a little bit of type C tonight. Actually, if you don't want to download that code, they just want to turn on the CCD. I want to quickly advertise another work representing that CCDR about trying to pair music and video together. This is work recommended by a PhD student in your DP back here, where I was mentioning that the Adobe. And it says new 24 miles does really well at trying to associate music video. So here's an example of a system where it just where it just the music is played and it's playing the video that matches it. Right. So, feel free to check it out. Thanks so much.
Next, I'll leave the races for taking questions from the audience.
So, from what I understood, your model is this is the way forward. But if you say to predict the future, to know what the person is going to say, looks like it also has some kind of non-language model, learning with it to predict what's most likely going to be said. That's how also what you start doing the experimentation, or you design your model in a way to also learn model language model.
Yeah, probably pretty more. Really perfect that. It is pretty hard to do what the next word actually say. Right? So one of the things is that you're going to have to take the word and think in fact it is that word. That's really hard. You have to get the word right all the time. So I think it's interesting in hard to be more linear and that plays all the uncertainty about what's the next word that's going to be said. Even half that will work for the distribution of words that we said, not use that word. So it's a recommendation.
I wanted to clarify when you said you had the white box. Does that mean that your method knew which algorithm is being used to translate the other?
Yeah, I would say that this is using technical, but we try to do both ways. One way is we don't know what we don't know what the spot is using or not using. We also try it in ways where we know the
Does that change significantly the output of your system?
Yeah, there's a meaning for it, but kind of the results of comparison are all.
I understood that you correctly attack this not technologically content, so it's based on the content of the speech, correct?
Yeah, thanks for that. It depends on what the person said. If we do like a word change, and we the formal waveform, there's already characteristics of it.
So in that case, like something which I had in mind when we very the talk, part of speed out of the fear of the spy, now giving the code the potential of collecting the data. It needs the data to know what you're saying or then generate it.
Yeah, you gotta trust them. You
you mentioned that the recent words are very hard to kind of avail one more.
Is ASR model being one of the current models or working models? Do you think that it's a challenge for actually, the rare work is made up out of very working?
So I think like I think my map was my right there. What do you guys mean by that?
Oh yeah, so question is that printing words are very hard to detect, right? And rare words are easier to detect. Now ASR models are character-based models or working models. So and the working right, the rare work can be made up out of very different work pieces. Right? Do you think that is a challenge for the algorithm, or do you feel that kind of feasibility?
So we compare both character level and word level. So I guess I don't remember the relevant. I have to remember, but we basically saw this word working both.
Any other questions? Not necessarily.
Let's we have here is
Rohan, hey, the Zoom screen is not shared actually. Not yet. I mean, we can hear you guys, but we can't see the screen.
Okay, this is we should make the recording. Okay, that's it. So that's will be a series of light pixel and I'm going to hear how serial numbers and like see how they work in the here the rest of numbers and another. So the first paper is one talk and it's taking the use that
and first I would like to thank the organizers for having lecture on digital and commodity paper. Okay, so here I'm going to tell you about my project and some generation given difficulties. We'll start with a few generative examples for you.
Hey, Rohan, can't see the Zoom screen.
Let's see how the model works. First, we train algorithm that will division data for into a small division feature representation. This feature representation is one type with important vectors that are trained alongside. Then we can assemble the one vector representation into a different practice schedule. For this, we divide it into way or VPN. Once the bottom corner and the whole vectors are trained, we train the transformer corner with according all the roles condition on the visual feature. During this now, we take the sequence of sample code and reduce the decoder from the output encoder to get the struct in the wall structure. And this structure can be encoded into a waveform using an inverse structure projection form, or again based for orders such as million, which we use. Another difficulty is in the way how we evaluate visual effects sound generation model. If for fidelity relation we special exception distance, for a measure of how relevant is the sample, we need some more info. Specifically, we are going to compare distributions for the ground truth and the generated sample. This distribution are run by the subclass part, which from slash on which is on the step before. This distribution is measured by high levels. Here we're going to compare our results to the state of the output. Well, this is just one example, and all these two out are being displayed in front of you. In addition, we can compare the models quantitatively. Other models also consider baseline by much market, which was fidelity and generation speed. Notice that our model is trained with all classes at the same time and has fewer parameters in total, while being on in terms of relevance. If you found our logic system, feel free to logic outline interactive logic page, BBC paper implementation. The video is extensive here with implementation details, some limitation of our work, and some results. We also have a good development which will help you start something for customer here. We invite you to try it because it's very simple. We also have a new audio program where we show how a 30-second audio can be lost in press. It will just 18 10-bit integers. If you would like to view more of our work, check out our blog that has training series and various different models. Well, anyway, thanks for coming on. Enjoy this workshop and hope you will have a great day.
So our next speaker is audio videos teacher, arranging audio videos happening by
you can see you. I
Hey, excuse me, the Zoom screen is not shared actually.
In this work, we present a generic method for generating full facial 3D animation from speech. With this method, we can animate identities just given their template mesh.
I don't know that I'm a good cook. I enjoy cooking, and so I guess I'll just say that.
Oh, the other one is like Overboard.
I got it turns
that
like
is a movie
red,
that I watched
and
a
so
lot. Oh, the other one is like Overboard. That is a movie that I watched a lot.
An hour on trivia, and then I was like, an hour on trivia, and then I was like,
work for big businesses, they've got no interest in representing the people, so I thought, right.
Bin Blue at C3 soon.
Work for big businesses, they've got no
I have a question regarding how to annotate the. So for example, some annotation may have bias on video or audio questions. So how do you deal with this issue?
Oh, that's a very good question. Actually, I can actually have all video sets and audio, and for each video we have like different containers, and we like we will first insert the topic by proper explanation, and then we will like form the markup. We do only that we can audio so that is we get that the five, but indeed there's potential like different stuff from antennas. There like potentially small life, we are making sufficiently, you everything has a feature. You have the entire power and more feedback. Recording in progress. Any other?
We super has come out and we got all for the non specific, which doesn't get pretty something, but obviously data. So we believe getting it out, we're going to be wrong. I mean, it can be noisy data, but then your prior model is on the generation. You want like 8 each to identify.
Okay, cool. Yeah, so the second time we move on to the next batch of papers. So the first paper is the Brave protocol, and we're pull out the size 3 in the first top. The first one is nervous hierarchical from model association for both gestures and
Hello everyone, I'm Xian Liu from the Chinese University of Hong Kong. I will be introducing our paper, Learning Hierarchical Cross-Modal Association for Code Speech Gesture Generation in CVPR 2022. When communicating with others, we spontaneously make code speech gestures to equip the virtual avatars with speech gestures to equip the virtual avatars with such gestures. We should find their multi-level connections. Second, the dynamic patterns of different body parts are not the same, such as the flexible fingers and relatively still upper arms. Instead of generating the whole skeleton simultaneously, we should treat each part differently.
That's weird. Yeah, maybe just skip this one.
Motivated by this, we propose a novel framework, hierarchical audio to gesture. It contains 2 modules.
I don't know if it's going
The hierarchical audio learner is used.
originally there should be audio.
Okay, so the next paper we're going to hear about is cross-modal perceptionist. Can face geometry be gleaned from voices?
Do you want to use your Mac? Can I use my computer? Sure, you can use, or you can just join Zoom. Did you go to Zoom?
Yeah. Do you have the? You don't have this. Yeah, you can just join Zoom like I did. You can just place.
And from my screen. Disable. Oh, I disabled. Yeah. Okay, no problem. Yeah, hi everyone. I'm Chong Yu, and I'm presenting my work for cross-modal perceptionist and can this geometry be gleaned from voices. So this work, have you ever that when a non-speaker starts up, so you don't, even though or haven't heard yet, you might be able to approximate, imagine what the person looks like, or after you the person think the one's voice actually matches or it doesn't matches appears perfectly. So I think this is a long-standing problem in human perception. To what extent the voice can change human face shape, and our work aims to analyze the correlations between the two human perception modalities. And the previous research has explored 2D representation of basically the images here. They use encode decoder structures or generative serial networks and study whether they can reconstruct the face images from the speech. And however, their image representation inherently suffer from some potential irrelevant factors. So you can see there are a lot of the hairs, backgrounds, or spheres that is generated that is obviously irrelevant to the one's voices, and also, and prior methods show that the latest, and there are some other controversial factors such as ethnicity. So from previous work in their TSME map, they didn't show the clear cluster for different ethnicity different voices. So here from another work is from the cognitive science support that in the recent cognitive science support, they show that the low-level auditorial analysis can affect visual analysis here. So that possibly means that when the person hears speech, then they can approximately imagine what the person look like. And and this is another structure map for the human core. So that is densely connected to head. So that means when the core vibrates, the vibration will pass through the whole face structure. And the latent correlation might exist between these two modalities here. And we try to do a more elegant way in the 3D that seems to leave out some of the irrelevant factors such as background, hair models, and or textures here. And the more direct way is to build a supervised learning study here. And we pass a speech input here and learn the 3D element parameter. That is 3D multiple model parameters here. And the 3D element parameter that can reconstruct the 3D face mesh shape. So the difficulty here is how to get pair data. there's no public data set for the pairs speech and the 3D face shape data sets. So we try to do that by getting an off-the-shelf landmark detector and apply that on the images here. So after that, we get the one's facial landmark that is registration of faces, and we can use a 3D image fitting by optimization to fit the mesh into the landmarks here. So by joining this way, we can construct a data set VoxyLab 3D, since we use the VoxyLab, the voice from VoxyLab and their associated images, and we can reconstruct the 3D face shape from the images here. And another way is we try to use a supervised model that a supervised learning model that we use an latent image. We use a latent image as the we use a latent image as the latent representation here that bridge the 2D and 3D that bridge both the 2D and the 2D to 3D representation here. And the lower part is basically GAN-based loss that tries to synthesize face images here. And the upper part is 2D to 3D representation that try to learn from pre-trained models. And here, we try to examine the first examination is that is there a possible task. So this is the result from the supervised learning that directly fit the fit from both to the 3D element parameters here. Here we try to argue that this is an intuitive and reasonable result that because of voices are inherently very vague information for information to hit the 3D face geometry. So it matches our intuition that we can approximately imagine how a person look like, what a person look like, but we couldn't imagine the details about bumps or detailed wrinkles on these faces. So we show these 4 types can be reconstructed or can be shown in the 3D face meshes here. And these are the collection of results from supervised learning. And since our supervised learning results can contain both of the latent image representation and the 3D face overlay on the latent images here. So sorry, there's some delays here. So here next I show this is the coherency test that we use the neighboring voice features to reconstruct their 3D faces, and they are coherent. And this is a result from the supervised learning. Okay. And next are some comparison with the baseline method. We built the baseline method with directly concatenating the pre-trained model for voice to face and the face to and the image to 3D model. In this direct concatenation without joint training, we find that they usually predict the more monotonous face shape. But with our joint training of the voice and the 3D face geometry, we can reconstruct more accurate face shape based on their face types here. And for the analysis or improvement, we find that the voice information can improve most of the ear-to-ear ratio. That is basically the face width or head width. So that's possibly the major improvement, or the voice can hear about the face width size. And we also conduct subjective tests that we ensure the available results than the baseline methods here. Yeah, so the take-away message is simple that it's possible to reconstruct from one's facial structure from voices, and such correlation may exist. But there's much more implicit or subtle factors that may exist, such as when one smokes or when one drunk. After drinking, their voice can be changed a little bit. But here we target at a more normal way that when people talk or people give a interview, and they should speak in their normal way. So we couldn't, but we didn't leave out such potential factors that underline this analysis. Yeah, and please for more details, please check our project page and data. And thank you so much. Okay, thank you so much.
Okay, so the next paper we're going to hear about is sound and video representation learning with multiple pre-training tasks. And Arun is going to present it. Can you just share screen? Yeah. Yeah, you can mute yourself, like if you try on mute. Okay. Okay. Yeah. Or I can.
Okay. I am Arun. Oh, I see. I see. So this is a work during my PhD at ETH. So currently I'm working as a postdoc under Deva in Carnegie Mellon University. So coming straight to the problem, like so the goal of self-supervised learning is to learn from a large collection of data and to learn it from itself. For example, like global contrastive learning, which tries to learn at image level features, while dense contrastive learning that tries to learn at a very dense level. So we can see its advantages and disadvantages. Like, so when it comes to the global level learning for global contrastive learning, it performs high at for image classification accuracy, while when we have the dense contrastive learning, it performs good at dense prediction level task like object detection task. In our work, we focus on integrating like multiple self-supervised learning approach so that we get like good performance in diverse set of tasks. So let us come to like single self-supervised learning at different. Okay. Okay. Am I audible now better? Yes. Oh, thank you. So let's come to the single self-supervised learning for the task of in binaural sounds data. So here's the data set like we try to use which has like 360-degree video and 4 binaural phones, pairs of binaural phones. So let us take the first task as spatial alignment task. So here we try to learn the spatial features of sound. So we frame this task as like find the angular difference between the binaural sounds and the rotated video. So, and here we use just the contrast cross entropy loss to find the angle. And second task, it comes to the temporal alignment. So here we try to learn the synchronization between the video and audio. So in the video, it's generally taken in the external environment scenario. So we use like we make an assumption that sounds and the motion of objects are closely correlated. So we try to align the motion flow and the audio. Third, the task comes to estimating the temporal gap between randomly picked sound segments from a long video audio. So these are the 3 tasks for a binaural sound, single self-supervised task. When it comes to image, I showed in the motivation itself, the global contrastive learning and the dense contrastive learning. So here is the overall overall picture of our work. So we try to integrate like multiple self-supervised learning tasks, and we try to propose multi-SSL. And once we pre-train this multi-SSL, then we estimate the performance in diverse set of downstreaming tasks. Okay, so the different multi-SSL approaches we use as like first one is a name method, where we just train each of the encoder tasks separately and then concatenate all those features. We freeze that and then we attach the corresponding decoder for the each downstreaming task. Then it comes to the multitasking setting, where we have a single encoder and we have task specific heads for each of the n
tasks, and then we train all of them together. Once we have trained, we attach the decoder. And the third one is the incremental learning. We have a base encoder, then we incrementally learn each of the tasks. And once finally all tasks are learned, we use the frozen encoder and attach the decoder for the downstreaming task. So let us come to the result. Like single SSL task, we can see that each of the tasks performs good for different downstreaming tasks. So downstreaming tasks are semantic prediction, spatial sound supersession, and video retrieval. Probably I can explain more in detail during my poster session. Coming to the, so here is the result for the multi-SSL. So the main conclusion here we can see is that the multi-SSL performs better than single SSL ones. And sometimes it performs like as good as the supervised model as well. So here we show the results for 3 different tasks, and we have all different combinations as well and ablation study in the main paper. And these are the results for the images, both the single supervised and the multi SSL. And here also we see the similar performance. And here also multi SSL performs better than single one, and also the supervised counterparts. Okay, so the main take-home message is that multi-SSL performs better than single SSL, and sometimes even as good as supervised counterparts, which we see in both of the datasets, like OpenAudio dataset and the ImageNet dataset. And incremental learning was the one that performs good among all the 3 methods. So these are the, okay, that's all I had for today. Thank you. Okay, thank you. So the final speaker for this session is Sagnik. Sagnik is going to present the paper Active Audio View Separation of Dynamic Sound Sources. So you need to use my this one. Is this okay? And this one. Maybe just do this one. Sure. Can we go to the present to the yeah. Let's just go to slideshow. Present. Yeah. Can you hear me? Hi, I am Sagnik Majumdar, and today I'm going to talk about our paper Active Audio Visual Separation of Dynamic Sound Sources, done in collaboration with Ziad Palhala and Kristen Grauman.
I think this is the, I think it's, can you just share the other desktop? Sometimes, yeah, can you do that one? Yeah, looks good.
Yeah, so audio source separation involves separating a mixed set of sounds into one or more components of interest. This is also called the cocktail party problem, and we as humans try to solve it all the time. In this example, man is in a noisy environment, but he's trying to just listen to a speech of interest. While most current separation models are passive, models are passive in that they assume access to pre-recorded videos for separation. In active audiovisual source separation, the idea is to let audio and vision guide an active embodied agent's motion to better separate the latent sound playing at a target source. For instance, in this cartoon, the man strains his neck to better listen to a sound of interest. Such an active listening agent could be relevant to augmented reality and mobile robot applications, where a user or robot needs to understand a sound source of interest in a busy environment. In this work, we tackle an active separation setting where all sound sources are dynamic, or in other words, time varying in nature. In this example, there are 3 sound sources, where one is the target source of interest, which is denoted by SG, and the other 2 are distractors denoted by SD. The agent needs to move actively while receiving egocentric views and mixed binaural audio from the environment, and separate the latent, or in other words, monaural audio playing at the target at every step of its motion. Move to here propose the task of active audiovisual separation with static sources, where the monaural audio playing at all sources is periodic, and the agent needs to return an estimate of the periodic target at the end of its motion. However, in our new task, all sources are dynamic, which means that not only does the agent hear a new mixture at every step, but it hears every segment of the dynamic target only once in its motion as part of the binaural mixture. To successfully solve the task, the agent needs to separate the complete target waveform. This makes our task both more realistic and challenging. Here we show an example trajectory of our agent from this new task. Not only does our agent rely on vision and audio to find spots in the environment whose local geometry helps with the separation, it also makes use of the acoustic and semantic similarities in the dynamic audio for improving estimates of past target segments, in addition to producing high quality estimate of the most recent target segment. For this example, the predicted monaural is:
The time of our meeting drew nigh. Ralph called on me first, the most common question, without asking first, during this time, to Miss Reed. I had a great respect and affection for her, and had some reason to believe.
Where the ground truth monaural is:
The time of our meeting drew nigh. Ralph called on me first, the most common question, without asking first, during this time, to Miss Reed. I had a great respect and affection for her, and had some reason to believe.
We next show how our model design helps in tackling the challenges of this more realistic and challenging active separation task. Our model is designed as follows. It first uses a passive audio separator, which takes in the mixed audio as input, and along with the target audio category that is to be separated, and predicts the monaural spectrogram at every time step. Next, we use a transform memory to kind of aggregate these predicted audio from the current time step and also from the past time steps to make an improved prediction. In addition to that, we have a multi-step prediction mechanism in the transform memory, which helps in improving the audio estimates from the past time steps. Next, we take the current predicted monaural audio and the current predicted binaural audio along with the egocentric view of the agent and feed it to a policy network, which is an RL policy, and we predict the action that the agent needs to take at the current time step. We train these 2 modules in a cyclic fashion using supervised learning for the audio separator and PPO for the PPO, which is an RL algorithm for the active policy. We use a dynamic separation reward, which is a dense reward for training the active policy. Here is our experimental setup. So our episode is specified as follows. We have k different dynamic monaural sources of different categories, and among them one is the target. Along with that, we also specify the target audio type and the time budget for the agent. Our action space consists of the move forward, turn left, and turn right actions. And for running our experiments, we use the 3D Matterport 3D dataset along with the SoundSpaces audiovisual simulation platform. We compare against different kinds of models. A few of them are just stand-in, like heuristical models, which just stand in place and just rotate, or like just hold the initial pose and try to separate. A few others just try to remain close to the target and survey the area. And the most important model that we compare against is the previous state of the art for static source separation, which is the move to here model. We see that on both the heard and unheard sound settings, our model is able to outperform both the heuristical agents and the state-of-the-art move to here model by a large margin. In addition to that, our model is able to improve past estimates through time using the multi-step prediction. Yeah, this is like another result that we see. Yeah, so for more questions, you can check out the project page or reach out to us using the email. Thank you.
Okay, let's thank this group of papers and thank all invited paper talks. So I think for the sake of time, please reach out to them for any questions, and Andrew is going to invite introduce the next speaker.
Great, thanks. So the last
Hi, everybody. Hi, everybody. My name is Hilde Kühne. I'm professor at the Goethe University Frankfurt and affiliate professor at MIT IBM Watson AI Lab. And today I want to talk a bit about multimodal learning for video understanding. To get started, let's actually first think a bit about what video things that are technically dealing more with image-related problems like semantic segmentation, object detection, pose detection. We could imagine an intermediate range where people want to do, for example, tracking on objects or on pose, representation learning, multi-object tracking, action classification, and so on. And then on the far end of the spectrum, we would have high-level temporal tasks such as temporal action detection, spatial temporal action detection, temporal action segmentation, and things like activity understanding, reasoning, and other problems. And giving the spectrum, you could imagine that what's kind of like differentiating those things is the number of frames that need to be considered for each task. So on one side, we are more on image-based kind of like recognition side, where we can actually deal with many problems by just annotating enough data. Versus when we are on the other side of the spectrum, where we have long-range temporal relations to consider, it might get a bit tricky because here we have a lot more variation that we need to capture. And in fact, we have much less data and as well much less annotations, just because long-range temporal video data is still kind of like tricky to get. And annotations are also very hard to acquire and very cost-intensive, obviously. So with this kind of like problem setting, if we want to scale up, especially here on the further end of kind of like temporal analysis of videos, we need to kind of like think a bit out of the box. And obviously we cannot handle this with annotations, so we need to get away from annotations. And one way to get away from annotations, and this is what I want to talk about for the rest of the workshop, is actually zero-shot learning. And in the technical sense, zero-shot learning means problem setup in machining, where you assume that at test time, you observe samples from classes that you have not seen during training. And just to be 100% clear, this is technically not true for the setting that we have here. Because technically we just pull from a large amount of data, but we actually did a bit of analysis, and in most cases samples from the classes that we are looking at during testing are to some extent available in the training data, and therefore I want to propose a bit of a relaxed definition, at least for the next 25 minutes, which means that when I talk about multimodal zero-shot learning, I mainly mean that we want to classify data without having trained on respective test data sets. And technically, the long-term goal is that we mainly want to allow for classification without the need for annotation. So as long as those two kind of like are fixed, we should be fine. And just to give you an idea of the setup that I'm dealing with, or that we are usually dealing with, the idea is that we train on a large number of video data that come with audio, video, and text, for example, like how to 100 million data set, and then test on respective downstream data sets like UCOOP2, MSR, VTT, mining YouTube, and Crosstask, but without fine-tuning on this data. So we really just use how to 100 million trained model and see how well we do on those unknown data sets or unseen data sets. The way we do this in general is that technically all we want to do is we want to learn an embedding space. And we want this embedding space to have certain properties. First, obviously, we want to be able to project different modalities, like, for example, text and vision, into this joint embedding space so that they all live in one embedding space. But obviously, we don't want to do this just at random, but we want to do it in a way that the things that are semantically related, like, for example, text describing marinating chicken and respective visual representations or audio representations, are close together in our embedding space, and the things that have nothing to do with each other are technically far apart. And the reason we want to do this is because if we have such an embedding space, we can do pretty cool stuff. So first we can do zero-shot retrieval because we can just project, for example, a text query into our embedding space and then just check for the closest visual representations. But related to this task, we can also kind of like reframe it a bit and do zero-shot classification. And in this case, we just assume that we have a semantically meaningful class label, which is at the end of the day just text that we can project into the embedding space, and then, for example, find the video that's closest by. And when we can do zero-shot classification, then technically we can also do zero-shot temporal detection and segmentation, because this just means that we need to play this game for every frame or for every segment of the video, and then we kind of like get kind of like a continual representation that we can use to detect or segment actions. The way how it works, and I'm pretty sure this has been shown in this workshop several times, so I try to keep it short. We mainly do multimodal contrastive learning, which means we assume that we have pairwise features from different modalities, for example, text and video, and we mainly want to project them close to each other in embedding space if they come from the same source. So meaning they should kind of like capture same content. And if they are kind of like from different sources, we want them to be further apart. And this works for vision, sound, text, technically any matching modality. Now to the interesting question, how is this different from standard self-supervised learning? Because technically the contrastive learning pipeline is pretty much the same. And I want to spend 2 minutes to actually think about that, because I think it's worth to understand the difference here. In self-supervised learning, obviously, you probably all know, the idea is that you only have a single modality like an image, and you augment it in 2 different ways. And then you want to kind of like find similar pairs. But the idea of all this game is that you want to train a backbone on large scale data. So at the end of the day, you want to do representation learning. And for this representation learning, obviously, when you look at the architecture, what you usually do is you mainly focus on the backbone, and the projection heads are just thrown away after training. And the evaluation methods in this case is take the backbone and either fine-tune it on annotated data or do linear probing for classification. But anyway, just take the backbone and do something with it. Now, multimodal learning technically is a bit different. First, obviously, with respect to the fact that we are now talking not about a single modality, but 2 modalities or more. And the goal of multimodal learning is technically same as self-supervised. You can do pre-training and representation learning. But what you can also now do is actually zero-shot retrieval. And the interesting thing is when you are after zero-shot retrieval, then the projection heads are actually the most relevant part of your architecture, because those are the ones that will be used for the embedding, or for kind of like learning this embedding space. And therefore, in this case, another evaluation can actually focus on retrieval and zero-shot tasks. And this is exactly what we are after. So while self-supervised learning will mainly focus on things that optimize this part of the architecture, in our case, we even kind of like usually fix the backbones for better comparability and try to find ways to learn better projections that actually give us better zero-shot and retrieval accuracy. Having said that, next question is, why do we actually need those zero-shot thing at all? Aren't we good with just learning representations? And the reason why I would like to argue that it's worth looking at those multimodal embedding spaces, especially when you're kind of like interested in video understanding, is actually that practically real-world video understanding can be a very difficult task. And just to make a point, we have very great data sets and action recognition, and we have very good architectures that perform very good on even large scale data. But the problem is there is still a kind of like a gap towards real world applications. And this kind of like has to do with a set of problems that we have in action classification and video understanding specifically. And those problems is actually that technically actions themselves are not very well defined, which means that the perception of an action or the label that you get from an annotator usually highly depends on many things, like, for example, the duration of the video, the expertise of the annotator, and so on. And this means that usually if you want to create action data sets, your action labels have to be somehow pre-selected or predefined to make sure you get consistent labels. Just being able to learn those multimodal embedding spaces would kind of like allow us to get rid of these predefined labels and to start learning without them. Second problem is actually that actions are highly unconstrained. So while objects, for example, have a very clear physical outline in the real world, actions can be technically anything that you are doing 24/7. So when you're sitting on a couch, your action is sitting. When you're lying in bed and sleeping, your action can be sleeping. And therefore, there is no fixed or complete taxonomy for actions like we have them, for example, for WordNet or ImageNet. And therefore, it's also very hard to come up with a vocabulary that would allow us to capture, for example, your activities 24/7. And embedding spaces might actually be a remedy here, as they kind of like just elevate us from the need of having a vocabulary at all. And last but not least, obviously, we also have the point that we will never have enough annotated data to capture kind of like large real world scale. And therefore, embedding spaces are just kind of like an easy annotation-free alternative that we could use to capture what we want to capture. Okay, I hope I made kind of like a solid case for embedding spaces. Now let's look at how you can actually get there. And the first architecture that we proposed that was published on arXiv in 2020 and then made it to Interspeech 21 is AVL-NET, which is kind of like the vanilla architecture you can think of when you think about multimodal embedding spaces. So it's really just kind of like a visual branch, an audio branch, and a text branch. And the idea is to kind of like generate features that all have the same dimension and take those features from different modalities and project them in a joint space by pulling them close together if they come from the same source and pushing them apart if they are from another source. This is a very fun architecture, and beside text video retrieval, you can do even more funny things, like, for example, audio querying, where you can just give either a spoken description or even just a sound that an object makes, like, for example, sizzling, and you will get kind of like back videos where things are frying. Or you can do video audio querying, where you can have video inputs and you can retrieve audio segments that match those, and so on and so on and so on. But obviously, as it's kind of like a vanilla architecture, it's nice, but we figured out that it has some quirks. And one thing that's kind of like not really going along with our idea of having a joint semantic embedding space is the fact that for this architecture, we are just training pairwise losses. So we are making sure that things from the same modality end up close, things from the same source end up close together, but we can, for example, not make sure that everything that's chicken related will end up in one area and everything that's car related will end up in another area. To actually make sure that we get there, we need to put something on top. And therefore we thought, okay, if we have kind of like pairwise stuff, let's kind of like reorganize the space a bit in a way that we draw things closer together by simply clustering them. And this is the architecture that we proposed at ICCV 21, where we mainly extended the contrastive loss formulation we have seen before by a clustering loss. And just to give you an idea, so the upper part of this architecture is what you have seen before. And the lower part is actually how we make sure we learn real semantic embeddings. And to do this, what we do is we just take kind of like the projected feature and do a mean pooling over all modalities from the same source. So when we have kind of like a batch size of 2000 videos, we will get 2000 triplets, we will get 2000 mean features. We then do actually clustering over those features, and from each, and this means that we get a centroid for each input feature, because each mean will belong to a cluster. And this centroid will actually be the anchor point then for the single modalities. And together with pairwise loss, we will also try to minimize the distance between the single embeddings and the centroid. And by doing that, the hope is that we can actually draw things closer to each other when they, for example, have similar either visual representation or audio or text. And overall, it turns out that this is a very neat idea because we can, for example, visualize in T/S&E plots that with this clustering loss, we get a very nice kind of like clusters over time, or even continuous stripes over time, versus when we don't do clustering, things look a bit more scattered. And we can also kind of like make some assumptions about what we do. And it turns out that the centroid clustering is actually performing better than just swapping label predictions or doing joint pseudo-labeling predictions, which has been proposed before. And the reasoning why we think it's actually better to have kind of like this drawing things towards a centroid than just predicting labels is that by defining the centroid, we get some geometrical anchor that things can really group around. Some other lessons learned is that k-means and sinkhorn clustering technically perform more or less on par. So we went for k-means because it's very easy and neat to integrate, but technically just go with whatever is your preferred choice. And finally, we also showed that the resulting system can be used not only for retrieval and classification, but also for temporal segmentation. And temporal segmentation, for example, can look like that. So we have here some sample from Mining YouTube where we are given a certain number or a certain sequence of actions that we want to retrieve. And then the job is to kind of like align the videos with respect to this action ordering. And you can see this works very well. And this all without ever having seen a single video from Mining YouTube, all just being trained on how to 100 million. So that's pretty cool, but obviously we want to do better. And the way we want to do better is kind of like considering what are the problems that are still left. And technically we have kind of like two things, or we had two things that were bugging us all the time. And one thing is that technically the way our architectures were built was that every modality was considered completely separately till the final projection. So there was no way for modalities to actually interact with each other. And we have tried several things and nothing worked very well. And the next problem we actually had was that inputs for those architectures that I showed you always need to have fixed length. And this is obviously bad because especially vision and sound can come in different lengths. And we were not really able to accommodate that and just kind of like had fixed windows that we sampled over. So meaning we cut off sounds or cut off kind of like videos just more or less randomly. And the good news is along came transformers, and the way we thought we could actually use transformer architectures to help us with those problems is not by just putting kind of like cross-model layer at the end of everything before projection, but actually to kind of like use this attention model to in the lower levels of our architecture to allow features of different modalities as well as themselves to attend each other. And the second thing beyond this kind of like attention idea is that transformers, especially kind of like the idea of tokens, also allows us to process input of any combination and any length. So we gain a lot of flexibility here. And then to kind of like train that and to keep the flexibility, we propose a combinatorial loss function on top of everything to keep everything more or less stable. So to give you kind of like a deeper insight of the architecture that we actually will show at this CVPR. So technically the input is still the same. We have kind of like video, audio, and text, and kind of like extract features. And from the features, we get a set of tokens. And but from then we just say, okay, let's just concatenate the tokens. So the input of our transformer is just kind of like a list of tokens, and we don't give any specific knowledge or information which token comes from which modality. We just say, let the self-attention handle all that. And the idea is that when we kind of like forward the set of tokens, what will actually happen is within the attention, we will have some weights which will kind of like do self-attention within one modality. We will have other set of weights which will do cross-attention and so on. And technically, we just use this attention to learn which features on the lower level are relevant, either for themselves or across different modalities. And after the self-attention block, we actually split them up again, project them, and then actually use combinatorial loss to train our embedding space. And it turns out not only that this works very well, so that we are actually kind of like able to improve state-of-the-art numbers, but what's more interesting is it actually allows us to look a bit under the hood of our systems and to start looking at how modalities interact internally. And when we actually look at which keys and queries interact with each other, we find that text is actually mainly looking at other text samples, so it's mainly doing self-attention. Vision is kind of like attending text features as well as vision features. And audio is a bit out there because audio is also heavily attending text and actually less attending audio or vision features. Last one might be Quark because text is technically the ASR transcription of audio. So those two signals are very close together. So to a certain extent, it makes sense that audio is mainly attending text because text is just kind of like a different flavor of the audio part. But let's say it's very cool to at least get an idea of what's kind of like relevant for which interaction. But we are curious, and we also wanted to go a bit further and understand a bit better what we actually do there when we learn those joint multimodal embedding spaces and what we actually learn at the end of the day. And one way to better understand what's going on under the hood is actually grounding. So referential expression grounding is something that has become trendy in the recent years. And the idea is that you're given kind of like a sentence and you need to localize the respective referential expression, for example, in image. And technically, we take this idea and extend it towards video by looking at spatial temporal grounding for our instructional video data. And spatial temporal grounding mainly means that first on the temporal part, we want to find the temporal boundaries of action steps that are described in our referential expression. And at the same time, we actually want to figure out the bounding boxes in each frame where the temporal, where we actually kind of like temporally labeled that. So it's kind of like a challenging task, but the good news is we were not the only ones who thought that this would be a good idea, because at the same time as we started, or as we actually were finishing our labeling data set, a second data set came up, the UCOOC instruction data set, which also provided bounding boxes for action grounding in instructional videos, but mainly focusing on the spatial part. So not necessarily focusing on the temporal extent, but only spatial. But anyway, a pretty cool data set. And this is actually collaboration between BU and MIT IBM Lab and Brian Russell from Adobe Research, which was published at NeurIMS 2021. And hopefully we will soon in this kind of like sense also release our data set that we annotated on Grounding YouTube, where we technically followed the same idea. We want to do action grounding with referential expressions in instructional videos, with the only difference that we are actually looking for untrimmed spatial temporal grounding. So we provide bounding boxes for a certain period of time and also want you to come up with the right temporal extent of an action and the right spatial extent of an action. Having said that, obviously you can imagine that this is a pretty decent challenge because you actually have to capture two things which are kind of like not necessarily correlated. First, the long temporal range of an action, but also at the same time, the single frame spatial bounding boxes. And it turns out one architecture that we tried, or one flavor that we tried that was actually pretty successful is just have two branches responsible for two different things. One local branch, which is responsible for learning spatial representations, and one global branch, which is actually capturing the start and end frame. So just take those two problems and decouple it. And it turns out that this is a way that's technically kind of like inspired by two systems which are on their own doing either one or the other. But when you combine them, you actually get kind of like best of both worlds. So, and the reasoning why we think we kind of like get best of both worlds is that technically visual information is good at capturing local spatial information, but might not be optimal for capturing, for example, start and end of an action, while audio information is actually good at capturing temporal information because the audio signal is very kind of like precise when you have actions that are tied to certain sounds, like for example, chopping or sizzling and things like that. And then technically text can be used in the middle to glue both of them together. And with that, it actually turns out we can actually even achieve pretty decent accuracy even on such a challenging task. But what we also see is you definitely need to combine those both elements, so you cannot go with one alone. But this is actually a very nice finding. The only question is, why should we actually care about grounding? And just to give you one last idea why we think grounding might actually be a good idea is one thing that we hope we can actually do with multi-model data is start to learn cross-lingual or multilingual representations, especially for low resource languages where not much text is actually available and kind of like many sources are based on video or audio information. And here we hope that multimodal can actually kind of like build a bridge between languages, mainly because sound may kind of like be different, but objects will always look the same in any language. And therefore we hope that multimodal information can actually support multimodal data processing here. Okay. Having said that, let me actually conclude my talk with some reasonings why I think this is really worth it and why I want to spend my time on this topic. And to summarize, the main reason is I actually don't want to have to label any more training data, to be honest. But beyond just me being lazy, I hope that being able to learn this label-free semantic space actually will allow us, so people working in video understanding, to work with really large-scale data beyond annotation large-scale data, and also will kind of like free us a bit from those assumptions that we make when we start labeling data. And with that, I actually hope that this label-free semantic space will allow video understanding to grow a bit beyond the traditional classification setup that we have at the moment. And as we have seen here in the workshop, start to explore new topics and applications. And with that, I really want to thank all the people who worked so hard for those works to come up. The PhD students at MIT, Columbia, UCF, and my own Nina, and as well as our senior researchers, Jim, Sam, David, and Rogerio. And I thank you for listening.
So,
Okay, it's MU, and I'll be joining UW Medicine starting this fall as an assistant professor. This talk is going to be about learning to see by listening. This was work that I've done while as a PhD student at UC San Diego, and some of it as well during my postdoc in Carnegie Mellon. Unfortunately, I'm not going to be able to do this talk in person or in Zoom, as I'm probably right now still in transit going to CVPR. So if you have any questions about the talk, or if you're a student and just want to work in self-supervised learning and multimodal learning, please feel free to reach out to me. I would be happy to chat both in person at the conference or online. So this talk is about audiovisual representation learning. Just to motivate this, I will just give you a few examples, right? So here are just 6 sounds, and can you recognize them? Can you try to imagine what the videos would look like as you're listening to this sound? If you're like me and many other people, you probably were able to at least identify what the sound was like, and you could imagine some scenes where this sound would make sense. So this natural association between audio and video is prevalent. Also, the sounds can be very distinct of each other, which can be very informative of the visual input. Another characteristic is the fact that all these sounds represent what's happening right now. The association between the audio and the visual input is quite immediate. And finally, they are basically everywhere. They are quite abundant, and this association is freely available on any video that you'd be working with. So these examples give you a hint of how we can use audio to learn visual representations. It's by using this natural audio-visual correspondence. During this talk, I'm going to talk about 2 works that really use this audio-visual correspondence at its core. The first one, it will be on how to learn visual representations using robust learning. The second one will be on unsupervised visual sound source localization. Unsupervised learning from audio and video is in fact a long-standing problem in machine learning, with the earliest papers published by Virginia Dessau in 1994. In fact, even at the time, the formulation with which the problem was posed was very similar. The idea was to really learn audio and visual models that could map the inputs to a common representation that is matched in the feature space. Now, for a long time, there was not a lot of progress, but in recent years, with the development of deep learning, this idea surged back, and there has been a variety of different works published in this area using audiovisual correspondence or similar ideas, for example, using temporal synchronization between audio and video, or even spatial alignment or echolocation. Just make this idea clear of how to use audiovisual correspondence. I'm going to just touch on this work, Avid, since it's my own, but a lot of these works kind of use the same type of ideas. Okay, so the goal of this project initially was to just learn high quality audio and video models without the use of human annotations and through the use of audiovisual correspondence. So in this work, I introduced a new procedure where representations are learned by solving two concurrent tasks. For example, from an audio like this one, you can think of a multiple choice task where the network is asked to select what is the correct video. So in this case, the video of the man playing the guitar. Conversely, from a video like this one, the network would be asked to select the corresponding audio clip. To do this, we can train neural network encoders to align the audio and visual representations obtained for corresponding clips, using, for example, the contrastive loss shown here. To minimize this loss, the posterior should be maximized, which means that the video and the audio representations of the same instance should be as close as possible in this shared feature space, while representations of different instances should be as far as possible. Here I'm representing the features in a sphere because in practice they are L2 normalized. Of course, we can train our models to do anything, but the interesting finding is that by learning to match audio and video, the models learn to group similar videos together, even though they were never told to do so. This slide shows the nearest neighbors obtained by a model trained with the loss from before. The first column in each group depicts a random video selected from different categories, also shown there. And the remaining columns show the top 4 retrievals with the closest video representations. As you can see, with these models, can group semantically similar videos effectively, even though they actually look quite different visually. At the time of publication, this work was also outperforming other methods that also rely on audiovisual correspondence for actions like human action recognition. Also, to put these numbers in perspective, we can also compare with fully supervised model that was fully trained on kinetics using human annotations. What we can see is that while supervised learning is still ahead, this gap between supervised and self-supervised is closing. And in datasets like HMDB, the performance is already comparable. I was quite excited about the performance of this method, so I set out to improve upon it. While working on this previous project, I observed that while often correlated, audio and video sometimes are not informative of each other. So see, for example, these two videos.
I can ride my bike with.
As you can see, people sometimes edit their videos, other times they don't, but the video is naturally silent, like the yoga example. In these cases, establishing correspondences between the audio and the video clips is impossible, and forcing these correspondences can be detrimental. So in this next project, I developed a robust learning algorithm to tackle these unreliable correspondences. Now, to understand this procedure, you need to take a step back and understand the training dynamics of audiovisual instance discrimination. Suppose that we have an instance of a baseball game, as shown here. One question that we can ask is, how does the audio affect the video representation? Since we are minimizing this loss, then the answer is given by the partial derivative of the loss with respect to the video representation, which can be written as a weighted sum of all positive and negative audios. For the positive audio, this indicator function here would become 1, which means that the weighted associated with the audio is a positive scalar. This means that the corresponding audio acts as an attraction point for the video representation, which makes sense. More importantly, if this video and the audio representations were to be further apart, then the posterior would be smaller and the attraction force would increase. The opposite happens for negative audios. In this case, the indicator function is 0, which makes the weights associated with these audios to be negative. So the negative audios act as repelling forces for the video representation. And if the negative were to be further apart, then these repelling forces would be smaller. But for negatives that are close together, the repelling force is larger. Again, this makes intuitive sense. So if the models are making larger mistakes, they should just adjust accordingly. However, these updates become problematic when the notion of positive and negatives is not reliable. Let's start with positive pairs. After training an Avid model, I've plotted the histogram of similarity scores between each audio and the corresponding video. The pairs with high similarity tend to be instances where the video and the audio are informative of each other. For example, this case.
Relatively clear skies, maybe.
Since the audio and the video representations are close in the feature space, the influence of this positive pair is rather small. In the top of this table, I'm showing the magnitude of the gradients that are induced by each instance. Here's another example with high similarity. As we get closer to the middle of the distribution, we start to see instances where the correlation is weaker. And for instances at the bottom of this distribution, the audio and the video are uninformative of each other. The problem is that since the audio and the visual features are so far in the feature space, the gradients that they produce are significantly larger in magnitude. I call these instances false positives because due to their large gradients, they dominate training even though their audiovisual correspondences are actually misleading. Now, to see if these examples actually make the models worse, I did an analysis study. I started by artificially injecting faulty positives into a data set by randomly selecting some percentage of the videos and changing the audio to that of a different video. Then I compared two versions of the same model, one that was trained on the noisy data and another that simply ignores the injected faulty positives. And then the models were evaluated on action recognition. As you can see here, as we inject more faulty positives, the performance of the model that uses all the noisy data, the green line, decreases much faster than the model that knows which instances to ignore. This clearly shows that these faulty associations can harm representation learning. Now, of course, in practice, we don't have access, we don't know which instances have weak correspondences, so we have to detect them and effectively reduce their impact. So to do this, I propose an extension of the contrastive learning loss that weighs each instance individually. Ideally, this weight should be 0 if the instances are faulty and 1 if not. Now, to estimate these weights, we can go back to the audiovisual similarity scores that we saw before. Instances with high similarity should remain untouched, that is, with the weight close to 1, since they are likely to be good correspondences, and those with low similarity should be downweighted. This was accomplished by attaching the weights to the cumulative distribution of the similarity scores. This is similar in spirit with works of learning with noisy labels, either by weighting or designing losses that are less affected by outliers. The main technical contribution here is that the realization that once the model is trained by cross-model instance discrimination, that we can use the similarity between the two modalities to identify potential faulty correspondences. So how effective is this procedure? We saw this plot before, showing the performance of the Avid model trained on data with injected faulty positives and the performance of the Oracle method that knew beforehand which instances were faulty. After retraining the weighting strategy on this data, the results look like this. Notice that the weighting strategy even outperforms the oracle, which knows in advance which instances to ignore. The reason is that in practice, large data sets that I use to run these experiments already contain faulty positives, faulty correspondences that were not injected. They were just there all along. And so unlike the oracle, the weighting strategy is also able to detect and mitigate those cases. Next, we also should take a look at the problem of negative pairs. So consider this video of a guy working out with an Olympic bar. In this plot, I'm showing a slightly different histogram than the one that I showed before. Here, this is the histogram of similarities between this specific video and the audio of other random clips, so mostly negatives. Now, suppose that the video lies somewhere in the feature space. The majority of the negatives will be from random instances that have no relation to our video. Their audio representation will be far, and the repelling forces that they generate will be small. On the other hand, negatives that are closer to our video are also more semantically related. In fact, in the limit, you'll find many negatives that are from the exact same action class. We call this faulty negatives since ideally we would like to use them as positives because they are from the same class. And the problem is that because they tend to be closer in feature space, then the repelling forces that they are generating are much larger. And so they have also a disproportionately large influence during training. Once again, I conducted an analysis study similar to the one that we saw before to verify that the presence of these negatives is detrimental. So I trained two versions of the AVID model, the standard procedure that uses faulty negatives and the modified AVID procedure that ignores them. I define here faulty negatives as instances that belong to the same class. The results showed that overwhelmingly, faulty negatives are indeed quite detrimental. Of course, in practice, we don't have class information, so we need to detect these faulty negatives without using these human annotations. To understand how, first note that minimizing this instance discrimination loss, this contrastive loss, is equivalent to minimizing the Kullback-Leibler divergence between the model posterior distribution and the one hot target that flags which one is the positive pair. This one hot target dictates a strict definition of positives and negatives. In other words, corresponding pairs are positives, and thus they have a target value of 1, and all other instances are negatives, and so they have a target value of 0. However, this does not have to be the case. Instead, I generalize this definition of negatives by using a soft target distribution over instances. Ideally, instances that are semantically similar in the original video, such as those that belong to the same class, should have higher target values, and unrelated instances should have target values that are closer to 0. Now, to estimate this soft target distribution, we can go back to the histogram of similarities between instances. As we saw before, these scores can give us a good sense of what instances are related to each other. They can be used to define a target distribution as shown here. Under this definition, instances which tend to be similar to the original video, like the two videos of people working out in the gym, are used as weaker negatives or even as positives if this target distribution is evaluated to something close to 1. Now, looking more closely at the loss function, we see that both the posterior and the target distributions are computed by comparing the base video to the audio of other instances. This means that the target distribution doesn't necessarily contain more information than the posterior of the current model. So as a result, models that are trained under this objective do not improve substantially. Instead, we show that we can leverage other relationships in the data in order to compute a target distribution that is complementary to the posterior. I won't go into much detail on these alternatives, but it was shown experimentally that the last one, cycle consistent prediction, was working better in practice. Now, these are the type of faulty negatives that we can detect with this scoring function. So on the top here, I'm showing examples of base instances, and on the bottom, I'm showing the 3 most likely faulty negatives that were detected. As you can see, in this case, all instances are from a weather forecasting channel, so that they are indeed faulty negatives. They should actually be used as positives instead. Here's another example, and another, and another, and another. We do see some detection failures in some cases, but the detection rate was high enough in order to improve representation learning, which is the end goal of this work. See, for example, the case of the retrieval task for action recognition on UCF. The baseline, which is AVID, achieved 75.2% recall. Previously, we saw that weighted AVID, which was tackling the issue of faulty positives, achieved 77.4%. Contrastive learning with soft targets, which tries to address the problem of faulty negatives, achieves 78.1%. And we can also combine faulty positives and faulty negative detection to further push this number to 79.4%. For example, this is much better than what was achieved by prior work that do not fully account for these faulty correspondences. Also in practice, standard data sets that we used in this work are often very well curated. And so I would expect these gains to be even larger if applied to real world and curated data. In fact, one type of data where faulty correspondences appear frequently is in videos of daily tasks in egocentric data. In fact, most of the times, the audio and video in these cases are actually very uncorrelated. The exception is when there are interactions that are occurring between human and objects while they are performing these daily tasks. So in a follow-up work, which has not been released yet, but it will be soon, so stay tuned. So in this work, we showed that by focusing on these moments of interaction, and so try to prevent the use of these faulty correspondences, this is actually key to learn good representations from egocentric data and for these egocentric related tasks. Big shout out to Iman Vital, which was this student leading this project. Okay, so let's now move on to the second part of the talk. In the first part, the goal was to learn global representations of both the video and the audio that can match to each other. However, in these representations, we cannot locate where the sound is coming from. What are the objects producing the sound? This second part of the talk will be about just that. How can we localize the sound sources in the video and hopefully being able to do this effectively without using direct supervision for this task. Imagine that you have an image that, for example, could contain multiple objects, could be a complex image or a video and the corresponding sound. The idea is that we should be able to train a model that when given this as input, they should be able to predict what parts of the image are producing the sound. What are the objects that are responsible for that sound? And ideally, we would want to do this without relying on ground truth bounding box annotations or segmentation maps during training. So this problem is often referred to as unsupervised visual sound localization. Now, there's many works that have been trying to develop approaches to this problem. And there are several limitations of prior works. One is that audiovisual correspondence methods, like the one that I presented before, work poorly. And this is simply because the visual representations do not maintain the spatial resolution of the video. New methods try to address some of these problems by using cross-model attention before doing audiovisual matching. This is intuitive, but this presents a paradox because we need to have already accurate localizations in order to learn representations that are able to match the audio to the right regions. And in order to learn those representations, we would be able to already to localize the sound regions. So this is kind of a chicken and the egg problem. Also, this prior work often ignores the fact that most of the audio are often produced by objects, and so we can rely on visual prior that mostly focuses on trying to detect objects in general in order to give a strong prior for this task. In this work, we are proposing a method that tries to address these problems. On one hand, we introduce a way of using this object prior. On the other hand, we propose a new multiple instance contrastive learning objective that really avoids this chicken and the egg problem while still being able to match audio and visual representations with a high spatial resolution. Like before, neural network encoders are used to extract audio and visual representations. However, now we can compute the visual representations for different locations in the image. This could potentially be done using a detection model and ROI pooling, but for simplicity, we just took the output of a convolutional model without global average pooling. Then the audiovisual similarities can be obtained at the different locations to produce the audiovisual localization maps. Now, assuming that the sound source is visible somewhere in the video frame, we can simply align the audio representation with at least one of the local visual representations. This is a multiple instance learning problem, where we know that within each bag of visual features, VI here, at least one of the local feature is a positive. That is, it matches with the audio. Hence, we measure the alignment between the sound and the entire video using the maximum similarity to each of the local visual features. Note that because of this max operation, the supervision here is quite sparse, as only one of the visual features participates in the optimization at a time. This is unlike traditional correspondence methods that operate on global features, where all the video locations need to be matched to the audio representations, or even it's also not like the current attention-based methods where parts of the frame should match the audio representations. However, despite its simplicity, we were able to achieve great localization performance on standard benchmark datasets like Flickr SoundNet and VGG sound sources. Here I'm showing the precision of the localization predictions, assuming an IOU threshold of 50% for 3 different methods. Our method that I just described before is in red. The traditional contrastive learning approaches that operate on global features is shown in green, and an alternative method is shown in blue that maintains a high spatial resolution, like our method, but it uses but pulls the localized audiovisual similarity scores by averaging instead of using the max operation. Hence, all features would also need to be matched with the audio. As can be seen here, the impact of this change on localization performance is quite large. We also show that objects form a strong prior for visual sound localization, as most sounds in nature are produced by objects. These object priors can in principle be obtained from an image alone, as they are not meant to identify sounding objects, they are only meant to identify objects in general. Fortunately, we can leverage existing pre-trained models for either object classification or object detection in order to achieve this, without needing to collect extra supervision for the localization of specific sound sources, or even without training any other models. We can just use the pre-existing pre-trained models. At this time, we can then merge these object-guided localization maps with audiovisual localization simply by weighted average. Here's the localization performance of a model using varying weighting factors on 2 datasets, Flickr SoundNet and VGG sound sources. As can be seen, even though object-guided localization does not even use the audio information, it can achieve performance that is on par with audiovisual localization alone. However, this object bias should actually only be seen as a prior, since we can achieve optimal performance by incorporating further evidence from the audiovisual localization. That means for intermediate values of alpha. Also, comparing to the full method, comparing our full method to the current state of the art, we also see impressive gains. Interestingly, we found that object-guided localization alone already outperforms prior work. Again, this is surprising since object-guided localization does not even use audio in its prediction, showing again the value of an object prior. Here's also a couple of examples of the model in action. The first column here are the ground truth annotations from several humans for the location of the sound source in the video. The second column is the object prior. The third column is audiovisual localization map. And the fourth column is the final merged result. As you can see, all methods were capable of finding the sound sources, but the final merge prediction displays slightly more accurate results. Now, despite these outstanding results, we found several limitations in our work, which also applies to most of existing work. We see that models can easily overfit when trained on audiovisual localization, even with large data sets. And as a result, early stopping becomes a necessary procedure to obtain good results. This is problematic since on one hand, we are not able to fully benefit from scaling up these methods. On the other hand, early stopping defeats the purpose of unsupervised localization altogether, since we need a fully annotated evaluation data set in order to track performance. Second, we found that our method suffers from high false positive rates. That is, it can easily hallucinate the presence of sounding objects, even when none are present. However, current evaluation protocols ignore completely these false positive rates, as all test samples are assumed to contain visible sound sources. This is of course unrealistic, and better evaluation protocols should be developed. Finally, we found that our method also struggles with localizing small sound sources. In my view, we can tackle this problem by using detection-based models instead, which can be better pre-trained for providing object priors for objects of all sizes. In fact, in another follow-up work to this one, which should also come out soon, it's not released yet, we try to address the first two problems. We propose methods to prevent overfitting and to lower these false positive rates. So here a big shout out to Shentong Mo, which has been leading the efforts in these two projects on sound source localization. Once again, if I have not been able to join the workshop and you have questions, comments, or ideas that you want to share, please do reach out. Thanks for listening.
I just wanted to thank all of you for coming. It's been really great to see all of you and be here in person with everyone. I want to thank all the organizers, particularly Rohan, Daffy, Marcia, Nahong, who have been working behind the scenes today, dealing with all sorts of technical problems and everything that could possibly come up. And I also want to thank everyone who participated, both the invited talks, but especially the people who submitted papers for the workshop. I'm really excited to see so much interesting work. So thanks everyone. I'm excited to interact with you throughout the rest of the week.